Apache Spark is an open-source distributed computing system that can process large amount of data quickly. It is designed to handle both batch processing and real-time streaming, making it a powerful tool for data processing and analytics. Hi everyone, welcome to this Apache Spark Full Course. Today we have an exciting agenda lined up for you. But before we get started, if you like our videos, then please do not forget to subscribe to our Edureka YouTube channel and hit the bell icon to stay updated with all the latest trending technologies. Also, if you are interested in our Apache Spark certification training, then please click on the link given in the description box. Now, without any delay, let us go through the agenda. In this session, we will be covering a wide range of topics related to Apache Spark, including what is Apache Spark. Here, we'll be giving you an overview of what Apache Spark is and its use cases. Then we'll move on to the Apache Spark architecture. In this, we'll look into various components of Spark architecture, including the driver, executor, and cluster manager. Next, we'll see how to become a Spark developer. Moving further, we'll understand what is Scala and what is RDD in Spark. Then we have Spark DataFrame. Up next, we'll look into Spark SQL, then Spark Streaming. Here we will give you an overview of Spark Streaming and how it can be used for real-time data processing. Then we have Machine Learning using Spark ML library. Next, we'll move on to the Spark GraphX, where you will be having a hands-on using GraphX in Spark. After that, we have Spark Java. Then we will compare Hadoop MapReduce and Spark, followed by Apache Kafka with Spark Streaming. Then we have PySpark, where you will have an overview of PySpark and resources for learning PySpark. Finally, we will wind up the session with some of the most important Apache Spark interview questions. So, if you are ready to learn more about Apache Spark, then let's get started.
What is Spark? Spark is an open-source, scalable, massively parallel in-memory execution environment for running analytics applications. You can just think of it as an in-memory layer that sits above the multiple data stores, where data can be loaded into the memory and analyzed in parallel across a cluster. Coming to big data processing, much like MapReduce, Spark works to distribute the data across a cluster and then process that data in parallel. The difference here is that unlike MapReduce, which shuffles the files around the disk, Spark works in memory, and that makes it much faster at processing the data than MapReduce. It is also said to be the lightning-fast unified analytics engine for big data and machine learning. So now, let's look at the interesting features of Apache Spark. Coming to speed, you can call Spark as a swift processing framework. Why? Because it is 100 times faster in memory and 10 times faster on the disk on comparing it with Hadoop. Not only that, it also provides high data processing speed. Next, powerful caching. It has a simple programming layer that provides powerful caching and disk persistence capabilities. And Spark can be deployed through Mesos, Hadoop via Yarn, or Spark's own cluster manager. As you all know that Spark itself was designed and developed for real-time data processing, so it's an obvious fact that it offers real-time computation and low latency because of in-memory computations. Next, polyglot. Spark provides high-level APIs in Java, Scala, Python, and R. Spark code can be written in any of these 4 languages. Not only that, it also provides a shell in Scala and Python. These are the various features of Spark. Now, let's see the various components of Spark ecosystem. Let me first tell you about the Spark core component. It is the most vital component of Spark ecosystem, which is responsible for basic I/O functions, scheduling, monitoring, etc. The entire Apache Spark ecosystem is built on the top of this core execution engine, which has extensible APIs in different languages like Scala, Python, R, and Java. As I have already mentioned that Spark can be deployed through Mesos, Hadoop via Yarn, or Spark's own cluster manager. The Spark ecosystem library is composed of various components like Spark SQL, Spark Streaming, Machine Learning Library. Now, Let me explain you each of them. The Spark SQL component is used to leverage the power of declarative queries and optimize storage by executing SQL-like queries on Spark data, which is present in the RDDs and other external sources. Next, Spark streaming component allows developers to perform batch processing and streaming of data in the same application. And coming to machine learning library, it eases the deployment and development of scalable machine learning pipelines like summary statistics, correlations, feature extraction, transformation functions, optimization algorithms, etc. And GraphX component lets the data scientist to work with graph and non-graph sources to achieve flexibility and resilience in graph construction and transformation. And now talking about the programming languages, Spark supports Scala. It is a functional programming language in which the Spark is written. So, Spark supports Scala as an interface. Then, Spark also supports Python interface. You can write the program in Python and execute it over the Spark. Again, if you see the code in Python and Scala, both are very similar. Then, R is very famous for data analysis and machine learning. So, Spark has also added the support for R, and it also supports Java. So, you can go ahead and write the code in Java and execute it over the Spark. Next, the data can be stored in HDFS, local file system, Amazon S3 Cloud, and it also supports SQL and NoSQL database as well. So this is all about the various components of Spark ecosystem. Now let's see a real-time use case. Here I'm considering Yahoo as an example. So what are the problems of Yahoo? Yahoo properties are highly personalized to maximize relevance. The algorithms used to provide personalization, that is the targeted advertisement, and personalized content are highly sophisticated. And the relevance model must be updated frequently because stories, newsfeed, and ads change in time. And Yahoo has over 150 petabytes of data that is stored on 35,000 node Hadoop cluster, which should be accessed efficiently to avoid latency caused by the data movement and to gain insights from the data in cost-effective manner. So to overcome these problems, Yahoo looked to Spark to improve the performance of its iterative model training. Here, the machine learning algorithm for news personalization required 15,000 lines of C++ code. On the other hand, the machine learning algorithm has just 120 lines of Scala code. So that is the advantage of Spark. And this algorithm was ready for production use in just 30 minutes of training on 100 million datasets. And Spark's rich API is available in several programming languages and has resilient in-memory storage options and is compatible with Hadoop through Yarn and the Spark Yarn project. It uses Apache Spark for personalizing its news web pages and for targeted advertising. Not only that, it also uses machine learning algorithms that run on Apache Spark to find out what kind of news users are interested to read, and also for categorizing the news stories to find out what kind of users would be interested in reading each category of news. And Spark runs over Hadoop Yarn to use existing data and clusters. And the extensive API of Spark and machine learning library is the development of machine learning algorithms. And Spark reduces the latency of model training via in-memory RDD. So this is how Spark has helped Yahoo to improve the performance and achieve the targets. So this is the Spark architecture. In your master node, you have the driver program which drives your application. So the code that you're writing behaves as a driver program, or if you're using the interactive shell, the shell acts as a driver program. Inside the driver program, the first thing that you do is you create a Spark context. Assume that the Spark context is a gateway to all Spark functionality. It is similar to your database connection. So any command you execute in your database goes through the database connection. Similarly, anything you do on Spark goes through the Spark context. Now, this Spark context works with the cluster manager to manage various jobs. The driver program and the Spark context takes care of executing the job across the cluster. A job is split into the tasks, and then these tasks are distributed over the worker node. So anytime you create a RDD in the Spark context, that RDD can be distributed across various nodes and can be cached there. So RDD is set to be taken, partitioned, and distributed across various nodes. Now, worker nodes are the slave nodes whose job is to basically execute the tasks. The task is then executed on the partition RDDs in the worker nodes, and then returns the result back to the Spark context. Spark context takes the job, breaks the job into the tasks, and distributes them on the worker nodes. And these tasks works on partition RDDs, perform whatever operations you wanted to perform, and then collect the result and give it back to the main Spark context. If you increase the number of workers, then you can divide jobs in more partitions and execute them parallelly over multiple systems. This will be actually a lot more faster. Also, if you increase the number of workers, it will also increase your memory and you can cache the jobs so that it can be executed much more faster. So this is all about Spark architecture. Now let me give you an infographic idea about the Spark architecture. It follows master-slave architecture. Here, the client submits Spark user application code. When an application code is submitted, driver implicitly converts a user code that contains transformations and actions into a logically directed graph called DAG. At this stage, it also performs optimizations such as pipelining transformations. Then, it converts a logical graph called DAG into physical execution plan with many stages. After converting into physical execution plan, it creates a physical execution units called tasks under each stage. Then, these tasks are bundled and sent to the cluster. Now, driver talks to the cluster manager and negotiates the resources. And cluster manager launches the needed executors. At this point, driver will also send the task to the executors based on the placement. When executors start, they register themselves with the drivers, so that driver will have a complete view of the executors. And executors now start executing the tasks that are assigned by the driver program. At any point of time when the application is running, driver program will monitor the set of executors that runs. And the driver node also schedules a future task based on data placement. So this is how the internal working takes place in Spark architecture. There are 3 different types of workloads that Spark can cater. First, batch mode. In case of batch mode, we run a batch job. Here, you write a job and then schedule it. It works through a queue or batch of separate jobs through manual intervention. Next, interactive mode. This is an interactive shell where you go and execute the commands one by one. So you will execute one command, check the result, and then execute the other command based on the output result and so on. It works similar to the SQL shell. So shell is the one which executes a driver program. So it is generally used for development work or it is also used for ad hoc queries. Then comes the streaming mode where the program is continuously running. As in when the data comes, it takes the data and do some transformations and actions on the data and then produce output results. So these are the 3 different types of workloads that Spark actually caters. Now let's move ahead and see a simple demo. Here, let's understand how to create a Spark application in Spark Shell using Scala. So let's understand how to create a Spark application in Spark Shell using Scala. Assume that we have a text file in the HDFS directory and we are counting the number of words in that text file. So let's see how to do it. So before I start running, let me first check whether all my daemons are running or not. So I'll type sudo jps. So all my Spark daemons and Hadoop daemons are running. That I have master, worker as Spark daemons and name node, resource manager, node manager, everything as Hadoop daemons. So the first thing that I do here is I run the Spark shell. So it takes a bit time to start. In the meanwhile, let me tell you the web UI port for Spark shell is localhost 4040. So this is a web UI for Spark. Like if you click on jobs, right now we have not executed anything. So there is no details over here. So you have jobs, stages. So once you execute the jobs, you will be having the records of the tasks that you have executed here. So here you can see the stages of various jobs and tasks executed. So now let's check whether our Spark shell has started or not. Yes, so you have your Spark version as 2.1.1 and you have a Scala shell over here. So before I start the code, let's check the content that is present in the input text file by running this command. So I'll write var test is equal to sc.text file because I have saved a text file over there, and I'll give the HDFS path location. I've stored my text file in this location and sample is the name of the text file. So now let me give test.collect so that it collects the data and displays the data that is present in the text file. So in my text file, I have Hadoop, research, analyst, data, science, and science. So this is my input data. So now let me map the functions and apply the transformations and actions. So I'll give var map is equal to sc.text file, and I will specify my input path location. So this is my input path location, and I'll apply the flat map transformation to split the data that is separated by space, and then map the word count to be given as word, 1. Now this will be executed. Yes. Now let me apply the action for this to start the execution of the task. So let me tell you one thing here. Before applying an action, the Spark will not start the execution process. So here I have applied reduce by key as the action to start counting the number of words in the text file. So now we are done with applying transformations and actions as well. So now the next step is to specify the output location to store the output file. So I'll give as counts.save as text file and then specify the location for my output file. I'll store it in the same location where I have my input file, and I will specify my output file name as output9. Cool. I forgot to give a double quotes, and I will run this. So it's completed now. So now let's see the output. I will open my Hadoop web UI by giving localhost 50070 and browse the file system to check the output. So as I have said, I have example as my directory that I have created, and in that I have specified output9 as my output. So I have the two part files being created. Let's check each of them one by one. So we have the data count as 1, analyst count as 1, and science count as 2. So this is the first part file. Now let me open the second part file for you. So this is the second part file where you have Hadoop count as 1 and the research count as 1. So now let me show you the text file that we have specified as the input. So as I have told you, Hadoop count is 1, research count is 1, analyst 1, data 1, science and science as 1, 1. So you might be thinking data science is a one word. No. In the program code, we have asked to count a word that is separated by a space. So that is why we have science count as 2. I hope you got an idea about how word count works. Similarly, I will now parallelize 1 to 100 numbers and divide the task into 5 partitions to show you what is partitions of task. So I will write sc.parallelize 1 to 100 numbers and divide them into 5 partitions and apply collect action to collect the numbers and start the execution. So it displays you an array of 1 to 100 numbers. Now let me explain you the jobs, stages, partitions, event timeline, DAG representation and everything. So now let me go to the web UI of Spark and click on jobs. So these are the tasks that you have submitted. So coming to word count example. So this is the DAG visualization. I hope you can see it clearly. First you collected the text file, then you applied flat map transformation and mapped it to count the number of words, and then applied reduce by key action and then saved the output file as save as text file. So this is the entire DAG visualization of the number of steps that we have covered in our program. So here it shows the completed stages, that is 2 stages. And it also shows the duration, that is 2 seconds. And if you click on the event timeline, it just shows the executor that is added. And in this case, you cannot see any partitions because you have not split the jobs into various partitions. So this is how you can see the event timeline and the DAG visualization. Here you can also see the stage ID, descriptions, when you have submitted that. I have just submitted it now. And in this, it also shows the duration that it took to execute the task and the output bytes that it took, the shuffle read, shuffle write, and many more. Now to show you the partitions, see, in this you just applied sc.parallelize, right? So it is just showing one stage where you have applied the parallelized transformation. Here it shows the succeeded task as 5 by 5. That is, you have divided the task into 5 stages and all the 5 stages has been executed successfully. Now here you can see the partitions of the 5 different stages that is executed in parallel. So depending on the colors, it shows the scheduler delay, the shuffle read time, executor computing time, result serialization time and getting result time, and many more. So you can see the duration that it took to execute the 5 tasks in parallel at the same time is maximum 1 milliseconds. So in memory, Spark has a much faster computation. And you can see the IDs of all the 5 different tasks. All are success. You can see the locality level. You can see the executor and the host IP ID, the launch time, the duration it take, everything. So you can also see that we have created RDD and parallelized it. Similarly, here also for word count example, you can see the RDD that has been created and also the actions that you have applied to execute the task. And you can see the duration that it took. Even here also it's just 1 milliseconds that it took to execute the entire word count example. And you can see the IDs, locality level, executor ID. So in this case, we have just executed the task in 2 stages. So it is just showing the 2 stages. So this is all about how Web UI looks and what are the features and information that you can see in the Web UI of Spark after executing the program in the Scala shell. So in this program, you can see that first we gave the path to the input location and checked the data that is presented in the input file. And then we applied flat map transformations and created RDD. And then applied action to start the execution of the task and save the output file in this location. So I hope you got a clear idea of how to execute a word count example and check for the various features in Spark Web UI like partitions, DAG visualizations, and everything.
So here are a few reasons why Spark is considered to be the most powerful big data tool in the current year. Firstly, its ability to integrate itself with Hadoop. Spark can be integrated well with Hadoop, and that's a great advantage for those who are familiar with latter. Technically, a standalone project. Spark has designed in the way to run on Hadoop Distributed File System or HDFS. It can be straightaway got into work with MapR. It can run on HDFS inside MapReduce. Having deployed on Yarn, it can even run on the same cluster along the side of MapReduce jobs. Followed by the first reason, the second reason says that it can meet the global standards. According to the technology forecast, Spark is the future of worldwide big data processing. The standards of big data analytics are rising immensely with Spark and driven by high-speed data processing and real-time results. By learning Spark now, one can meet the global standards to ensure compatibility between next generation of Spark applications and distributions by being a part of Spark developers community. If you think you love technology, contributing in the development of growing technology and its growing stage can give a boost to your career. After this, you can stay up to date with latest advancements that take place in Spark and be among the initial ones to build the next generation of big data applications. The third reason says that it is highly faster than MapReduce because Spark is an in-memory data processing framework and is all set up to take all the primary processing for Hadoop workloads in future. Being way faster and easier to program than MapReduce, Spark is now among the top-level Apache projects, which has acquired the appraisal of large community of users as well as contributors. Batai Zaharia, CTO Databricks and one of the brains behind Apache Spark projects, puts forth Spark as a multi-phased query tool that could help democratize the use of big data. He also projected the possibility of end of MapReduce era with the growth of Apache Spark. Followed by the third reason, we have the fourth reason which says Spark is capable to perform in production environment. The number of companies that are using Spark or are planning to the same has exploded over the last year. There is a massive surge in the popularity of Spark. The reason being is its matured open source components and an expanding community of users. The reasons why Spark has become one of the most popular projects in big data are the ingrained high-performance tools handling distinct problems and workloads and a swift and simple programming interface in high-end programming languages like Scala, Java, and Python. There are several reasons as to why enterprises are increasingly adopting Spark, ranging from speed and efficiency and ease of use to single integrated system for all the data pipelines and many more. Spark, being the most active big data project, has been deployed in production by all major Hadoop as well as non-Hadoop vendors across multiple sectors including financial services, retail, media houses, telecommunications, and public sectors. Now, the last important reason for Spark being so powerful is its rising demand for Spark developers. Spark is a brand new and yet completely spread out in the big data market. The use of Spark is increasing at a very fast speed among many of the top-notch companies like NASA, Yahoo, Adobe, and many more. Apart from those belonging to Spark community, there is a handful of professionals who have learned Spark and can work with it. This in turn has created a soaring demand for Spark developers. In such scenario, learning Spark can give you a steep competitive edge. By learning Spark at this point in time, you can demonstrate the recognized validation for your experience. This is what John Triper and Alliances and Ecosystem Lead at Databricks has to say. The adoption of Apache Spark by business, large and small, is growing at an incredible rate across a wide range of industries, and the demand for developers with certified expertise is quickly following suit. So these were the few important reasons why Apache Spark is considered to be the most powerful tool in the current IT industry. Let's move ahead and understand the roadmap to become an Apache Spark developer. There is always a thin line of gap between actually becoming a certified Apache Spark developer and to be an actual Spark developer capable enough to perform in real-time application. So how do we become a certified Apache Spark developer who is capable to perform in real time? So the step-by-step approach to the same is given as below. To become an expert level Spark developer, you need to follow the right path and the expert level guidance from the certified real-time industry experts in the industry. For a beginner, it is the best time to take up a training and certification exam. Once the certification has begun, you should start up with your own projects to understand the working terminology of Apache Spark. Spark's major building blocks, which are the RDDs or Resilient Distributed Datasets and DataFrames. Also, Spark has the capability to integrate itself with high-performance programming languages like Python, Scala, and Java. PySpark RDDs are the best examples for the combination of Python and Apache Spark. You can also understand how to integrate Java with Apache Spark through an amazing article called Spark Java Tutorial Article from Edureka, which I have linked in the description box below. Once you have the better grip on the major building blocks of Spark, which are the RDDs and DataFrames, you can move ahead into learning some of the major components of Apache Spark, which are mentioned as below, which are the Spark SQL, Spark Mlib, Spark GraphX, Spark R, and Spark Streaming, and a lot more. Once you get the required training and certification, it's time for you to take most important and bigger leap, the CCA 175 certification. You can begin solving some sample CCA 175 and Spark certification examination papers, which I have linked in the description box below. And once you get a briefer idea and confidence, you can register for the CCA 175 examination and excel with your true Spark and Hadoop developer certification. So this is the roadmap to become a true and certified Apache Spark developer. Now that we have discussed about the roadmap to become an Apache Spark developer, let us move ahead and discuss about the Apache Spark developer's salary. Apache Spark developer is one of the most highly decorated professionals with handsome salary packages compared to others. We will now discuss the salary trends of Apache Spark developers in different nations. First, India. In India, the average salary offered to an entry-level Spark developer is between 6 lakhs to 10 lakhs per annum. And on the other hand, for an experienced level Spark developer, the salary trends are in between 25 lakhs to 40 lakhs per annum. Next, the United States of America. In the United States of America, the salary offered for a beginner level Spark developer is $75,000 to $100,000 US per annum. Similarly, for an experienced level Spark developer, the salary trends lie between $145,000 to $175,000 per annum. Now with this, let us move ahead and discuss the skills of a Spark developer. The skills required to become an excellent Spark developer are to be capable enough to load the data from different platforms into Hadoop platform using various ETL tools. Decide an effective file format for a specific task. Based on business requirements, clean data through streaming API or user-defined functions. Effectively schedule Hadoop jobs, hand-holding with Hive and HBase for schema operations. Followed by that, you should have a capability to work on Hive tables and to assign schemas. Deploy HBase clusters and continuously manage them. Execute Pig and Hive scripts to perform various joins in datasets. apply different HDFS formats and structures like to speed up analytics, maintaining the privacy and security of Hadoop clusters, fine-tuning of Hadoop applications, troubleshooting and debugging any Hadoop ecosystem at runtime, and finally, installing, configuring, and maintaining enterprise Hadoop environment if required. Now, we shall move ahead and understand the Apache Spark developer's roles and responsibilities. The roles and responsibilities of a Spark developer are to be capable enough to write executable code for analytics services and Spark components, knowledge in high-performance programming languages like Java, Python, and Scala, should be well versed with related technologies like Apache Kafka, Storm, Hadoop, and Zookeeper, ready to be responsible for system analysis that include design, coding, unit testing, and other software development lifecycle activities, gathering user requirements and converting them into strong technical tasks and provide economical estimates for the same. Should be a team player with global standards so as to understand project delivery risks. Ensure the quality of technical analysis and expertise in solving issues. Review code, use case, and ensure it meets the requirements. So these were the few roles and responsibilities of a Spark developer. Now let us move ahead and learn the companies that are using Apache Spark. Apache Spark is one of the widest spread technology that has changed the faces of many IT industries and helped them to achieve their current accomplishments and further. Let us now discuss some of the tech giants and major players in IT industries that are under the use of Spark. Few of the companies are Oracle, Dell, Yahoo, CGI, Facebook, Cognizant, Capgemini, Amazon, IBM, LinkedIn, Accenture, and many more. What is Scala? Scala is a programming language invented by Martin Odesky and his research group in the year 2003. The name Scala depicts about the scalability that the language offers. Now you can raise a question, aren't the other latest programming languages like Python, Ruby, Perl, and the legendary Java not scalable? The answer is yes, they are scalable, but with some limitations, for the same reasons for which the Scala was invented. Scala minimizes the code length and reduces the execution time. It is basically derived from Java. It was in the year 2006 when Twitter was first introduced in America, and the developers used Ruby on Rails as their weapon of choice to develop this application, which later proved out to be the wrong choice when they had to manage the huge amount of big data which was dropping in. It was then when they switched their back into Java and used Scala as their new programming language to handle the big data using Hadoop and Spark frameworks. Hadoop can work with both Java and Scala, but Spark is designed to work only with Scala. In case if you would like to learn big data with Spark framework, learning Scala would be most important. Scala is considered as a compiler-based multi-paradigm language which is concise, fast, and efficient. The major advantage of Scala is the JVM. The Scala code is first compiled by Scala compiler and the bytecode for the same is generated, which will be transferred to the Java virtual machine to generate the output. Thus, the Scala became the key to the success for managing huge amount of big data. Now that we have understood the importance of Scala, let us now understand why actually it is the most preferred language in the present trends. The technological advancements have led us to the invention of octa-core processors, and the programmers are also looking for a language which could process with a higher pace using all the available resources. Now Scala is one such programming language which is capable to work with data which is in a distributed fashion and can access all the available resources to support the parallel data processing. Scala is an upgraded version of Java. Scala eliminates all the boilerplate codes and has multiple libraries and API supports which will allow the programmer to use it with ease. It eliminates all the hectic process of learning all the APIs and libraries involved in the process. The core reason for which the programmers fall in love with Scala because it is an immutable language. Scala supports immutable data and it has support to the higher order functions. Higher order functions can be defined as a function where the programmer can pass an entire function as a parameter to another new function. Scala supports multiple type constructs which will enable the programmer to work with wrappers or container types with ease. Now that we have understood the needs for which we needed Scala, let us move into the powerful features which give it an edge over the other existing programming languages. The first feature is Scala is an object-oriented programming language. Scala is both functional programming language as well as an object-oriented programming language. Every variable and value which is used in Scala is implicitly saved as an object by default. The second feature is Scala is an extensible programming language. Scala can support multiple language constructs without the need of any domain-specific language extensions, libraries, or APIs. The third feature is Scala is a statically typed programming language. Scala binds the declared data type of the variable along with it until the variable's entire scope throughout the program. The fourth feature is Scala is a functional programming language. Scala provides a lightweight syntax for defining anonymous functions. It allows functions to be nested. It also supports higher order functions. The fifth feature is Scala is interoperatable. Scala compiles the code using a Scala compiler and generates a respective Java bytecode which will be later transferred to the JVM in order to generate an output. So these were the features of Scala. Now let us get into the frameworks which are supported by Scala. So these are the few examples for the frameworks which Scala can support. Scala can support Akka, Spark, Play, Neo4j, Scalding, and many more frameworks. Akka is a toolkit on runtime for building highly concurrent, distributed, and fault-tolerant applications on JVM. Akka is an approach to handle concurrency based on actor model. Akka is written in Scala with language bindings provided for both Scala and Java. Spark framework is designed to handle and process big data, and it solely supports Scala. Play framework is designed to create web applications, and it uses Scala in the process in order to obtain the best-in-class performance. Scalding is a DSL or domain-specific language in Scala programming language. It integrates cascading. It is a functional programming paradigm used in Scala, which is much closer to the Java in original model for MapReduce functions. Neo4j is a Java Spring framework supported by Scala with domain-specific functionality, analytical capabilities, graph algorithms, and many more. So with this, we are done with our theory part. Now let us enter into the practical part. So first, let us understand the data types in Scala. So these are the few data types which are present in Scala. Let us discuss about each and every one of them in detail. So the first data type is any. It is considered as a super data type. Second data type is anyval. It is used to represent any value type. The third data type is anyref. It is considered as a subtype of a reference type. The fourth data type is double. We all know that double is a 64-bit precision float data type. The fifth data type is float. It is a 32-bit precision float data type. The sixth one is long. It is a 64-bit signed value. The seventh one is integer. It is a 32-bit signed value. Now, the eighth one is short data type, which is considered as a 16-bit signed value. And the ninth one is byte. It is an 8-bit signed value. The 10th one is unit. It corresponds to no value. And the 11th one is boolean, which is true or false. 12th one is character, which is 16-bit unsigned Unicode character. And the 13th one is null, which is null or empty reference. And the last one is nothing data type. It is considered as a subtype of every type and it does not include any values. So with this, we finish the data types in Scala. Now let us discuss about the variables in Scala. We all know that the variables are considered as reserved memory locations which are used to store the values. Now the variables in Scala are mainly divided into two types, immutable and mutable. So let us understand mutable and immutable variable types in Scala in detail. Mutable variable types are the variables which are declared using the keyword var, where you can reassign the values to the pre-declared variables. And immutable data type in Scala is declared using the keyword val, where after declaring a value to the variable, it cannot be reassigned. As you can see, the codes below explain the details. Now, let us understand the following in practical. So here, I have declared a variable a using the keyword var, and I have stored an integer value 10 into the variable a. So this is a mutable variable type which can be reassigned to a different value. So the value is been declared. Now let us try to reassign a different value to the same variable a, and let us check out if it accepts or not. So the variable has clearly accepted the new value. Now let us try to understand the immutable type of variables. Now I'm declaring a new variable a using the keyword val, which happens to be an immutable type of variable in Scala. Now I have declared an integer type value to the variable a. So the value is successfully accepted. Now let us check if it accepts a different value or not. As you can see, it has thrown an error saying reassignment to val, which says it cannot accept a new value to the predefined val type of variable, which happens to be immutable. Now we shall check with the string data types. Here I'm creating a variable b of mutable type and I'm assigning a string value to it. And it has successfully accepted the string value. Now let us try to reassign a string type value to the variable b. As you can see, it has accepted a different string value and it is displaying here. This proves that it is a mutable type of variable. Now let us try to perform a few mathematical operations on our Scala REPL. So here I have declared a block of code which has an immutable type of variable x, which stores the summation of two different variables which are of immutable type, which is a equal to 100 and b is equal to 200. Now I'm about to perform an addition operation on the two variables and store the value into the new variable which is x. The operation is successfully performed and the value 300 is stored into the variable x. So this was a shorter block of code, so it has been successfully executed. Now imagine if you are calculating for 1 million numbers. It might be time consuming and it might be an additional pressure on the processor. For the same reason for which Scala developed lazy variables. Now we shall perform a lazy evaluation which will explain us in detail about lazy variables. Here I've created a new variable x of immutable type using the keyword lazy, which makes the variable as a lazy variable. As you can see, it is a lazy variable of integer type and the name of the variable is x. Now let us perform a multiplication operation on the lazy variable x in order to generate an output. As you can see, I'm multiplying the value x by 2 to generate the output. Now we have the output 200. Here, what happened is, it is accessing the values of x only when I'm performing an action onto it. Until then, no memory is allocated and no action is performed on the lazy variable x. So with this, let us move into the collections in Scala. The collections in Scala are as follows: arrays, lists, sets, maps, and tuples. So let us discuss about each and every one of them in detail. The first one is arrays. We all know that array is a data structure which stores fixed size sequential collection of elements which are of same data type. We shall look into a few examples of arrays in Scala. Here I am creating a new array of immutable type and the name of the array is array, and I am allocating 10 memory allocations of integer type. The array has been successfully stored and the default value 0 is been stored. So the new immutable type of array is been declared and it has stored 0 as the default value in all its memory locations. We can add an element by accessing the array memory locations. For example, I am trying to store a value 10 into the 0th location of the array. Now let us print the array. As you can see, the integer value 10 is been successfully loaded into the first location of the array and it has been displayed here. Now let us try an array of string type. I have stored an array of string type and my elements are Edureka Brainforce organization. Now let us print the values present in our myString array. So here is the data which is present in my string array, which is Edureka Brainforce organization. Now let us discuss about array buffers. Before going to access the array buffers, we need to import the library called array buffer, and the following code will import the array buffer. The library has been successfully imported. Now let us work with array buffers. Here I am creating an array buffer of immutable type, which is a, and I am storing data of integer type. The array buffer has been successfully created. Now let us add values into it. We can add a single value by using the following code into the array buffer. The element 1 is successfully added into the array buffer and you can see it. Now let us try to add multiple elements into the array buffer. As you can see, I am trying to add multiple elements into the array buffer, which are 2, 3, 4, and 5. As you can see, the elements are successfully added and the present elements in the array buffer are 1 to 5. Now let us try to add a complete array into the array buffer. Here I am trying to add the array 6, 7, 8 into the array buffer using the following code. As you can see, the complete array is also been added into the array buffer and the output has been displayed, which has the elements starting from 1 to 8. Now we shall try to perform some operations on array buffer. The first operation I'm trying here is trim. Here I'm trying to trim the last end of the array buffer, which are the 7 and 8 elements. Here I'm describing them by using the number 2, which describes to delete the elements of last 2 elements from the array buffer. Now let's try out the code. Yeah, the operation has been successfully applied. Now let us see the elements which are present in our array buffer. As you can see, the last 2 elements have been trimmed out and the remaining elements are starting from 1 to 6. Now let us try to perform a next operation. The next operation I'm trying out to insert a new element into the second location of the array buffer. I'm trying to insert number 9 into the second location by using the following code. As you can see, the operation has been successfully applied. Let us display the data. As you can see, the number 9 has been successfully inserted into the second memory location of the array buffer. Now let us try to perform a next operation. Now let us try to insert multiple numbers in the location number 2. Here I'm trying to insert the numbers 0, 9, 6 and 1 inside the memory location 2. As you can see, the numbers are successfully inserted. Now let's display the data. The numbers 0, 9, 6, 1 are successfully inserted from the memory location 2 and the data has been successfully displayed. Now let us try to remove an element from the memory location 2 using the remove keyword. The element has been successfully removed, which was 0. As you can see, 0 is in the second memory location of the array buffer A. Now let us try to print the data. As you can see, 0 has been eliminated and the remaining numbers are present in the array buffer. Now let us try to remove multiple elements from the memory location 2. Here, I am specifying the memory location 2 and I want to remove 3 elements starting from the memory location 2. As you can see, the code has been successfully executed and 3 elements from the memory location 2 have been eliminated. Now let us display the data of array buffer A. As you can see, the elements 9, 6, 1 have been eliminated and the remaining elements are displayed here, which are 1, 2, 9, 3, 4, 5, 6. Now let us try to declare an array with the numbers 1, 2, 3, 4 and find out the sum of all the elements present in that array using the following code. As you can see, the sum of all the elements present in an array 1, 2, 3, 4 is 10, which is displayed here. Now let us try to find out the maximum element in an array using the following code. As you can see, I am using the keyword max in order to find out the maximum element in the present array, which happens to be 4, which is displayed here. We all know that arrays also support sorting. Here, we shall try to sort out the given array, which has the elements 1, 5, 3, 2, 4. As you can see, they are not in a sorted order. Let us use the following code to sort them. As you can see, the elements are sorted. Now let us display the data present in the array A. As you can see, the elements are in a sorted order now, starting from 1 to 5. With this, we finish with arrays. Now let us move into lists. The Scala list is an immutable sequence of elements implemented as a linked list. Unlike an array, a linked list consists of many small objects, each containing a reference to the object as well as the reference to the rest of the list. Now we shall look into a few examples of lists in Scala. We shall begin with creating a Scala object of lists. The following code can be used to create a list of object type in Scala. As you can see, the list is created in object type and the elements 1, 2, 3 are stored in there. Now we shall try to declare a normal kind of list, which can be declared by using the following code. The list has been successfully created and the integer type of values are stored in the list. Now let us create a new list X and let us try to add elements into the list. The element 2 has been successfully added into the list. Now let us try to add few more elements into the same list. I am trying to add the value 1 into the same list X as an object. As you can see, the elements 1 and 2 both are inserted into the same list X as objects. Now let us try to add one more element into the same list. Now I am adding 0 element into the same list X as an object using the following code. As you can see, all the 3 elements are added into the same list X as objects. Now we shall try to delete some elements from the list. Here I am declaring a new list by name original list and I'll apply filter operations onto the list to delete the elements which are less than 2. The following code will help us to delete the elements which are less than 2. As you can see, the filter operation has been successfully applied and the elements which are less than or equal to 2 have been eliminated and the remaining elements 5, 4, 3 have been displayed. Now let us understand list buffers. Before accessing list buffers, we need to import the library list buffer. The following code will help us to import the library. The list buffer library has been successfully imported. Let us work with our examples. Here I'm creating a new list using the keyword list buffer and I'm trying to insert the elements starting from 1 to 9. The list buffer has been successfully created now. Let us try to perform our further operations on the list buffer. The first operation would be trying to remove an element from the list buffer. Here I'm using the keyword remove to remove the element which is present in the list buffer's first location, which is 0th location. So the first element in the 0th location is element 1. Let us try to perform this operation. The operation has been successfully performed and the element 1 is been removed. Let us display the data. As you can see, the element 1 is been eliminated and we have the remaining elements in the list buffer. Now let us try to create a list buffer using the range method. Here I'm using the keyword range to generate a list of numbers between 1 to 10. As you can see, the list has been successfully created and we have the elements starting from 1 to 9, excluding 10, which happens to be the range of the numbers. We can also create a list using range function in a stepwise manner. Here I'm providing 2 as a step count, which will generate the numbers starting from 1 to 10. As you can see, the data has been successfully ingested into the list X in the following stepwise count of 2. The list can also be generated using the fill method. Here I'm using fill keyword in order to generate a new list which will be having the text apple for 3 times. As you can see, the list has been successfully generated and string apple is been repeated for 3 times and stored in the new list. Lists can also be created using a tabulate method, where you can provide a condition according to which the numbers will be inserted into the list. Here I'm using tabulate keyword and I'm using the function which is n is equals to n plus n, which will add the numbers and store the details into the new list X. As you can see, the value to my variable n was 5 and according to the condition n plus n, we have the numbers ingested into the following list X. 0 plus 0 is 0, 1 plus 1 is 2, 2 plus 2 is 4, 3 plus 3 is 6 and 4 plus 4 is 8. Now let us try to perform merge operation on any two lists. Let me create a new list. So here I'm creating a new list by name A and I'm storing 1, 2, 3 elements into the new list. And now let us create another new list by name B and store different values into that list and finally try to concatenate them both. Here both the lists are created now, which are A and B. Now let us try to concatenate them using the following code and store the data into the new list C. As you can see, we have created two new lists A and B. And next we have used the following code to concatenate both the list A and B and store the value into the new list which is C. Here we can see the elements of list A and the elements of list B stored into the new list C. Now we shall learn about list buffers. Before we work with list buffers, we need to import the library list buffer. The list buffer has been successfully imported. Now let us look into a different example of list buffers. Here I'm creating a new list buffer flowers where I'll be inserting string data type. The flowers list buffer has been successfully created. Now let's try to add the elements into it. Here I have added 3 elements, rose, lily and tulip into the list buffer using the following codes. Now let us try to add multiple elements into the list buffer using the following code. Here I'm trying to insert daisy, sunflower and jasmine into the list buffer flowers using the following code. The new data has been successfully loaded into the list buffer flowers and the data has been displayed. Now let us try to delete the elements from the list buffer. Here I'm using the following code to remove the element rose from the list buffer. You can see the rose is been eliminated from the list buffer and the remaining elements are been displayed here. Now let us try to remove multiple elements from the list buffer. I'm using the following code to remove 2 elements at a time from the list buffer flowers, which are lily and tulip. So the lily and tulip have been eliminated from the list buffer and the remaining elements have been successfully displayed. We can also remove the elements in a sequential manner. Here I'm trying to remove daisy and sunflower in a sequential manner using the following code. As you can see, the elements daisy and sunflower which were in a sequence have been successfully eliminated from the flowers list buffer and the remaining element which is jasmine has been displayed here. Now let us try to convert this list buffer into list using the following code. I'm using the keyword to list in order to transform the list buffer into the list. The list buffer flowers has been successfully converted into list and the data has been stored into the new list which is flowers list. So with this, we've finished the examples in list. Let us move into the next topic, which is sets. Sets can be defined as a collection that contains no duplicate elements. By default, Scala uses an immutable set. If you want to use mutable set, you'll have to import a library called import Scala collections mutable set class explicitly. We shall try out some examples of sets in Scala. Here I'm trying to create a new set with name S and I'm trying to store integer type of values into the set. The set has been successfully created. Now let us try to add elements into the set. I am deliberately trying to add duplicate contents into the set to try out if it accepts it or not. As you can see, it did not accept duplicate elements. Now let us try to create an immutable set by providing the elements with no duplicate elements. As you can see, the Scala has identified it has to be an immutable set with no duplicate elements. Now let us perform few basic operations on sets. Here I'll create a new set by name fruit, and I'll try to ingest string type of values which are apples, oranges and pears into the set. The set has been successfully created and the values have been ingested. Now let us find out the head of the set. The head of the set is nothing but the starting element present in the set. As you can see, we should be obtaining apples as a result, and we have obtained apples as a result. Now we shall try to print the tail of our set, which must be oranges and pears. Let us use the following code to print the tail of our set. As you can see, the tail of our set is been printed, which is oranges and pears. Now let us check if our set is empty or not using the following code. You can see our set is not empty and Scala has provided as a result as false, which proves that it is not empty. Now let us try to create a new set which is empty and try out the following code if we get the result as true or false. Here I am creating a new empty set num which must be storing integer type of variables. So the empty set has been successfully created. Now let us check if it is empty or not. The following code must help us to find out if the set is empty or not. As you can see, Scala has thrown true, saying that the set nums is empty. Now let us try to perform concatenation operation on sets. We shall create two sets and try to concatenate them. Here I am creating a new set called fruit1 and I am storing string type values apples, oranges and pears into the new set fruit1. And similarly, let us create another set by name fruits2. Fruits2 is been successfully created now. I am storing string type values mangoes, banana and oranges into this fruit2 set. And set has been successfully created. Now let us try to concatenate fruits2 and fruits1 using the following code. Now fruit2 and fruit1 have been concatenated and I've stored the resultant value into the new set which is fruit. Now let us display the data which is present in our fruit. As you can see, the elements of first and second sets have been printed together and the duplicate values have been eliminated. The duplicate value was orange, which was existing both in the list 1 and the list 2. It has been eliminated here and it is printed for only once. Now we shall try to work with mutable sets. In order to create the mutable set, you need to provide the keyword mutable collection. In order to work with mutable sets, you need to provide the keyword scala.collection.mutable. So the mutable set has been successfully created. It must be storing integer type of values inside it. Now let us try to add elements into this new set. The element 1 has been successfully inserted into the set. Now let us try to add multiple elements into the same set. The multiple elements 2 and 3 have been successfully inserted into the set and the result is been displayed here from 1 to 3. Now let us try to add a new element into the set and see whether it can add it or not. I have tried 6. Since it is a new element, the set has accepted the value 6 and provided the result as true. Now let us try to add a number which is previously existing in the set, say 2, and try to add it into the set and see whether it accepts it or not. As you can see, the set did not accept it. It is showing false because 2 is already existing in the set. This proves that the sets will not include duplicate values into them. In order to add duplicate values into the set, you need to convert the set into a list. With this, we've finished sets. Now let us move into the next topic, which is maps. A Scala map is a collection of a key value pair. A map cannot have duplicate keys, but different keys can have same values. We shall try out few examples of maps in Scala. Here I'm creating a new map by name colors1 and I'm assigning a key value pair. Here the key is red and the respective value for the red is #FF0000. And similarly, I'm trying to add another two sets of key value pairs into the map colors1. The first map has been successfully created. Now let me create another map colors2 and insert different colors into it. As you can see, colors2 has been successfully declared with different values of blue, yellow and red. Now we have red in both colors1 and colors2. Now let us use the following code to print the keys present in colors1. As you can see, red, azure, Peru are the three keys present in colors1. Let us print the values present in colors1. The values have been successfully printed which are present in colors1. Now let us check if colors1 is empty or not. The result is false, which proves that the colors1 is not empty. Now let us try to concatenate both the maps colors1 and color2. The following code will help us to concatenate both the maps, and the result is stored into the new map, which is colors. As you can see, the values have been stored into the new map, which is colors, and the color red is printed only for once, eliminating the duplication. As you can see, both color1 and color2 have been concatenated and saved into the new variable, which is colors, and the red color is been printed only once, eliminating the duplication. Let us try another example in maps. Now I have declared a new map called mapping, which has the key value pairs Virat as key and Kohli as value, and similarly Mahendra as key and Singh Dhoni as value. Let us map them using the keyword scala.collection.mutable.map. They have been successfully mapped now. Now let us find out the value of the key Virat. Similarly, let us try to map Mahendra. Similarly, let us try to remove the key value pair of Mahendra using the following code, which must remove both its key and value. As you can see, only Virat and Kohli have been existing in the map. Now let us try to add a new element into the map using the following code. Here I am adding Ajay Sharma into the map. As you can see, both Virat Kohli and Ajay Sharma are the two values present in the map now. Now we shall use get or else function in order to print the data which is present in the map. Now I am trying to print the key value pair of Virat. If that value is existing in the map, it must be printing the value. If not, it must be printing 0. As you can see, it has printed Kohli, which is existing in the map. So with this, we finish maps. Now let us move on to tuples. Scalar tuples combines a fixed number of items together so that they can be passed around as a whole. Unlike an array or list, a tuple can hold objects with different types, but they are also immutable. The following is an example of tuple holding an integer and a string. Here I am creating a new tuple by name A, and I am storing values 1 and 4, which are integer type, and values Ajay and Devgan, which are string type. The tuple has been successfully declared. Now let us try to access the elements in a tuple. We can use the following code to access the elements present in a tuple. Let me try to access the first element in a tuple, which is 1. Remember, the memory location in tuples starts from 1, not from 0. So the first element in the tuple, which is 1, is successfully printed. Now let me access the element Ajay, for which I need to give the memory location as 3. So the Ajay string has been successfully printed now. So with this, we finished tuples. Let's now move into the next topic, which is control statements. The control statements supported in Scala are if else, for each, while, and do while. Let us discuss about each and every one of them in practical. Let us try out if else first. Here I am declaring a new variable x with value 5. Let us execute if else statement in order to understand how does it work. Here I am applying if else control statement, and I am assigning the resultant value to the new variable, which is s. Here my control statement is if the x value is greater than 0 and x is less than true, it must provide a result as true, which is 1. If it is not true, it must provide the value as 0. Let us see. So it is true because x is greater than 0 and less than 6. So we have obtained a true result as 1. Here, let us try out another example where I'll provide the condition as x must be greater than 0 and it must be less than 6. If it is true, it must provide as positive. If not, it must provide as false, which is 0. So the result is true and it has provided the result as positive. Now let us understand while loop in Scala. Here I am declaring a new variable args, which will be storing a string value Edureka, and then I'll be counting the value of the string. Later I'll be applying a while loop based on the count of the string, and I'll be printing the elements in args until the condition is true. As you can see, Edureka has been printed as long as the control statement was true. Now let us execute for each control statement. Here I have declared a new variable args, which will be storing a string value hello, and I'll be using for each control statement in order to print the data which is present in args, printing each and every element in the args in a new line. As you can see, the data has been successfully printed. Now let us try out a simple for loop. Here I'm applying a simple for loop where the count starts from 1 to 5, and I'll be printing the elements from 1 to 5 in a new line, which is by the function println. Now let us try out to understand an advanced for loop. Here I'm declaring a for loop along with a condition inside the for loop, which happens to be I is equals to j. The results will only be printed when the value of I is equals to j. This kind of condition avoids the unnecessary control flow into the for loop. Now let us discuss about yield. Yield is similar to lazy evaluation. Here the control flow is executed but not displayed. The results are saved into I but not be displayed. The results are saved in form of a vector. Here let us consider another example of field where the elements will be multiplied by 2 and will be saved in I in form of a vector. As you can see, the elements have been multiplied by 2 and the results are saved in I in form of a vector. Now we shall understand do-while loop. The only difference between while loop and the do-while loop is the control statement. In while loop, the control statement will be at the beginning. In do-while loop, the same control statement will be at the end of the loop. In do-while loop, the data will be printed at least for once because the print command will be encountered before the condition is encountered by the control flow. Now let us work out with an example using the control flow statements. I'm using an example to find out the area of a circle using the following code. Here, let me declare the radius of the circle. We shall declare the radius of a circle as 15. Now we must get the result. The result is 706.5. So with this, we've finished the control statements. Spark is one of the top mandatory skills required by each and every big data developer. It is used in multiple applications which need real-time processing, such as Google's recommendation engine, credit card fraud detection, and many more. To understand this in depth, we shall consider Amazon's recommendation engine. Assume that you are searching for a mobile phone in Amazon and you have certain specifications of your choice. Then, the Amazon search engine understands your requirements and provides you the products which match the specifications of your choice. All this is made possible because of the most powerful tool existing in big data environment, which is none other than Apache Spark. And resilient distributed dataset is considered to be the heart of Apache Spark. So with this, let's begin our first question. Why do we need RDDs? Well, the current world is expanding the technology and artificial intelligence is the face for this evolution. The machine learning algorithms and the data needed to train these computers are huge. The logic behind all these algorithms are very complicated and mostly run in a distributed and iterative computation method. The machine learning algorithms could not use the older MapReduce programs because the traditional MapReduce programs needed a stable state HDFS. And we know that HDFS generates redundancy during intermediate computations, which resulted in a major latency in data processing. And in HDFS, gathering data from multiple processing units at a single instance was time consuming. Along with this, the major issue was the HDFS did not have random read and write ability. So using these older MapReduce programs for machine learning problems would be impractical. Then the Spark was introduced. Compared to MapReduce, Spark is an advanced big data processing framework. Resilient distributed dataset, which is a fundamental and most crucial data structure of Spark, was the one which made it all possible. RDDs are effortless to create, and the mind-blowing property which solved the problem was its in-memory data processing capability. RDD is not a distributed file system. Instead, it is a distributed collection of memory where the data needed is always stored and kept available in RAM. And because of this property, the elevation it gave to the memory accessing speed was unbelievable. The RDDs are fault tolerant, and this property brought it a dignity of a whole new level. So, our next question would be, what are RDDs? The resilient distributed datasets, or the RDDs, are the primary underlying data structures of Spark. They are highly fault tolerant and they store data amongst multiple computers in a network. The data is written into multiple executable nodes so that in case of a calamity, if any executing node fails, then within a fraction of a second, it gets backup from the next executable node with the same processing speeds of the current node. The fault tolerant property enables them to roll back their data to the original state by applying simple transformations onto the lost part in the lineage. RDDs do not need anything called hard disk or any other secondary storage. All that they need is the main memory, which is RAM. Now that we have understood the need for RDDs and what exactly an RDD is, so let us see the different sources from which the data can be ingested into an RDD. The data can be loaded from any source like HDFS, HBase, Hive, SQL, you name it, they got it. Hence, the collected data is dropped into an RDD. And guess what? The RDDs are free-spirited. They can process any type of data. They won't care if the data is structured, unstructured, or semi-structured. Now, let me walk you through the features of RDDs which give it an edge over the other alternatives. In-memory computation. The idea of in-memory computation brought the groundbreaking progress in cluster computing. It increased the processing speed when compared with the HDFS. Moving on to lazy evaluations, the phrase lazy explains it all. Spark logs all the transformations you apply onto it and will not throw any output onto the display until an action is provoked. Next is fault tolerance. RDDs are absolutely fault tolerant. Any lost partition of an RDD can be rolled back by applying simple transformations onto the lost part in the lineage. Speaking about immutability, the data once dropped into an RDD is immutable because the access provided by RDD is just read-only. The only way to access or modify it is by applying a transformation onto an RDD which is prior to the present one. Discussing about partitioning, the important reason for Spark's parallel processing is its partitioning. By default, Spark determines the number of parts into which your data is divided, but you can override this and decide the number of blocks you want to split your data. Let's see what persistence is. Spark's RDDs are totally reusable. The users can apply certain number of transformations onto an RDD and preserve the final RDD for future use. This avoids all the hectic process of applying all the transformations from scratch. And now, last but not the least, coarse-grained operations. The operations performed on RDDs using transformations like map, filter, flat map, etc. change the RDDs and update them. Hence, every operation applied onto an RDD is coarse-grained. These were the features of RDDs, and moving on to the next stage, we shall understand the creation of RDDs. RDDs can be created using three methods. The first method is using parallelized collections. Next method is by using external storage like HDFS, HBase, Hive, and many more. The third one is using an existing RDD which is prior to the present one. Now, let us see, understand, and create an RDD through each method. Now, Spark can be run on virtual machines like Spark VM, or you can install a Linux operating system like Ubuntu and run it standalone. But we here at Edureka use the best-in-class Cloud Lab, which comprises of all the frameworks you need at a single-stop cloud framework. No need of any hectic procedures of downloading any file or setting up environment variables and looking for a hardware specification, etc. All you need is a login ID and password to the all-in-one ready-to-use Cloud Lab where you can run and save all your programs. Let us fire up our Spark shell using the command spark2-shell. Now our Spark shell has been fired up. Let's create our new RDD. So here we are creating our new RDD with the first method, which is using the parallelized collections. Here we are creating a new RDD by the name parallelized collections RDD. We are starting a Spark context and we are parallelizing an array into the RDD, which consists of the data of the days of a week, which is Monday, Tuesday, Wednesday, Thursday, Friday, and Saturday. Now let's create this. Our new RDD, parallelized collections RDD, is successfully created. Now let's display the data which is present in our RDD. So this was the data which is present in our RDD. Now let's create a new RDD using our second method. The second method of creating an RDD was using an external storage such as HDFS, Hive, SQL, and many more. Here I'm creating a new RDD by the name Spark file, where I'll be loading a text document into the RDD from an external storage which is HDFS, and this is the location where my text file is located. So the new RDD Spark file is successfully created. Now let's display the data which is present in our Spark file RDD. So the data which was present in our Spark file RDD is a collection of alphabets starting from A to Z. Now let's create a new RDD using the third method, which is using an existing RDD which is prior to the present one. In the third method, I'm creating a new RDD by the name words, and I'm creating a Spark context and parallelizing a statement into the RDD words, which is Spark is a very powerful language. So this is a collection of words which I have passed into the new RDD words. Now let us apply a transformation onto the RDD and create a new RDD through that. So here I'm applying map transformation onto the previous RDD, that is words, and I'm storing the data into the new RDD which is word pairs. So here we are applying map transformation in order to display the first letter of each and every word which is stored in the RDD words. Now let's continue. The transformation has been applied successfully. Now let's display the contents which are present in our new RDD, which is word pair. So as explained, we have displayed the starting letter of each and every word, as S is the starting letter of Spark, I is the starting letter of ease, and so on. L is the starting letter of language. Now we have understood the creation of RDDs. Let us move on to the next stage, where we'll understand the operations that are performed on RDDs. Transformations and actions are the two major operations that are performed on RDDs. Let us understand what are transformations. We apply transformations in order to access, filter, and modify the data which is present in an RDD. Now, transformations are further divided into two types, narrow transformations and wide transformations. Now, let us understand what are narrow transformations. We apply narrow transformations onto a single partition of parent RDD because the data required to process the RDD is available on a single partition of parent RDD. The examples for narrow transformation are map, filter, flat map, partition, and map partitions. Let us move on to the next type of transformations, which is wide transformations. We apply wide transformations onto the multiple partitions of parent RDD because the data required to process an RDD is available on multiple partitions of the parent RDD. The examples for wide transformations are reduce by and union. Now, let us move on to the next part, which is actions. Actions, on the other hand, are considered to be the next part of operations which are used to display the final result. The examples for actions are collect, count, take, and first. Till now, we have discussed about the theory part on RDD. Let us start executing the operations that are performed on RDDs. In our practical part, we'll be dealing with an example of IPL matches data. So here, I have a CSV file which has the IPL match records, and this CSV file is stored in my HDFS, and I'm loading my matches.csv file into the new RDD, which is CK file, as a text file. So the matches.csv file has been successfully loaded as a text file into the new RDD, which is CK file. Now let us display the data which is present in our CK file using an action command. So collect is the action command which I'm using in order to display the data which is present in my CK file RDD. So here we have in total 636 rows of data which consist of IPL match records from the year 2008 to 2017. Now let us see the schema of our CSV file. I'm using the action command first in order to display the schema of our matches.csv file. So this command will display the starting line of the CSV file we have. So the schema of our CSV file is the ID of the match, season, city where the IPL match was conducted, date of the match, team 1, team 2, and so on. Now let's perform the further operations on our CSV file. Now moving on to the further operations, I am about to split the second column of my CSV file, which consists the information regarding the states which conducted the IPL matches. So I'm using this operation in order to display the states where the matches were conducted. So the transformation has been successfully applied and the data has been stored into the new RDD, which is states. Now let's display the data which is stored in our states RDD using the collection action command. So these were the states where the matches were being conducted. Now let's find out the city which conducted the maximum number of IPL matches. Here I'm creating a new RDD again, which is states count, and I'm using map transformation and I'm counting each and every city and the number of matches conducted in that particular city. The transformation is successfully applied and the data has been stored into the scount RDD. Now let us create a new RDD by name stateCountM and apply reduce by key transformation and map transformation together, and consider tuple 1 as the city name and tuple 2 as the number of matches which were considered in that particular city, and apply sort by key transformation to find out the city which conducted maximum number of IPL matches. The transformations are successfully applied and the data is being stored into the stateCountM RDD. Now let's display the data which is present in stateCountM RDD. Here I'm using take action command in order to take the top 10 results which are stored in stateCountM RDD. So according to the results, we have Mumbai, which conducted the maximum number of IPL matches, which is 85, since the year 2008 to the year 2017. Now let us create a new RDD by name FIL RDD and use flat map in order to filter out the matched data which were conducted in the city Hyderabad and store the same data into the file RDD. So the transformation has been successfully applied. Now let us display the data which is present in our file RDD, which consists of the matches which were conducted excluding the city Hyderabad. So this is the data which is present in our file RDD, which excludes the matches which were played in the city Hyderabad. Now let us create another RDD by name FIL and store the data of the matches which were conducted in the year 2017. We shall use filter transformation for this operation. The transformation has been applied successfully and the data has been stored into the FIL RDD. Now let us display the data which is present there. We shall use collect action command. And now we have the data of all the matches which were played especially in the year 2017. Similarly, we can find out the matches which were played in the year 2016 and we can save the same data into the new RDD which is FIL2. Similarly, we can find out the data of the matches which were conducted in the year 2016 and we can store the same data into our new RDD which is FIL2. I have used filter transformation in order to filter out the data of the matches which were conducted in the year 2016 and I have saved the data into the new RDD which is FIL2. Now let us understand the union transformation. We shall apply the union transformation onto the FIL RDD and FIL2 RDD in order to combine both the data present in both the RDDs. Here I am creating a new RDD by the name union RDD and I'm applying union transformation on the two RDDs that we created before. The first one is FIL RDD, which consists of the data of the matches played in the year 2017, and the second one is FIL2, which consists the data of the matches which were played in the year 2016. Here I'll be clubbing both the RDDs together and I'll be saving the data into the new RDD which is union RDD. Now let us display the data which is present in our new RDD which is union RDD. I'm using collect action command in order to display the data. So here we have the data of the matches which were played in the years 2016 and 2017. And now let's continue with our operations and find out the player with maximum number of man of the match awards. For this operation, I'm applying map transformation and splitting out the column number 13, which consists of the data of the players who won the man of the match awards for that particular match. So the transformation has been successfully applied and the column number 13 has been successfully split and the data has been stored into the man of the match RDD. Now we are creating a new RDD by the name man of the match count. We are applying map transformations onto our previous RDD and we are counting the number of awards won by each and every particular player. Now we shall create a new RDD by the name man of the match and we are applying reduce by key transformation onto the previous RDD which is man of the match count, and again we are applying map transformation and considering tuple 1 as the name of the player and tuple 2 as the number of matches he played and won the man of the match awards. Let us use take action command in order to print the data which is stored in our new RDD which is man of the match. So according to the result, we have AB de Villiers who won the maximum number of man of the matches which is 15. So these were the few operations that were performed on RDDs. Now let us move on to our Pokemon use case so that we can understand RDDs in a much better way. So the steps to be performed in Pokemon use case are loading the Pokemon data.csv file from an external storage into an RDD, removing the schema from the Pokemon data.csv file, and finding out the total number of water type Pokemons, finding the total number of fire type Pokemons. I know it's getting interesting, so let me explain you each and every step practically. So here I'm creating a new RDD by name Pokemon Data RDD1 and I'm loading my CSV file from an external storage that is my HDFS as a text file. So the Pokemon data.csv file has been successfully loaded into our new RDD. So let us display the data which is present in our Pokemon Data RDD1. I'm using collect action command for this. So here we have 721 rows of data of all the types of Pokemons we have. So now let us display the schema of the data we have. I have used the action command first in order to display the first line of our CSV file, which happens to be the schema of our CSV file. So we have index of the Pokemon, name of the Pokemon, its type, total points, HP, attack points, defense points, special attack, special defense, speed, generation, and we can also find if a particular Pokemon is legendary or not. Here I'm creating a new RDD which is no header, and I'm using filter operation in order to remove the schema of our Pokemon data.csv file. The schema of Pokemon data.csv file is been removed because the Spark considers the schema as a data to be processed. So for this reason we remove the schema. Now let's display the data which is present in our no header RDD. I'm using action command collect in order to display the data which is present in no header RDD. So this is the data which is stored in a no header RDD without the schema. So now let us find out the number of partitions into which our no header RDD is been split into. So I'm using partitions transformation in order to find out the number of partitions the data was split into. According to the result, the no header RDD has been split into 2 partitions. I'm here creating a new RDD by name water RDD, and I'm using filter transformation in order to find out water type Pokemons in our Pokemon data.csv file. I'm using action command collect in order to print the data which is present in water RDD. So these are the total number of water type Pokemons that we have in our Pokemon data.csv. Similarly, let's find out the fire type Pokemons. I'm creating a new RDD by the name Fire RDD and applying filter operation in order to find out the fire type Pokemons present in our CSV file. I'm using collect action command in order to print the data which is present in Fire RDD. So these are the fire type Pokemons which are present in our Pokemon data.csv file. Now let us count the total number of water type Pokemons which are present in our Pokemon data.csv file. I'm using count action for this. And we have 112 water type Pokemons present in our Pokemon data.csv file. Similarly, let's find out the total number of fire type Pokemons we have. I'm using count action command for the same. So we have a total 52 number of fire type Pokemons in our Pokemon data.csv file. Let's continue with our further operations where we'll find out a highest defense strength of a Pokemon. I'm creating a new RDD by the name defense list, and I'm applying map transformation and splitting out the column number 6 in order to extract the defense points of all the Pokemons present in our Pokemon data.csv file. So the data has been stored successfully into our new RDD, which is defense list. Now I'm using max action command in order to print out the maximum defense strength out of all the Pokemons. So we have 230 points as the maximum defense strength amongst all the Pokemons. So in our further operations, let's find out the Pokemons which come under the category of having highest defense strength, which is 230 points. In order to find out the name of the Pokemon with highest defense strength, I am creating a new RDD with the name defense with Pokemon name, and I'm applying map transformation onto the previous RDD, which is no header, and I'm splitting out column number 6, which happens to be the defense strength, in order to extract the data from that particular row, which has the defense strength as 230 points. Now I'm creating a new RDD again with the name maximum defense Pokemon, and I'm applying group by K transformation in order to display the Pokemon which have the maximum defense points, that is 230 points. So according to the result, we have Steelix, Steelix Mega, Shuckle, Aggregon, and Aggregon Mega as the Pokemons with highest defense strength, which is 230 points. Now we shall find out the Pokemon which is having least defense strength. So before we find out the Pokemon with least defense strength, let us find out the least defense points which are present in the defense list. So in order to find out the Pokemon with least defense strength, I have created a new RDD by name minimum defense Pokemon, and I have applied distinct and sort by transformations onto the defense list RDD in order to extract the least defense points present in the defense list. And I have used take action command in order to display the data which is present in minimum defense Pokemon RDD. So according to the results, we have 5 points as the least defense strength of a particular Pokemon. Now let us find out the name of the Pokemon which comes under the category of having 5 points as defense strength. Now let us create a new RDD which is defense Pokemon name 2 and apply map transformation and split the column number 6 and store the data into our new RDD which is defense with Pokemon name 2. The transformation has been successfully applied and the data is now stored into the new RDD which is defense with Pokemon name 2. The data has been successfully loaded now. Let us apply the further operations. Here I am creating another RDD with name minimum defense Pokemon, and I'm applying group by key transformation in order to extract the data from the row which has the defense points as 5.0. The data has been successfully loaded now, and let us display the data which is present in minimum defense Pokemon RDD. Now according to the results, we have two number of Pokemons which come under the category of having 5 points as their defense strength. The Pokemons Chassiny and Happiny are the two Pokemons which are having the least defense strength. What is a data frame? In simple terms, a data frame can be considered as a distributed collection of data. The data is organized under named columns which provide us the operations to filter, group, process, and aggregate the available data. Data frames can also be used with Spark SQL, and we can construct data frames from structured data files, RDDs, or from an external storage like HDFS, Hive, Cassandra, HBase, and many more. With this, we shall look into a more simplified example which will give us a basic description of a data frame. So we shall deal with an employee database where we have entities and their data types. So the name of the employee is our first entity and its respective data type is string data type. Similarly, employee ID has data type of string, employee phone number which is integer data type, and employee address happens to be string data type, and finally the employee salary is float data type. All this data is stored into an external storage which may be HDFS, Hive, or Cassandra using the DataFrame API with their respective schema which consists of the name of the entity along with its data type. Now that we have understood what exactly a data frame is, let us quickly move on to our next stage where we shall understand the requirement for a data frame. It provides us multiple programming language supportability. It has the capacity to work with multiple data sources. It can process both structured and unstructured data. And finally, it is well versed with slicing and dicing the data. So the first one is the supportability for multiple programming languages. The IT industries required a powerful and an integrated data structure which could support multiple programming languages and at the same time without the requirement of additional API. DataFrame was their one-stop solution which supported multiple languages along with a single API. The most popular languages that a data frame could support are R, Python, Scala, Java, and many more. The next requirement was to support the multiple data sources. We all know that in a real-time approach to data processing, we'll never end up at a single data source. Data frame is one such data structure which has the capability to support and process data from a variety of data sources. Hadoop, Cassandra, JSON files, HBase, CSV files are the examples to name a few. The next requirement was to process structured and unstructured data. The big data environment was designed to store a huge amount of data regardless of which type exactly it is. Now, Spark's data frame is designed in such a way that it can store a huge collection of both structured and unstructured data in a tabular format along with its schema. The next requirement was slicing and dicing data. Now, the humongous amount of data stored in Spark's data frame can be sliced and diced using the operations like filter, select, group by, order by, and many more. These operations are applied upon the data which are stored in form of rows and columns in a data frame. These were the few crucial requirements which led to the invention of data frames. Now, let us get into the important features of data frames which bring it an edge over the other alternatives. Immutability, lazy evaluation, fault tolerance, and distributed memory storage. Let us discuss about each and every feature in detail. So the first one is immutability. Similar to the resilient distributed datasets, the data frames in Spark are also immutable. The term immutable depicts that the data once stored into a data frame will not be altered. The only way to alter the data present in a data frame would be by applying simple transformation operations onto them. So the next feature is lazy evaluation. Lazy evaluation is the key to the remarkable performance offered by Spark. Similar to the RDDs, data frames in Spark will not throw any output onto the screen until and unless an action command is encountered. The next feature is fault tolerance. There is no way that the Spark's data frames can lose their data. They follow the principle of being fault tolerant to the unexpected calamities which tend to destroy the available data. The next feature is distributed storage. Spark's data frame distributes the data amongst multiple locations so that in case of a node failure, the next available node can take its place to continue the data processing. The next stage will be about the multiple data source that the Spark data frame can support. The Spark API can integrate itself with multiple programming languages such as Scala, Java, Python, R, MySQL, and many more, making itself capable to handle a variety of data sources such as Hadoop, Hive, HBase, Cassandra, JSON files, CSV files, MySQL, and many more. So this was the theory part, and now let us move into the practical part, where the creation of a data frame happens to be our first step. So before we begin the practical part, let us load the libraries which were required in order to process the data in DataFrames. So these were the few libraries which we required before we process the data using our DataFrames. Now that we have loaded all the libraries which were required to process the data using the DataFrames, let us begin with the creation of our data frame. So we shall create a new data frame with the name employee and load the data of the employees present in an organization. The details of the employees will consist the first name, the last name, and their mail ID along with their salary. So the first data frame has been successfully created. Now let us design the schema for this data frame. So the schema for this data frame has been described as shown. The first name is of string data type, and similarly the last name is of string data type along with the mail address, and finally the salary is integer data type, or you can give float data type also. So the schema has been successfully delivered. Now let us create the data frame using create data frame function. Here I'm creating a new data frame by starting a Spark context and using the create data frame method and loading the data from employee and employee schema. The data frame is successfully created now. Let's print the data which is existing in the data frame empdf. I'm using show method here. So the data which is present in empdf has been successfully printed. Now let us move on to the next step. So the next step for our today's discussion is working with an example related to the FIFA dataset. So the first step in our FIFA example would be loading the schema for the CSV file we are working with. So the schema has been successfully loaded now. Now let us load the CSV file from our external storage, which is HDFS, into our data frame, which is FIFA DF. The CSV file has been successfully loaded into our new data frame, which is FIFA DF. Now let us print the schema of our data frame using the print schema command. So the schema has been successfully displayed here, and we have the following credentials of each and every player in our CSV file. Now let's move on to our further operations on our data frame. We shall count the total number of records of the players we have in our CSV file using count command. So we have a total of 18,207 players in our CSV file. Now let us find out the details of the columns on which we are working with. So these were the columns which we are working with, which consists the ID of the player, name, age, nationality, potential, and many more. Now let us use the column value, which has the value of each and every player for a particular team, and let us use describe command in order to see the highest value and the least value provided to a player. So we have a count of a total number of 18,207 players, and the minimum worth given to a player is 0 and the maximum is given as 9 million pounds. Now let us use the select command in order to extract the column name and the nationality to find out the name of each and every player along with his nationality. So here we can display the top 20 rows of each and every player which we have in our CSV file along with his nationality. Similarly, let us find out the players playing for a particular club. So here we have the top 20 players playing for their respective clubs along with their names. For example, Messi playing for Barcelona and Ronaldo for Juventus, and etc. Now let's move on to the next stages. Now let us find out the players who are found to be most active in a particular national team or a particular club with age less than 30 years. We shall use filter transformation to apply this operation. So here we have the details of the players whose age is less than 30 years and their club and nationality along with their jersey numbers. So with this, we have finished our FIFA example. Now to understand the data frames in a much better way, let us move on into our use case, which is about the most hot topic, the Game of Thrones. Similar to our previous example, let us design the schema of our CSV file first. So this is the schema for our CSV file, which consists the data about the Game of Thrones. So this is the schema for our first CSV file. Now let us create the schema for our next CSV file. I have named the schema for our next CSV file as schema2, and I've defined the data types for each and every entity. The schema has been successfully designed for the second CSV file also. Now let us load our CSV files from our external storage, which is our HDFS. So the location of the first CSV file, characterdepths.csv, is our HDFS, which is defined as above. And the schema has been provided as schema, and the header true option is also been provided. We are using Spark read function for this, and we are loading this data into our new data frame, which is Game of Thrones data frame. Similarly, let's load the other CSV file, which is battles.csv, into another data frame, which is Game of Thrones battles data frame. The CSV file has been successfully loaded. Now let us continue with the further operations. Now let us print the schema of our Game of Thrones data frame using print schema command. So here we have the schema, which consists of the name, alliances, death rate, book of death, and many more. Similarly, let's print the schema of Game of Thrones battles data frame. So this is a schema for our new data frame, which is Game of Thrones battle data frame. Now let us continue with the further operations. Now let us display the data frame which we have created using the following command. The data frame has been successfully printed, and this is the data which we have in our data frame. Now let's continue with the further operations. We know that there are a multiple number of houses present in the story of Game of Thrones. Now let us find out each and every individual house present in the story. Let us use the following command in order to display each and every house present in the Game of Thrones story. So we have the following houses in the Game of Thrones story. Now let's continue with the further operations. The battles in the Game of Thrones were fought for ages. Let us classify the wars waged with their occurrence according to the years. We shall use select and filter transformation, and we shall access the columns of the details of the battle and the year in which they were fought. Let us first find out the battles which were fought in the year 298. The following code consists of filter transformation, which will provide the details for which we are looking. So according to the result, these were the battles which were fought in the year 298, and we have the details of the attacker kings and the defender kings, and the outcome of the attacker along with their commanders and the location where the war was fought. Now let us find out the wars waged in the year 299. So these were the details of the wars which were fought in the year 299, and similarly let us also find out the wars which were waged in the year 300. So these were the wars which were fought in the year 300. Now let's move on to the next operations in our use case. Now let us find out the tactics used in the wars waged, and also find out the total number of wars waged by using each type of those tactics. The following code must help us. Here we are using select and group by operations in order to find out each and every type of tactics used in the war. So they have used ambush, seize, raising, and pitch type of tactics in wars, and most of the times they have used pitch battle type of tactics in wars. Now let us continue with the further operations. The ambush type of battles are the deadliest. Now let us find out the kings who fought the battles using these kind of tactics, and also let us find out the outcome of the battles fought. Here the following code will help us extract the data which we need. Here we are using select and where commands, and we are selecting the columns year, attacker king, defender king, attacker outcome, battle type, attacker commander, defender commander. Now let us print the details. So these were the battles fought using the ambush tactics, and these were the attacker kings and the defender kings along with their respective commanders, and the wars waged in a particular year. Now let's move on to the next operation. Now let us focus on the houses and extract the deadliest house amongst the rest. The following code will help us to find out the deadliest house and the number of battles they waged. So here we have the details of each and every house and the battles they waged. According to the results, we have Stark and the Lannister houses to be the deadliest among the others. Now let's continue with the rest of the operations. Now let us find out the deadliest king among the others. We shall use the following command in order to find the deadliest king amongst the other kings who fought the major number of wars. So according to the results, we have Joffrey as the deadliest king who fought a total number of 14 battles. Now let us continue with the further operations. Now let us find out the houses which defended most number of wars waged against them. So the following code must help us find out the details. So according to the results, we have Lannister house to be defending the most number of wars waged against them. Now let us find out the defender king who defended most number of battles which were waged against him. So according to the result, Rob Stark is the king who defended most number of battles which waged against him. Now let's continue with the further operations. Since Lannister House is my personal favorite, let me find out the details of the characters in Lannister House. This code will describe their name and gender, 1 for male and 0 for female, along with their respective population. So let me find out the male characters in the Lannister house first. So here we have used select and where commands in order to find out the details of the characters present in Lannister house, and the data is been stored into df1 data frame. Let us print the data which is present in our df1 data frame using show command. So these are the details of the characters present in Lannister house, which are male. Now similarly, let us find out the female characters present in Lannister house. So these are the characters present in Lannister house who are females. So we have a total number of 69 male characters and 12 number of female characters in the Lannister house. Now let us continue with the next operations. At the end of the day, every episode of Game of Thrones had a noble character. Let us now find out all the noble characters amongst all the houses that we have in our Game of Thrones CSV file. The following code must help us find out the details. So the details of all the characters from all the houses who are considered to be noble have been saved into the new data frame, which is df3. Now let us print the details from the df3 data frame. So these are the top 20 members from all the houses who are considered to be noble along with their genders. Now let us count the total number of noble characters from the entire Game of Thrones stories. So there are a total of 430 number of noble characters existing in the whole Game of Thrones story. Nonetheless, we have also faced a few commoners whose role in the Game of Thrones is found to be exceptional. We shall now find out the details of all those commoners who were highly dedicated to their roles in each episode. The data of all the commoners is being successfully loaded into the new data frame, which is df4. Now let us print the data which is present in the df4 using the show command. So these are the top 20 characters identified as commoners amongst all the Game of Thrones stories. Now let us find out the count of total number of common characters. So there are a total of 487 common characters amongst all the stories of Game of Thrones. Let us continue with the further operations now. There were a few roles who were considered to be important and equally noble. Hence, they were carried out until the last book. So let us filter out those characters and find out the details of each one of them. The data of all the characters who are considered to be noble and carried out until the last book are being stored into the new data frame, which is df4. Now let us print the data which is existing in the data frame 4. So according to the results, we have two candidates who are considered to be the noble and their character is been carried out until the last book. Amongst all the battles, I found the battles of the last books to be generating more adrenaline in the readers. Let us find out the details of those battles using the following code. So the following code will help us to find out the wars which were fought in the last years of the Game of Thrones. So these are the details of the wars which were fought in the last years of the Game of Thrones, and the details of the kings and the details of their commanders and the location where the war was fought.
Why Spark SQL? Is it like why we are learning it? Why it is really important for us to know about this Spark SQL side? Is it like really hot in market? If yes, then why? We want all those answers from this. So if you're coming from Hadoop background, you must have heard a lot about Apache Hive. Now, what happens in Apache Hive? So like in Apache Hive, SQL developers can write their queries in a SQL way, and it will be getting converted to your MapReduce and giving you the output. Now, we all know that MapReduce is slower in nature. And since MapReduce is going to be slower in nature, then definitely your overall Hive query is going to be slower in nature. So that was one challenge. So if you have, let's say, less than 200 GB of data, or if you have a smaller set of data, this was actually a big challenge that in Hive, your performance was not that great. It also do not have any resuming capability. If you're stuck, you cannot start it. Also, Hive cannot even drop your encrypted databases. That was also one of the challenge when you deal with the security side. Now, what Spark SQL have done is, Spark SQL have solved almost all of the problem. So in the last sessions, we have already learned about the Spark way, right? How Spark is faster from MapReduce and all. We have already learned that in our previous few sessions. Now, so in this session, we are going to kind of take a leverage of all that. So definitely in this case, since Apache Spark is faster because of the in-memory computation. What is in-memory computation? We have already seen it. So in-memory computations is like whenever we are computing anything in memory directly. So because of in-memory computation capability, because Apache Spark was faster, so definitely your Spark SQL is also going to become fast. Now, so if I talk about the advantages of Spark SQL over Hive, definitely number one, it is going to be faster in comparison to your Hive. So a Hive query, which is let's say taking around 10 minutes, in Spark SQL, you can finish that same query in less than 1 minute. Don't you think it's an awesome capability of Spark SQL? Definitely yes, right? Now, second thing is if let's say you're writing something in Hive, now you can take an example of let's say a company who is let's say developing Hive queries from last 10 years. Now they were doing it, they were all happy that they were able to process big data, that they were worried about the performance, that Hive is not able to give them that level of processing speed what they are looking for. Now this was let's say a challenge for that particular company. Now there's a challenge, right? The challenge is they came to know now about Spark SQL. Fine. Let's say they came to know about it, but they came to know that we can execute everything in Spark SQL and it is going to be faster as well. Fine. But don't you think that if these companies working from let's say past 10 years in Hive, they must have already written a lot of code in Hive? Now, if you ask them to migrate to Spark SQL, will it be an easy task? No, right? Definitely it is not going to be an easy task. Why? Because Hive syntax and Spark SQL syntax, though they both tackle the SQL way of writing the things, but at the same time, it is always it carries a big difference. So there will be a good difference whenever we talk about the syntax between them. So it will take a very good amount of time for that company to change all of the query mode to the Spark SQL way. Now Spark SQL came up with a smart solution. What they said is, even if you're writing the query with Hive, you can execute that Hive query directly through Spark SQL. Don't you think it's a kind of very important and an awesome facility, right? Because even now, if you're a good Hive developer, you need not worry about that how you will be now migrating to Spark SQL. You can still keep on writing to Hive query and your query will automatically be getting converted to Spark SQL way. Similarly, in Apache Spark, as we have learned in the past sessions, especially through Spark streaming, that Spark streaming is going to make you real-time processing, right? You can also perform your real-time processing using Apache Spark. Now, this sort of facility is you can take leverage even in your Spark SQL. So let's say you can do a real-time processing and at the same time, you can also perform your SQL query. Now with Hive, that was a problem. You cannot do that because when we talk about Hive, now in Hive, it's all about, Hadoop is all about batch processing. Batch processing where you keep historical data and then later you process it, right? So it definitely Hive also follow the same approach. In this case also, Hive is going to just only follow the batch processing mode. But when it comes to Apache Spark, it will also be taking care of the real-time processing. So how all these things happens? So your Spark SQL always uses your metastore services of your Hive to query the data stored and managed by Hive. So when you were learning about Hive, so we have learned at that time that in Hive, everything what we do is always stored in the metastore. So that metastore was the crucial point, right? Because using that metastore only, you were able to do everything up. So like when you're doing, let's say your any sort of query, or when you're creating a table, everything was getting stored in that same metastore. Now what happens? Spark SQL also use the same metastore. Now whatever metastore you have created with respect to Hive, same metastore you can also use it for your Spark SQL. And that is something which is really awesome about this Spark SQL, that you need not create a new metastore, you need not worry about a new storage space and all. Everything what you have done with respect to your Hive, same metastore you can use it. Now you can ask me then how it is faster if they're using same metastore. Remember the processing part. Why Hive was slower? Because of its processing way. Because it is converting everything to the MapReduce and thus it was making the processing very, very slow. But here in this case, since the processing is going to be in-memory computation, so in Spark SQL case, it is always going to be the faster. Now, definitely, it just because of the meta store side, we are only able to fetch the data and all, but at the same time, for any other thing of the processing related stuff, it is always going to be at the, when we talk about the processing stage, it is going to be in memory, thus it's going to be faster. So let's talk about some success stories of Spark SQL. Let's see some use cases. Twitter sentiment analysis. If you go through our, if you remember our Spark streaming session, we have done a Twitter sentiment analysis, right? So there you have seen that we have first initially got the data from Twitter, and that too we have got it with the help of Spark streaming. And later what we did, later we just analyzed everything with the help of Spark SQL. So you can see an advantage of Spark SQL. So in Twitter sentiment analysis, where let's say you want to find out about the Donald Trump, right? You are fetching the data, every tweet related to the Donald Trump, and then kind of doing analysis and checking that whether it's a positive tweet, negative tweet, neutral tweet, very negative tweet, very positive tweet. Okay, so we have already seen the same example there in that particular session. So in this session, as you are noticing what we are doing, we just want to kind of show that once you are streaming the data in the real time, you can also do a processing using Spark SQL. Thus, you are doing all the processing at the real time. Similarly, in the stock market analysis, you can use Spark SQL. A lot of queries you can adopt there. In the banking fraud case transactions and all, you can use that. So let's say your credit card currently is getting swiped in India, and in next 10 minutes, if your credit card is getting swiped in, let's say, in US, definitely that is not possible, right? So let's say you are doing all that processing real time, you're detecting everything with respect to Spark streaming. Then you are, let's say, applying your Spark SQL to verify that whether it's a user trend or not, right? So all those things you want to match up with Spark SQL, so you can do that. Similarly, in the medical domain, you can use that. Let's talk about some Spark SQL features. So there will be some features related to it. Now, you can use what happens when the SQL got combined with the Spark. We started calling it as Spark SQL. Now, when definitely we are talking about SQL, we are talking about either a structured data or a semi-structured data. Now, SQL queries cannot deal with the unstructured data. So that is definitely one of the things you need to keep in mind. Now, your Spark SQL also support various data formats. You can get the data from Parquet. You must have heard about Parquet, that it is a columnar based storage, and it is kind of very much a compressed format of the data what you have, but it's not human readable. Similarly, you must have heard about JSON, Avro, where we keep the value as a key value pair, Hive, Cassandra, right? These are NoSQL DBs. So you can get all the data from these sources. Now you can also convert your SQL queries to your RDD way. So you will be able to perform all the transformation steps. So that is one thing you can do. Now, if we talk about performance and scalability, definitely on this red color graph, if you notice, this is related to your Hadoop. You can notice that red color graph is much more in comparison to blue color, and blue color denotes my performance with respect to Spark SQL. So you can notice that Spark SQL is performing much better in comparison to your Hadoop. So we are on this y-axis, we are taking the running time. On the x-axis, we were considering the number of iterations. When we talk about Spark SQL features, now a few more features we have. For example, you can create a connection with simple your JDBC driver or ODBC driver, right? These are simple drivers being present. Now you can create your connection with your Spark SQL using all these drivers. You can also create a user-defined function. Means, let's say if any function is not available to you, in that case, you can create your own function. So let's say if a function is available, use that. If it is not available, you can create a UDF, means user-defined function, and you can directly execute that user-defined function and get your desired result. So this is one example where we have shown that you can convert, let's say if you don't have an uppercase API present in Spark SQL, how you can create a simple UDF for it and can execute it. So if you notice here what we are doing, let's say this is my data. So if you notice in this case, this is data set is my data part, right? So this is I'm generating as a sequence. I'm creating it as a data frame. See this 2DF part here. Now after that, we are creating a upper UDF here, and notice we are converting any value which is coming to my uppercase, right? We are using this to uppercase API to convert it. We are importing this function, and then what we did. Now, when we came here, we are telling that, okay, this is my UDF. So UDF is upper. Why? Because we have created here also as upper. So we are telling that this is my UDF in the first step. And then when we are using it, let's say with our data sets, what we are doing, so data sets we are passing here that, okay, whatever we are doing, convert it to my upper UDF, right? So convert it to my uppercase. So see, we are telling you we have created our upper UDF. That is what we are passing inside this text value. So now it is just getting converted and giving you all the output in your uppercase way. So you can notice that this is your last value and this is your uppercase value, right? So this got converted to my uppercase in this particular way. Now, if you notice here also, same step. So we can register all of our UDF. This is what being shown here. So now this is how you can do that, spark.udf.register. So using this API, you can just register your data frames. Now, similarly, if you want to get the output after that, you can get it using this following way. So you can use the show API to get the output for this. Spark SQL architecture, let's see that. So what is Spark SQL architecture? Now Spark SQL architecture, if we talk about, so what happens, you are, let's say, getting the data with using your various formats, right? So let's say you can get it from your CSV, you can get it from your JSON format, you can also get it from your JDBC format. Now there will be a data source API. So using data source API, you can fetch the data. After fetching the data, you will be converting to a data frame way. So what is data frame? So in the last one, we have learned that when we were creating everything is RDD, what we were doing. So let's say this was my cluster, right? So let's say this is machine, this is another machine, this is another machine, right? So let's say these are all my clusters. So what we were doing in this case, now when we were creating all these things as our cluster, what was happening here? We were passing all of our values here, right? So let's say we were keeping all the data, let's say block B1 was there. So we were passing all the values and were creating it in the form of, in the memory, and we were calling that as RDD. Now, when we were working in SQL, we have to store the data, which is a tabular data, right? So let's say there is a table, which is, let's say, having column details, let's say name, age, let's say here I have some value, 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 right? So let's say I have some value of this table format. Now, if I have to keep this data into my cluster, what you need to do, so you will be keeping first of all into the memory. So you will be having, let's say, name, age, this column details first of all here. And after that, you will be having some details of this data set. So let's say this much data you have. Some part, the similar kind of table with some other values will be here also. But here also you are going to have column details. You will be having name, age, some more data here. Now, if you notice, this is sounding similar to RDD, but this is not exactly like RDD, right? Because here we are not only keeping just the data, but we are also storing something like a columnar storage, right? We are also keeping the column in all our data nodes, or we can call it as a worker node, right? So we are also keeping the column details along with the row details. So this thing is called as data frames. Okay, so that is called your data frame. So that is what we are going to do. So we are going to convert it to the data frame API. Then using the data frame DSLs or by using Spark SQL or SQL, you will be processing the results and giving the output. We will learn about all these things in detail. So let's see the Spark SQL libraries. Now there are multiple APIs available to us. Like we have data source API, we have data frame API, we have interpreter and optimizer and SQL service. We will explore all this in detail now. So let's talk about data source API. If we talk about data source API, what happens here? In data source API, it is used to read and store the structured and unstructured data into your Spark SQL. So as you can notice, in Spark SQL, we can fetch the data using multiple sources, right? You can get it from Hive, Pick, Cassandra, CSV, Apache Base, DBase, Oracle DB. So many formats are available, right? So this API is going to help you to get all the data, to read all the data, store it wherever you want to use it. Now, after that, your data frame API is going to help you to convert that into a named column and row. Remember, I just explained you that how you store the data in that, because here you're not keeping it like a RDD. You're also keeping the named column as well as row details. That is the difference coming up here. So that is what it is converting in this case. So you are using data frame API to convert it into your named column and rows, right? So that is what you will be doing. So it also follows the same properties like your RDDs. Like your RDDs were lazily evaluated and all, same properties will also follow up here. Okay. Now, interpreter and optimizer. In interpreter and optimizer step, what we are going to do. So let's say if we have this DataFrame API, so we are going to first create this named column. Then after that, we will be now creating an RDD. We will be applying our transformation step. We will be doing our action step, right, to output the value. So all those things where it happens, it is happening in the interpreter and optimizer step. So this is all happening in the interpreter and optimizer step. So this is what all the features you have. Now, let's talk about SQL service. Now in SQL service, what happens? It is going to again help you. So it is just doing all the transformation action in the last step. After that, using Spark SQL service, you will be getting your Spark SQL outputs. So now in this case, whatever processing you have done, right, in terms of transformations and all of that. So you can say that your Spark SQL service is an entry point for working along the structured data in your Apache Spark. Okay, so it is going to kind of help you to fetch the results from your optimized data or maybe whatever you have interpreted before. So that is what it's doing. So this kind of completes this whole diagram. Now let's see that how we can perform our queries using Spark SQL. Now, if we talk about Spark SQL queries, so first of all, we can go to Spark shell itself and can execute everything. You can also execute your program using Spark, your Eclipse also directly. From there also you can do that. So if you are, let's say, log in with your Spark shell session, so what you can do, so let's say you need to import this, because in 2.x you must have heard that there is something called a Spark session which came up. So that is what we are doing. So in our last sessions, we have already learned about all these things up. Now Spark session is something what we are importing. After that, we are creating a session Spark using a builder function. Look at this. So this builder API, we are using this builder API, then we are using the app name, we are providing our configuration, and then we are telling that we are going to create our values here, right? So that's why we are giving get or create. Then we are importing all these things, right? Once we import it, after that we can say that, okay, we will want to read this JSON file. So this employee.json we want to read up here. And in the end, we want to output this value, right? So this DF becomes my data frame containing the value of my employee.json. So this JSON value will get converted to my data frame. Now in the end, we are just outputting the result. Now, if you notice here what we are doing, so here we are first of all importing our Spark session. Same story, we are just executing it. Then we are building our things. We're telling that we are going to create that. Again, we are importing it. Then we are reading our JSON file by using read.json API. We are reading our employee.json, okay, which is present in this particular directory, and we are outputting. So you can see that JSON format will be the key value format. But when I'm doing this df.show, it is just showing up all my values here. Now let's see how we can create our data set. Now when we talk about data set, you can notice what we're doing. Now we have understood all this, so let's see how we can create a data set. Now first of all, in dataset, what we do, so in dataset, we can create the class. You can see we are creating a case class employee, right? Now in case class, what we are doing, we are then just creating a sequence, inputting the value Andrew, age, like name and the age column. Then we are displaying our output, all this data set, right? Now we are creating a primitive data set also to demonstrate mapping of this data frames to your data sets, right? So you can notice that we are using 2DS. Instead of 2DF, we are using 2DS in this case. Now you may ask me what's the difference with respect to data frame, right? So with respect to data frame, in data frame what we were doing, we were create again the data frame and data set both exactly look same. It will also be having the name column and rows and everything up. It is introduced lately in 1.6 versions and later. And what is it provides it? It provides a encoder mechanism using which you can get when you are, let's say, reading the weight data back. Let's say you are deserializing and not doing that step, right? It is going to be faster. So the performance wise data set is better. That's the reason it is introduced later. Nowadays, people are moving from data frame to data set sites. Okay, so now we are just outputting in the end. See the same thing in the output part. So we are creating employee class, then we are putting the value inside it, creating a data set, we are looking at the values, right? So these are the steps we have just seen, understood that. Now how we can read our file? So we want to read the file, so we will use read.json as employee. Employee was what? Remember case class which we have created last time? This was the class we have created here, case class employee. So we are telling that we are creating like this. Then we are just outputting this value. We're just using show, you can see. This way we can see this output also. Now let's see how we can add the schema to RDD. Now in order to add the schema to RDD, what we are going to do? So in this case also, you can look at, we are importing all the values, right? We are importing all the libraries, whatever are required. Then after that, we are using this Spark context text file, reading the data, splitting it with respect to comma, then mapping the attributes to your employee case class, what we have done, and converting these values to integer. So in the end, we are converting to 2DF, right? After that, we are going to create a temporary view or table. So let's create this temporary view employee. Then we are going to use spark.sql and passing up our SQL query. Can you notice that we are now passing the value and we are assessing this employee, right? We are assessing this employee here. Now, what is this employee? This employee was our temporary view which we have created. Because the challenge in Spark SQL is whenever you want to execute any SQL query, you cannot say select asterisk from a data frame. You cannot do that. This is not even supported. So you cannot do select asterisk from your data frame. So instead of that, what we need to do is we need to create a temporary table or a temporary view. So you can notice here we are using this create or replace temp view. Why replace? Because if it is already existing, override on top of it. So now we are creating a temporary table which will be exactly similar to this data frame. Now you can just directly execute all the query on your temporary view or temporary table. So you can notice here, instead of using employee df, which was our data frame, I'm using here temporary view. Okay. Then in the end, we are just mapping the names and all, right? And we are outputting the values. That's it. Same thing. This is just an execution part of it, right? So we are just showing all the steps here. You can see in the end, we are outputting all this value. Now, how we can add this schema to RDD? Let's see this transformation step. Now in this case, you can notice that we can map this youngster, right? So we are converting this map name into the string for the transformation part, right? So we are checking all this value that, okay, this is the string type name. We are just showing up this value, right? Now what we are doing, we are using this map encoder from the implicit class, which is available to us, to map the name and age part. Okay, so this is what we are going to do, because remember in the employee case class, we have the name and the age column that we want to map now. Now in this case, we are mapping the names to the ages. So you can notice that we are doing for ages of our youngest DF data frame, that what we have created earlier. And the result is an array. So the result what you're going to get will be an array with the name mapped to your respective ages. You can see this output here. So you can see that this is getting mapped, right? So we are seeing this output like name is John, age is 28. That is what we are talking about. So here in this case, you can notice that it was representing like this. In this case, the output is coming out in this particular format. Now, let's talk about how we can add the schema, how we can read the file, we can add our schema and all. So we will be first of all importing the type class into your Spark shell. So this is what we have done by using import statement. Then we are going to import the row class into the Spark shell. So row will be used in mapping RDD schema, right? So you can notice we are importing this also. Then we are creating an RDD called as employee RDD. So in this case, you can notice that is the employee RDD we are creating, and we are creating this with the help of this text file. So once we have created this, we are going to define our schema. So this is the schema approach. Okay. So in this case, we are going to define it like name, then space, then age. Okay. Because these were the two I have in my data also. In this employee.txt, if you look at, these are the two data which we have, name and age. Now what we can do, once we have done that, then we can split it with respect to space. We can say that our mapping value, and we are passing it all this value inside our struct field. Okay, so we are defining our now fields RDD. That is what we are doing here. See this fields RDD, which is going to now output after mapping the employee RDD. Okay, so that is what we are doing. So we want to just do this into my schema string. Then in the end, we will be obtaining this field. If you notice this field what we have created here, we are obtaining this into a schema. So we are passing this into a struct type, and it is getting converted to your schema way. So that is what we will do. You can see all this execution, same steps we are just executing in this terminal. Now let's see how we are going to transform the results. Now whatever we have done, right? So now we have already created an RDD called row RDD. So let's create that row RDD we are going to create, and we want to transform the employee RDD using the map function into row RDD. So let's do that. Okay. So in this case, what we are doing, so look at this employee RDD, we are splitting it with respect to comma, and after that we are telling, see, remember we have name and then age like this. So that's what we're telling. We're telling that attribute 0, comma attributes 1. And why we're trimming it? Just in order to ensure if there is no spaces and all which are there. So those things we don't want to unnecessarily keep up. So that's the reason we are defining this trim statement. Now after that, once we are done with this, we are going to define a data frame employee DF, and we are going to store that RDD schema into it. So now if you notice this row RDD which we have defined here and schema which we have defined in the last case, right? Now if you go back and notice here, schema we have created here, right, with respect to my fields. So that schema and this value what we have just created here, row RDD, we are going to pass it and say that we are going to create a data frame. So this will help us in creating the data frame. Now we can create our temporary view on the base of employee DF. Let's create an employee temporary view. And then what we can do, we can execute any SQL queries on top of it. As you can see, spark.sql, we can create all the SQL queries and can directly execute that. Now what we can do, if we want to output the values, we can quickly do that. Now we want to, let's say, display the name. So we can say, okay, attribute 0 contains the name. We can use the show command. So this is how we will be performing the operation in the schema way. Now, so this is the same output way, means we are just executing this whole thing up. You can notice here also, we are just saying attribute 0.show. It is representing all my output. Now, let's talk about JSON data. Now, when we talk about JSON data, let's talk about how we can load our files and work on this. So in this case, we will be first, let's say, importing our libraries. Once we are done with that, now after that, we can just say that read.json. We are just bringing up our employee.json here. See, this is the execution of this part. Now, similarly, we can also write back in the Parquet, or we can also read the value from Parquet. You can notice this, if we want to write, let's say, this value employee DF data frame to my Parquet way. So I can say write.Parquet. So this will be created, employee.Parquet will be created, and here all the values will be converted to employee.Parquet. Only thing is the data, if you go and see in this particular directory, this will be a directory which will be getting created. So in this data, you will notice that you will not be able to read the data. So in that case, because it's not human readable, so that's the reason you will not be able to do that. So let's say you want to read it now. So you can again bring it back by using read.Parquet. You are reading this employee.Parquet which you have just created. Then you are creating a temporary view or temporary table. And then by using spark.sql, you can execute on your temporary table. Now in this way, you can read your Parquet file data. And in the end, we are just displaying the result. See the similar output of this. Okay, this is how we can execute all these things up. Now once we have done all this, let's see how we can create our data frames. So let's create this file path. So let's say we have created this file employee.json. After that, we can create a data frame from our JSON path, right? So we are creating this by using read.json. Then we can print the schema. What does do? This is going to print the schema of my employee data frame. Okay, so we are going to use this print schema to print up all the values. Then we can create a temporary view of this data frame. So we are doing that. See, create or replace temp view. We are creating that, which we have seen it last time also. Now after that, we can execute our SQL query. So let's say we are executing our SQL query from employee where age is between 18 and 30, right? So this kind of SQL query, let's say we want to do, we can get that. And in the end, we can see the output also. Let's see this execution. So you can see that all the employees whose age are, let's say, between 18 and 30, that is showing up in the output. Now let's see this RDD operation way. Now what you can do, so we are going to create this RDD, other employee RDD, now which is going to store the content of employee George and New Delhi, Delhi. So see this part. So here we are creating this by using make RDD, and we have just, this is going to store the content containing George from New Delhi, right? You can see this. So New Delhi is my city name, state is Delhi. So that is what we are passing inside it. Now what we are doing, we are assigning the content of this other employee RDD into my other employee. So we are using this spark.read.json and we are reading up the value. And in the end, we are using this show API. You can notice this output coming up. Now let's see with the Hive table. So with the Hive table, if you want to read that, so let's do it with the case class and Spark sessions. So first of all, we are going to import our row class and we are going to use Spark session into the Spark shell. So let's do that. So we are importing this row, this Spark session and all. After that, we are going to create a class record containing this key, which is of integer data type, and a value which is of string type. Then we are going to set our location of the warehouse location, okay, to the Spark warehouse. So that is what we are doing. Now we are going to build a Spark session Spark to demonstrate the Hive example in Spark SQL. Look at this now. So we are creating Spark session.builder. Again, we are passing the any app name to it. We are passing the configuration to it. And then we are saying that we want to enable the Hive support. Now, once we have done that, we are importing this Spark SQL libraries and all, and then you can notice that we can use SQL. So we can create now a table SRC. So you can see create table if not exist SRC with column to stores the data as a key comma value pair. So that is what we are doing here. Now you can see all this execution of the same step. Now let's see the SQL operation happening here. Now in this case, what we can do, we can now load the data from this example which is present now. So you see this kvm.txt file which is available to us, and we want to store it into the table SRC which we have just created. And now if you want to just view all this output, we can say SQL select extract from SRC, and it is going to show up all the values. You can see this output. Okay, so this is the way you can show up the values. Now similarly, we can perform the count operation. Okay, so we can say select count extract from SRC to select the number of keys in the SRC tables. And now select all the records, right? So we can say that key select key comma value. So you can see that we can perform all our Hive operations here on this, right? Similarly, we can create a data set string ds from Spark df. So you can see this also by using SQL df what we already have. We can just say map and then provide the case class and can map this key comma value pair, and then in the end we can show up all this value. See this execution of this. In the end you can notice this output which we wanted. Now let's see result part. Now we can create our data frame here, right? So we can create our data frame records df and store all the results which contains the value between 1 to 100. So we are storing all the values between 1 to 100 here. Then we are creating our temporary view, okay, for the records. That's what we are doing. So for records df, we are creating a temporary view so that we can have all our SQL queries. Now we can execute all the values. So you can also notice we are doing join operation here, right? So we can display the content of join between the records and this SRC table. We can do a join on this part. So we can also perform all the join operations and get the output. Now let's see our use case for it. If we talk about use case, we are going to analyze our stock market with the help of Spark SQL. So let's understand the problem statement first. So now in our problem statement, so what we want to do, so definitely everybody must be aware of this stock market. Like in stock market, you can, a lot of activities happen. You want to analyze it in order to make some profit out of it and all those stuff, right? So now let's say a company have collected a lot of data for different 10 companies and they want to do some computation. Let's say they want to compute the average closing price. They want to list the companies with the highest closing prices. They want to compute the average closing price per month. They want to list the number of big price rises and fall and compute some statistical correlation. So these things we are going to do with the help of our Spark SQL statement. So this is our requirement. We want to process the huge data. We want to handle the input from the multiple sources. We want to process the data in real time, and it should be easy to use. It should not be very complicated. So all this requirement will be handled by my Spark SQL, right? So that's the reason we are going to use the Spark SQL. So as I just said that we are going to use 10 companies. So we are going to kind of use these 10 companies, and on those 10 companies, we are going to see that we are going to perform our analysis on top of it. So we will be using the stock data from Yahoo Finance for all these following stocks. So for Enon, Bix, Axis, so all these companies we are on which we are going to perform. So this is how my data will look like, which will be having date, opening, high rate, low rate, closing, volume, adjusted, close. All this data will be present here. Now, so let's see how we can implement a stock analysis using Spark SQL. So what we have to do for that? So this is how my data flow diagram will sound like. So we are going to initially have the huge amount of real-time stock data that we are going to process it with Spark SQL. So going to convert it into a named column way. Then we are going to create an RDD for functional programming. So let's do that. Then we are going to use our Spark SQL, which will calculate the average closing price per year, calculating the company with highest closing per year. Then by Spark SQL queries, we will be getting our outputs. Okay. So that is what we are going to do. So all the queries what we are getting generated. So it's not only this, we are also going to compute few other queries what we have. So all those queries we are going to execute here. Now this is how the flow will look like. So we are going to initially have this data what I've just shown you up. Now what you're going to do, you are going to create a data frame. You are going to then create a join close RDD. We will see what we are going to do here. Then we are going to calculate the average closing price per year. We are going to hit our Spark SQL query and get the result in the table. So this is how my execution will look like. So what we are going to do in this case, first of all, we are going to initialize the Spark SQL in the Spark shell. We are going to import all the required libraries. Then we are going to start our Spark session. after importing all the required library, we are going to create our case class, whatever is required here in the case class, you can notice here. Then we are going to define our parse stock schema. So because we have already learned how to create a schema, so we are going to create this parse stock schema by creating this way. Then we are going to define our parse RDD. So in parse RDD, if you notice, so here we are creating this parse RDD, right? So we are going to create all of that by using this RDD first. We are going to remove the header files also from it. Then we are going to read our CSV file into stocks AA on DF DataFrame. So we are going to read this sc.txt file. You can see we are reading this file and we are going to convert it into a data frame. So we are parsing it as an RDD. Once we are done, then if we want to print the output, we can do it with the help of show API. Once we are done with this, now we want to, let's say, display the average of adjacent closing price for NN for every month. So we can do all of that also by using select query, right? So we can say this data frame dot select and pass whatever parameters are required to get the average now. So you can notice here inside this, we are creating the alias of the things as well. So for this DT, we are creating alias here, right? So we are creating the alias for it, now, and then we are showing the output also. So here what we are going to do, now we will be checking that the closing price for Microsoft. So let's say they're going up by 2 or with greater than 2 or wherever it is going by greater than 2 and all, we want to get the output and display the result. So you can notice that wherever it is going to be greater than 2, we are getting the value. So we are hitting a SQL query to do that. So we are hitting the SQL query now. On this, you can notice the SQL query which we are hitting on the stocks MSFT, right? This is the, we have data frame we have created. Now on this, we are doing that and we are putting our query that where my condition this to be true, means where my closing price and my opening price, because let's say at the closing price, the stock price was, let's say, $100 and at the time in the morning when it opened with the, let's say, $98. So wherever it is going to be having a difference of 2 or greater than 2, that only output we want to get. So that is what we are doing here. Now once we are done, then after that what we are going to do, now we are going to use the join operation. So what we are going to do, so we will be joining the NN and XF stocks in order to compare the closing price, because we want to compare the prices. So we will be doing that. So first of all, we are going to create a union of all these stocks and then display this join close. So look at this, what we are going to do. We are going to use the Spark SQL. And if you notice this closely, what we are doing in this case. So now in the Spark SQL, we are hitting this query SQL and all those stuff. Then we are saying from this, and here we are using this join operation, right? See? This join operation. So this we are joining it on, and then in the end we are outputting it. So here you can see you can do a comparison of all this close price for all these stocks. You can also include now for more companies. Right now we have just shown you an example with 2 companies, but you can do it for more companies as well. Now in this case, if you notice what we're doing, we're writing this in the Parquet file format and saving into this particular location. So we are creating this join stock.parquet. So we are storing it as a Parquet file format. And here, if you want to read it, we can read that and show the output. But whatever file you have saved it as a Parquet file, definitely you will not be able to read that up, because that file is going to be the Parquet way, and Parquet way are the files which you can never read. You will not be able to read them up. Now you will be seeing this average closing price per year. I'm going to show you all these things running also. So I'm just right now explaining you how things will be doing up here. So I will be showing you all these things in execution as well. Now in this case, if you notice what we are doing, again we are creating our data frame here. Again we are executing our query. Whatever table we have, we are executing on top of it. So in this case, because we want to find the average closing per year, so what we are doing in this case, so we are going to create a new table containing the average closing price of, let's say, NN, ABAX and FAST. And then we are going to display all this new table. So we are in the end, we are going to register this table also as a temporary table so that we can execute our SQL queries on top of it. So in this case, you can notice that we are creating this new table, and in this new table, we are putting our SQL query, right? That SQL query is going to contains the average closing price. So the SQL query is finding out the average closing price of NN and all these companies. Then whatever we have, now we are going to apply our transformation step. Now transformation of this new table which we have created with the year and the corresponding 3 company data what we have created into the company or table. So you can notice that we are creating this company or table, and here first of all we are going to create a transform table company or and going to display the output. So you can notice that we are hitting the SQL query, and in the end we are printing this output. Similarly, if we want to, let's say, compute the best of average close, we can do that. So in this case, again, the same way. Now, if once you have learned the basic stuff, you can notice that everything is following a similar approach. Now, in this case, also, we want to find out, let's say, the best of the average closing. So we are creating this best company here. Now, it should contain the best average closing price of ANN, ABEX, and FAST. So we can just get this greatest and all that, right? So we're creating that. Then after that, we are going to display this output, and we will be again registering it as a temporary table. Now, once we have done that, then we can hit our queries now. So we want to check, let's say, best performing company per year. What we have to do for that? So we are creating a final table in which we are going to compute all the things. We are going to perform the join and all. So all those SQL query we are going to perform here in order to compute that which company is doing the best. And then we are going to display the output. So this is what the output is being showing up here. We are again storing as a temporary view, and here again the same story of correlation what we're going to do here. So now we will be using our statistics libraries to find the correlation between ANN and ABEX companies closing price. So that is what we are going to do now. So correlation in finance and the investment industries is a statistics that measures the degree to which two securities move in relation to each other. So the closer the correlation is to be 1, this is going to be a better one. So it is always like how two variables are correlated with each other. Let's say your age is highly correlated to your salary, what you're earning, right? When you are young, you usually earn less, and when you are more age, definitely you will be earning more because you will be more mature. Similar way, I can say that your salary is also dependent on your education qualification and also on the premium institute from where you have done your education. Let's say if you are from IIT or IIM, definitely your salary will be higher from any other campuses, right? Means it's a probability with what I'm telling you. So let's say if I have to correlate now, in this case, the education and the salary part, I can easily create a correlation, right? So that is what the correlation goes. So we are going to do all that with respect to our stock analysis now. Now what we are doing in this case, so again you can notice we are creating this series 1 where we are hitting the select query. Now we are mapping all this ANN close price, we are converting to RDD. Similar way for series 2 also we are doing that, right? So this is we are doing for ABEX. So earlier we have done it for ANN close. And then in the end we are using the statistics.core to create a correlation between them. So you can notice this is how we can execute everything. Now let's go to our VM and see everything in our execution. Question from Atul. So this VM, how we will be getting? You will be getting all this VM from Edureka. So you need not worry about all that part. That how I will be getting all this VM and all. So once you enroll for the courses and also you will be getting all this VM from the Edureka site. So even if I'm working on Mac operating system, my VM will work. Yes. Every operating system it will be supported. So no trouble, you can just use any sort of VM and all, means any operating system to do that. So what Edureka do is they just don't want you to be troubled in any sort of stuff here. So what they do is they kind of ensure that whatever is required for your practicals, they take care of it. That's the reason they have created their own VM, which is also going to be a lower size in comparison to Cloudera Hortonworks VM. And this is going to definitely be more helpful for you. So all these things will be provided to you. Question from Nitin. So all this project I'm going to learn from the sessions? Yes. So once you enroll for, so right now whatever we have seen, definitely we have just got an upper level of view of this, how the session looks like for Apache Spark. But when we actually teach all these things in the course, it's usually are much more in the detailed format. So in detailed format, we kind of keep on showing you each step in detail that how the things are working, even including the project. So you will be also learning with the help of project on each different topic. So that is the way we kind of go for it. Now, if I am stuck in any other project, then who will be helping me? So there will be a support team 24/7. If you are stuck at any moment, you need to just give a call, Ankit, and a call or an email. There is a support ticket, and immediately the technical team will be helping you across. The support team is 24/7. They are all technical people, and they will be assisting you across on all that. Even the trainers will be assisting you for any of the technical query. Great, awesome. Thank you. Now, so if you notice, this is my data. We were executing all the things on this data. Now what we want to do, if you notice, this is the same code which I have just shown you earlier also. Now let us just execute this code. So in order to execute this, what we can do, we can connect to my Spark shell. So let's get connected to Spark shell. So once we'll be connected to Spark shell, we will go step by step. So first we will be importing our package. This takes some time. Let it just get connected. Once this is connected, now you can notice that I'm just importing all the important libraries. We have already learned about that. After that, you will be initializing your Spark session. So let's do that. Again, the same steps what we have done before. Once we will be done, we will be creating a stock class. We could have also directly executed from Eclipse also. This is just, I want to show you step by step whatever we have learned. So now you can see for company one, and then if we want to do some computation, we want to even see the values and all, right? So that's what we're doing here. So we are just getting the files, creating an RDD and all. So let's execute this. Similarly for your ABEX, similarly for your FAST, for all this. So I'm just copying all these things together because there are a lot of companies for which we have to do all this step. So let's bring it for all the 10 companies which we are going to create. So as you can see, this print schema is giving you the output, right? Now, similarly, I can execute for the rest of the things as well. So this is just giving you the similar way all the outputs will be shown up here, right? Company 4, company 5, all these companies, you can see this in execution. After that, we will be creating our temporary view so that we can execute our SQL queries. So let's do it for company 10 also. Then after that, we can just create all our temporary table for it. Once we are done, now we can do our queries. Like let's say we can display the average of adjusting closing price for and for each month. So we can hit this query. So all these queries will happen on your temporary view because we cannot anyway do all these queries on our data frames and all. So you can see this. This is getting executed, showing you the output also. Now, because we have done dot show, that's the reason you're getting this output. Similarly, if we want to, let's say, list the closing price for MSFT, which went up more than $2, right? So that query also we can execute now. We have already understood this query in detail. We're just seeing this execution part now so that you can appreciate whatever you have learned. See, this is the output showing up to you. Now, after that, how you can join all the stack closing price, right? Similar way how you can save the joint view in the parquet table. You want to read that back. You want to create a new table, right? So let's execute all these 3 queries together because we have already seen this. Look at this. So this, in this case, we are doing the join class. We are seeing this output. Then we want to save it in the parquet file. So we are saving it. Then we want to again read it back. Then we are creating our new table, right? Where we were doing that join and all. So that is what we are doing in this case. Then we want to see this output. Then we are again storing as a temp table and all. Now, once we are done with this step also, then what? So we have done it till step 6. Now we want to perform, let's say, a transformation on new table corresponding to the 3 companies so that we can compare. We want to create the best company containing the best average closing price for all these 3 companies. We want to find the companies with the best closing price average per year. So let's do all that as well. So you can see best company of the year, right? Now here also the same stuff we are doing. So we are registering our temp table. Okay, so there's a mistake here. So if you notice here, it is 1, but here we are doing a show of all, right? So there's a mistake here. So I'm just correcting it. So here also it should be 1. I'm just updating in the sheet itself so that it will start working now. So here I've just made it 1. So now after that, it will start working. Okay, wherever it is going to be all, I have to make it 1. So that is the change which I need to do here also. And you will notice it will start working. So here also I need to make it 1. So all those places wherever it was, so just kind of a good point to make. So wherever you are working on this, you need to always ensure that all these values what you are putting up here. Okay, so I could have also done it like this. 1 second. In fact, in this place, I need not do all this step. 1 second. let me explain you also why. No, in this place it's good. So see, from here this error started occurring. Why? Because my data frame what I have created here was 1. Let's execute it. Now you will notice this will start working. See, this is working now. Now after that I'm creating a temp table. That temp table what we are creating is, let's say, company all. Okay, so this is the temp table which we have created now. You can see this company all. Now in this case, if I'm keeping this company all itself, it is going to work. Because here anyway I'm going to use the whatever temporary table we have created, right? So now let's execute. So you can see now it started working, right? Now further to that, now we want to create a correlation between them, so we can do that. See, this is going to give me the correlation between the 2 column names and all. So that's we can see here. So this is the correlation. The more it is closer to 1 means the better it is. It means definitely it is near to 1. It is 0.9, which is a bigger value. So definitely it is going to be much, they both are highly correlated. Means definitely they are impacting each other's stock price. So this is all about the project part. What is streaming? Let's understand that. So let me start by an example to you. So let's say if there's a bank, and in bank, definitely I'm pretty sure all of you must have used credit card, debit card, all those cards what banks provide. Now, let's say you have done a transaction from India just now, and within an hour, your card is getting swiped in US. Is it even possible for your card to reach in an hour to US? Definitely no. Now, how that bank will realize that it is a fraud transaction? Because bank cannot let that transaction happen. They need to stop it at the time of when it is getting swiped. Either they can block it, give a call to you, ask you whether it is a genuine transaction or not, do something of that sort. Now, do you think they will put some manual person behind the scene that will be looking at all the transaction and he will block it manually? No. So they require something of the sort where the data will be getting streamed, and at the real time they should be able to catch with the help of some pattern. They will do some processing and they will get some pattern out of it, which if it is not sounding like a genuine transaction, they will immediately either block it or give you a call, maybe send you an OTP to confirm whether it's a genuine transaction or not. They will not wait till the next day to kind of complete that transaction. Otherwise, if fraud happens, nobody is going to trust that bank, right? So that is how we work on streaming. Now, someone have mentioned that without stream, processing of data is not even possible. In fact, we can see that there is no even big data which is possible. We cannot even talk about Internet of Things, right? And this is a very famous statement from Dana Sandhu from SQL Stream. Lot of companies like YouTube, Netflix, Facebook, Twitter, iTunes, Pandora, all these companies are using Spark streaming. Now, what is this? We have just seen with an example to kind of got an idea about streaming part. Now, as I said, with the time growing, with the internet growing, these streaming technologies are becoming popular day by day. It's a technique to transfer the data so that it can be processed as a steady and continuous stream. Means immediately as and when the data is coming, you are continuously processing it as well. In fact, this real-time streaming is what is driving today this big data and also Internet of Things. Now, there will be a lot of things like fundamental unit of streaming will be a stream. We will also be transforming our stream. We will be doing it. In fact, the companies are using it with their business intelligence. We will see more details in further of the slides. But before that, we will be talking about Spark ecosystem. When we talk about Spark ecosystem, there are multiple libraries which are present in it. First one is Spark SQL. Now in Spark SQL is like where you can, a SQL developer can write the query in a SQL way
and it is going to get convert into a Spark way and then going to give you output. Kind of analogous to Hive, but it is going to be faster in comparison to Hive. When we talk about Spark streaming, that is what we are going to learn. It is going to enable all the analytical and interactive applications for your live streaming data. Mlib. Mlib is mostly for machine learning, and in fact, the interesting part about Mlib is that it is completely replacing Mahout. In fact, it has almost replaced Mahout. All the core contributors of Mahout have moved in towards the MLlib side because of the faster response performance is really good in MLlib. GraphX. GraphX, okay, let me give you an example. Everybody must have used Google Map, right? Now, what you do in Google Map, you search for the path. You put your source, you put your destination. Now, when you just search for the path, it search multiple paths and then provide you an optimal path, right? Now, how it's providing the optimal path? These things can be done with the help of graphics. So wherever you can create a kind of a graphical structure, we will say that we can use graphics. Spark R. Now, this is the kind of a package provided for R. So R is an open source, which is mostly used by analysts. And now Spark community want, in fact, all the analysts kind of to move towards the Spark framework. And that's the reason they have recently started supporting Spark R, where all the analysts can now execute the query using Spark environment, thus getting better performance, and they can also work on big data. That's all about the ecosystem part. Below this, we are going to have a core engine. Core engine is the one which defines all the basics of Apache Spark. All the RDD related stuff and all is going to be defined in your Spark core engine. Moving further, now, so as we have just discussed this part, we are going to now discuss Spark streaming engine, which is going to enable analytical and interactive app for live streaming data. Now, why Spark streaming? If I talk about why Spark streaming, definitely we have just got an answer. Definitely it's very important. That's the reason we are learning it. But this is so powerful that it is used now by a lot of companies to perform their marketing. They kind of are getting an idea that what a customer is looking for. In fact, we are going to learn a use case of similar to that, where we are going to use Spark streaming. Now, where we are going to use a Twitter sentimental analysis, which can be used for your crisis management. Maybe you want to check how your product's gonna behave, service adjusting, target marketing. By all the companies around the world, this is getting used in this way. And that's the reason Spark streaming is gaining the popularity. And because of its performance as well, it is beating all other platforms at the moment. Now, moving further, let's see Spark streaming features. When we talk about Spark streaming features, it's very easy to scale. You can scale to even multiple nodes, which can even run till hundreds of nodes. Speed is going to be very quick, means in a very short time you can stream as well as process your data. Fault tolerant, even it makes sure that even you're not losing your data. Integration with your batch time and real-time processing is possible, and it can also be used for your business analytics, which is used to track behavior of your customer. So as you can see, this is so powerful, right? In each slide, we are kind of getting to know so many interesting things about this Spark streaming. Now, let's quickly have an overview so that we can get some basics of Spark streaming. Now, let's understand how it works. So as we have just discussed, it is for real-time streaming data. It is useful addition in your Spark Core API. So we have already seen at the base level, we have that Spark Core in our ecosystem. On top of that, we have Spark streaming. In fact, Spark streaming is kind of adding a lot of advantage to Spark community, because a lot of people are only joining Spark community to kind of use this Spark streaming. It's so powerful that everyone wants to come and want to use it, because all the other frameworks which we already have, which are existing, are not as good in terms of performance and all. and it's the easiness of using Spark Streaming is also great. If you compare your program with, let's say, Flume or with Storm, which is used for real-time processing, you will notice that it is much easier in terms of from a developer point of view as well. That's the reason a lot of people are showing interest in this domain. Now, it will also enable a high throughput and fault tolerant, so that to stream your data, to process all the things up. And the fundamental unit for Spark streaming is going to be DStream. What is DStream? Let me explain it. So DStream is basically a series of RDDs to process the real-time data. What we generally do is, if you look at this right-hand side, when you get the data, it is a continuous data. You divide it into batches of input data. We are going to call it as micro batch. And then we are going to get batches of process data. Though it is real time, but still how come it is batch? Because definitely you are doing processing on some part of the data, right? Even if it is coming at real time, and that is what we are going to call it as micro batch. Moving further. Now, let's see few more details on it. Now, from where you can get all your data, what can be your data sources here. So if we talk about data sources here, now we can stream the data from multiple sources like Parquet, Upka, Kafka. Even you have static sources like HBase, MongoDB, which are your NoSQL DBs, Elasticsearch, PostgreSQL, Parquet file format. You can get all the data from here. Now after that, you can also now do processing with the help of machine learning. You can do the processing with the help of your Spark SQL and then give the output. So this is a very strong thing, that you are bringing the data using Spark Streaming, but processing you can do by using some other frameworks as well, right? Like machine learning, you can apply on the data what you are getting at a real time. You can also apply your Spark SQL on the data which you are getting at the real time. Moving further, so this is a similar thing. Now in Spark Streaming, you can just get the data from multiple sources, like from Kafka, Flume, STFS, Kinesis, Twitter, bringing it to the Spark Streaming, doing the processing, and storing it back to your HDFS. Maybe you can bring it to your DB. You can also publish to your UI dashboard like Tableau, AngularJS. A lot of UI dashboards are there in which you can publish your output. Now, how it works, let us just break down into more fine-grained controls. Now, we are going to get our input data stream. We are going to put it inside our Spark Streaming, going to get the batches of input data. Once it executes through a Spark engine, we are going to get batches of process data. We have just seen the same diagram before, so the same explanation for it. Now, again, breaking it down into more granular part, we are getting a D stream. D stream was what? Small RDDs of data, multiple set of RDDs. So we are getting a D stream. So let's say we are getting an RDD at the rate of time 1, because now we are getting real stream data, right? So let's say in today, right now I got 1 second, maybe now I got 1 second, in 1 second I got more data. Now I got more data in the next slot, right? So that is what we are talking about. So we are creating data we are getting from time 0 to time 1. Let's say that we have an RDD at the rate of time 1. Similarly, it is just proceeding with the time. The RDD is getting proceeded here. Now, in the next thing, we are extracting the words from an input stream. So if you can notice what we are doing here, from where, let's say we started doing our operations as well. We started doing our any sort of processing. So as and when we get the data in this time frame, we started doing some processing. It can be a flat map operation. It can be any sort of operation you are doing. It can be even a machine learning operation or whatever you are doing. And then you are generating the words in that time frame. So this is how we are seeing that how granularly we can kind of see all these parts at a very high level. This work, we again went into detail, then again we went into more detail, and finally we have seen that how we can even process the data along the time when we are streaming our data as well. Now, one important point is, just like Spark context is a main entry point for any Spark application, similarly, to work on streaming, Spark streaming, you require a streaming context. What is that? when you're passing your input data stream, when you are working on the Spark engine, when you're working on the Spark streaming engine, you have to use your streaming context here. It's using streaming context only, you are going to get the batches of your input data. Now, so streaming context is going to consume a stream of data in Apache Spark. It is registers and input D stream to produce a receiver object. Now, it is the main entry point, as we discussed, that like Spark context is the main entry point for the Spark application. Similarly, your streaming context is an entry point for your Spark streaming. Now, does that mean now Spark context is not an entry point? No. When you create Spark streaming, it is dependent on your Spark streaming only. So when you create this streaming context, it is going to be dependent on your Spark context only, because you will not be able to create streaming context without Spark context. So that's the reason it is definitely required. Spark also provides a number of default implementations of sources, like you can get the data from Twitter, a character, 0MQ, which are accessible from the context. So it is supporting so many things, right? Now, if you notice this, what we are doing in streaming context, this is just to give you an idea about how we can initialize our streaming context. So we will be importing these two libraries. After that, can you see? I'm passing Spark context, SC, right? So I'm passing it every second. We are collecting the data, means collect the data for every 1 second. You can increase this number if you want. And then this is your SSC. It means in every 1 second, whatever going to happen, I'm going to process it. This is what we are doing in this case. Let's go to the D stream topic now. Now, in D stream, it is the full form is discretized stream. It's a basic abstraction provided by your Spark streaming framework. It's a continuous stream of data, and it is going to be received from your source and from processed. Streaming context is related to your Spark streaming part. Spark context is belonging to your Spark core. If you remember the ecosystem, Rahul, in the ecosystem we have that Spark context, right? Now, streaming context is built with the help of Spark context, and in fact, using streaming context only you will be able to perform your Spark streaming. Just like without Spark context, you were not able to execute anything in Spark application. Your Spark application will not be able to do anything. Similarly, without streaming context, your streaming application will not be able to do anything. It's just that streaming context is built on top of Spark context. Okay, great. Now, it's a continuous stream of data. If I'm talking about these stream, it is received from source or from a processed data stream generated by the transformation of input stream. If you look at this part, internally a D stream can be represented by a continuous series of RDDs. This is important here. Now, what we're doing is every second, remember last time we have just seen an example of like every second whatever going to happen, we are going to do processing. So in that every second, whatever data you are collecting and you're performing your operation. So the data what you're getting here will be your D stream. Means it's a content, you can say that all this thing will be your D stream part. It's a representation by a continuous series of RDD. Can you see so many RDDs getting formed? Because let's say right now in 1 second what data I got collected, I executed it. In the second this data is happening here. Okay, sorry for that. Now in the second time also it is happening here. Third second also it is happening here. No problem now. I'm not going to draw it now. Fine. So in the third second also, if I did something, I'm processing it here, right? So if you see this diagram itself, so it is every second whatever data is getting collected, we are doing the processing on top of it. And the whole continuous series of RDD, what we are seeing here, will be called as D stream. Okay, so this is what your D stream. Moving further. Now, we are going to understand the operation on D stream. So let's say you are doing this operation on this D stream, that you are getting the data from 0 to 1. Again, you are applying some operation on that. Then whatever output you get, you're going to call it as words DStream. Means this is the thing what you're doing a platform operation. That's the reason we are calling it as a word DStream. Now, similarly, whatever thing you're doing, so you're going to get accordingly an output DStream for it as well. So this is what is happening in this particular example. Now, flat map is a API. It is very similar to map. It's kind of flatten up your value. Okay. So let me explain you with an example. What is flat map? So let's say if I say that, hi, this is Edureka. Welcome. Okay. Let's say this is written. Now I want to apply a flat map. So let's say this is a form of RDD also. Now on this RDD, let's say I apply flat map. So let's say RDD. This is the RDD. Flat map. Sorry, capital. Flat map here. And then let's say you want to define something for it. So let's say you say that, okay, you are defining your variables here. Okay. So let's say a dot. Now after that you are defining your split. So you're splitting with respect to this. Now in this case, what is going to happen? Now I'm not showing you the exact thing here, just to explain you flat map, just to kind of give you an idea of how it works. It is going to flatten up this file with respect to the split what you have mentioned here. Means what? It is going to now create each element as one word. So it is going to create like this. Hi as one word, as one element. This as one word or one element, is as another word or one element, Edureka as one word or another element, welcome as one word or another element. So this is how your flat map works. Kind of flatten up your whole file. So this is what we are doing in our stream as well. Clear, Rahul? So this is how this will work. Now, so we have just understood this part. Now let's understand input DStream and receivers. Okay, what are these things? Let's understand this part. Okay, so what are the input DStream possible? There can be basic source, advanced source. In basic source, we can have file systems, sockets, connections. In advanced source, we can have Kafka, Flume, Kinesis. Okay, so your input DStreams are the DStreams representing the stream of input data received from streaming sources. This is again the same thing. Okay, so there are two types of streams which we just discussed. One is your basic and second is your advanced. Let's move further. Now, what we are going to see here. So if you notice, let's say here there are some events occurring. It is going to your receiver, and then in the DStream now RDDs are getting created and we are performing some steps on it. So the receiver sends the data into the DStream where each batch is going to contain the RDD. So this is what your DStream is doing, receiver is doing here. Now, moving further, transformations on the DStream. Let's understand that. What are the transformations available? There are multiple transformations which are possible. The most popular, let's talk about that. We have map, flat map, filter, reduce, group by. So there are multiple transformations available here. Now it is like you are getting your input data. Now you will be applying any of these operations, means any transformation step is going to happen, and then a new DStream is going to be created. Okay, so that is what's going to happen. So let's explore it one by one. So let's start with map. If I start with map, what happens with map? It is going to create batches of data. Okay, so let's say it is going to create a map value of it like this. So let's say X is mapped to B, Y is giving the output C, Z is giving the output A, right? So in this similar format, this is going to get mapped. So it is going to, whatever you are performing, it is just going to create batches of input data which you can execute it. So it returns a new DStream by passing each element of the source DStream through a function which you have defined. Let's discuss this flat map. Flat map we have just discussed. It is going to flatten up the things. So in this case also, if you notice, we are just kind of flattening up. It is very similar to map, but each input item can be mapped to 0 or more output in items here. Okay, and it is going to return a new D stream by passing each source element through a function for this part. So we have just seen an example of flat map anyway. So that same example, you can remember that will be more easy for you to kind of see the difference between with map itself. Now, moving further, filter. As the name states, you can now filter out the values. So let's say you have a huge data, you want to filter out some values, you just want to kind of work with some filtered data. Maybe you want to remove some part of it. Maybe you are trying to put some logic on it. Does this line contain this, right? Or does this line contain that? So in that case, it is filtering only with that particular criteria. So this is what we do here. So definitely most of the times your output is going to be smaller in comparison to your input. Reduce. Reduce is, it's just like it's going to do kind of aggregation on the work. Let's say in the end you want to sum up all the data what you have. That is going to be done with the help of reduce. Now after that, group by. Group by is like it's going to combine all the common values. That is what group by is going to do. So as you can see in this example, all the things which are starting with C got group by, all the things names starting with J got group by, all the names starting with T got group by. Now, so again, what is this stream window? Now, to give you an example of this window, everybody must be knowing Twitter, right? So now what happens in Twitter? Let me go to my paint. So in this example, let's understand how this windowing operation works. So let's say in initial first second, 10 seconds, let's say the tweets are happening in this way. Let's say #A, #A, #A. Now, which is the trending tweet here? Definitely A, right? A is my trending tweet. Maybe in the next 10 seconds, now again #A, #B, #B is occurring. Which is the trending tweet? B is happening here. Now, let's say in another 10 seconds, now this time, let's say #B, #B is happening. Now, which is trending? B is occurring. But now, I want to find out which is the trending one in last 30 seconds. #B, right? Because if I combine, I can do it easily. Now, this is your windowing operation example. Means you are not only looking at your current window, but you are also looking at your previous window. When I say current window, I am talking about, let's say, 10 seconds of slot. In this 10 second slot, let's say you are doing this operation on #B. So this is your current window. Now you are not only computing with respect to your current window, but you are also considering your previous window. Now let's say in this case, if I ask you, can you give me the output of which is trending in last 17 seconds? Will you be able to answer? No. Why? Because you don't have partial information for 7 seconds. You have information for your 10, 20, 30, means multiple of 10, but not intermediate one. So keep this in mind. Okay. So you will be able to perform windowing operation only with respect to your window size. It's not like you can create any partial value and can do the window operation. Now, let's get back to the slides. Now, it's a similar thing. So now it is shown here that we are not only considering the current window, but we are also considering the previous window. Now, let's understand the output operations of the D stream. When we talk about output operations, so output operations are going to allow the D stream data to be pushed out to your external system. If you notice here, means whatever processing you have done with respect to whatever data you are doing here, now your output you can store in multiple places. You can store it in the file system, you can keep in your database, you can keep even in your external systems. So you can keep in multiple places. So that is what being reflected here. Now, so if I talk about output operation, these are the ones which are supported. We can print out the value. We can use save as text file. When we use save as text file, it saves it into your HDFS. If you want, you can also use it to save it in your local file system. You can save it as an object file also. You can save it as a Hadoop file, or you can also apply for each RDD function. Now, what are for each RDD function. Let's see this example. So generally we explain all these parts in detail once we teach you in Edureka sessions, but just to give you an idea. Now this is a very powerful primitive that is going to allow your data to be sent out to your external systems. So using this, you can send it across to your out to your external systems. We have just seen our external system that it can be a file system, it can be anything. So using this, you will be able to transfer it. You will be able to send it out to your external systems. Now, let's understand the caching and persistence. Now, when we talk about caching and persistence, so DStream is also allowing the developers to cache or to persist the stream's data in memory. Means you can keep your data in memory. You can cache your data in memory for longer time. Even after your action is complete, it is not going to delete it. So you can just use this as many times as you want. So you can simply use your persist method to do that. So for your input streams which are receiving your data over the network, maybe using Kafka, Loom, sockets, the default persistence level is set to the replicate the data to 2 nodes for the fault tolerance. Like it is also going to be replicating the data into 2 parts. So you can see the same thing in this diagram. Let's understand this accumulators, broadcast variables, and checkpoints. Now these are mostly for your performance part. So this is going to help you to kind of perform, to help you in the performance part now. So it is accumulators is nothing but a variable that are only added through an associative and commutative operation. Usually, if you are coming from Hadoop background, if you have done, let's say, any MapReduce programming, you must have seen something about counters. Right? There we used to have a counters, which kind of helps us to debug the program as well, and you can perform some analysis in the console itself. Now, this is similar thing you can do with the accumulators as well. So you can implement your counters with this part. You can also sum up the things with this part. Now you can, if you want to track through UI, you can also do that. As you can see in this UI itself, you can see all your accumulators as well. Now, similarly, we have broadcast variables. Now, broadcast variables allow the programmer to keep a read-only variable cached on all the machines which are available. Now, it is going to be kind of caching it on all the machines. Now, they can be used to give every node a copy of a large input data set in an efficient manner. So you can just use that. Spark will also attempt to distribute the distributed broadcast variable using efficient broadcast algorithm to reduce the communication cost. So as you can see here, we are passing this broadcast value. It is going to Spark context and then it is broadcasting to these places, right? So this is how it is working in this application. Generally, when we teach in these classes and also, since these are advanced concepts, we kind of try to explain you with the practicals and all. Right now, we just want to give you an idea about what are these things. So when you go with the practicals of all these things, like how accumulators, see how this is happening, how it is getting broadcasted, things become more and more clear at that time. Right now, I just want that everybody at least get a high level overview of things. Now, moving further, so what is checkpoints? So checkpoints are similar to your checkpoints in the gaming. Now they can they make it run 24/7, make it resilient to the failure, unrelated to the application logic. So if you can see this diagram, we are just creating the checkpoint. So as in the metadata checkpoint, you can see it is the saving of the information which is defining the streaming computation. If we talk about data from checkpoints, it is saving of the generated RDD to the reliable storage. So this both are generating the checkpoint. Now moving forward, we are going to move towards our project where we are going to perform our Twitter sentiment analysis. Let's discuss a very important use case of Twitter sentimental analysis. This is going to be very interesting because we will just do a real-time analysis on Twitter sentiment analysis, And there can be a lot of possibility of this sentiment analysis, but we will be taking something from the Twitter, and it's going to be very interesting. So generally, when we do all this in our course, it is more detailed, because right now in the webinar, definitely going in deep is not very much possible. But during the training of Edureka, you learn all these things within the class. Awesome, right? That's something which we learn it during the session itself. Now, if we talk about some use cases of Twitter, as I said, there can be multiple use cases which are possible, because there are a lot of emotions behind whatever the campaign you are doing, right? So much of social media right now in these days are very active as well, right? You must be noticing that even politicians have started using Twitter, and that all their tweets are being shown in the news channel, and in fact they become a hot trending tweet. People start talking about positive, negative when any politician do something, right? And if we talk about anything else, even if we talk about, let's say, any sports, FIFA World Cup is going on, then you will notice always Twitter will be filled up with a lot of tweets, right? So how we can take use of it, how we can do some analysis on top of it. That's what we are going to learn in this. So there can be multiple sort of sentiment analysis, like it can be done for your crisis management, service adjusting, target marketing. We can keep on talking about when a new movie is released. Now even the movie makers kind of go and try to predict, okay, how this movie is going to perform. So they can easily make out even beforehand, okay, this movie is going to go in this kind of range of profit or not. So interesting, right? Earlier days it was not even possible. Even in the political campaign, in fact, you must have heard that in US when the president election was happening, they have used, in fact, a lot of social media, all this analysis and all, and that have in fact played a major role in winning that election. Similarly, how whether investors want to predict whether they should invest in a particular company or not, whether they want to check that whether like we should target which customers for advertisement, because we cannot target everyone. Problem with targeting everyone is that if we try to target everyone, it will be very costly. So we want to kind of set a target. Okay, these may be my set of people whom I should send this advertisement to be more effective, and as well as it is going to be cost effective as well. If you want to review the products and services also, in that case, we can also do this. Now, let's see some use cases. Like in terms of use case, I will show you a practical how it runs. So first of all, we will be importing all the required Spark packages, because we are going to now perform Twitter sentiment analysis. So we will be requiring some packages for that. So we will be doing that as a first step. Then we need to set all our authentication. Without authentication, we cannot do anything else. Now here the challenge is we cannot directly put your username and password, right? Don't you think it will get hacked if I put your username and password, right? So Twitter came up with something very smart thing. What they did is, they came up with something called as authentication tokens. So you have to go to dev.twitter.com, log in from there, and you will find kind of all these authentication tokens available to you. 4 will be there. You need to take them and put it here. Then, as we have learned the D-stream transformation, you will be doing all that computation here. So you will be having a D-stream transformation. Then you will be generating your tweet data and going to save it in this particular directory. Once you are done with this, then you are going to extract your sentiment. Once you extract it, and you're done. Let me just show you quickly how it works in our VM. Now, one more interesting thing about Edureka would be that you will be getting all this configuration machines. So you need not worry about from where I will be getting all this. Is it like very difficult to install? When I was going in this open source location, it was not working for me. In my operating system, it was not working. So many things we have generally seen people face issues. To resolve everything up, we kind of provide all this VM. Question from Rahul, this VM has pre-Spark? Yes, that's what. It has everything pre-installed, whichever will be required for your training. So that's the best part what we also provide. So in this case, your Eclipse will already be there. You need to just go to your Eclipse location. Let me show you how you can also go there if you want. As you can see, when Eclipse is there, you just need to go inside it and double click on it and start. You need not go and kind of install Eclipse and all. Even the Spark will already be installed for you. Let us go in our project. So this is our project which is in front of you. So this is our project which we are going to work on. Now you can see that we have first imported all the libraries, then we have set our authentication system, and then we have moved and kind of extracted the D-stream transformation, extracted the tweets, right? And then save the output finally, right? So these are the things which we have done in this program also. Now let's execute it. To run this program, it's very simple. Go to run as, and from run as, click on scale application. You will notice in the end, it is Rahul is saying that's great. Good to see that. So it is executing the program. Let this execute. And we are doing it actually for Trump. So usually for Trump anyway, the tweets are going to be negative, right? So let's see that. Because anything you do for Trump is going to be negative. Trump is anyway the hot topic for us. Let me make it a little bigger also. You will notice a lot of negative tweets coming up for him. Yes. Now, I'm just stopping it so that I can show you something. Yes, it's filtering the tweet for Trump. So we have actually, while writing the program itself, we have given it one location Trump. Using that, we were kind of asking for the tweet of Trump. Now, here we are doing analysis, and it is also going to tell us whether it's a positive tweet, negative tweet. As you can see the negative tweet is coming up, right? Because for Trump, anyone will not tweet positive, right? So that's something which is there. So that's the reason you're finding this as a negative tweet. So similarly, if there will be any other tweet which will be getting extracted. So right now, if I keep on moving ahead, we will see multiple negative tweets which will come up. So that's how this program runs. Okay. So this is how our program we will be executing. We can just extract it. Even the output results will be getting stored at a location. As you can see in this, if I go to my location here, this is my actual project where it is running. So you can just come to this location. Here are all your output. Okay, all your output is getting stored there. So you can just take a look as well. Yes, so it's everything is done by using Spark streaming only. Okay, that's what we've seen, right, Robert? That we were seeing it with respect to D-stream transformations and all. So we have done all that with the help of Spark streaming only. So that is one of the awesome part about this, that you can do such a powerful things with respect to your with respect to your this part. Now let's analyze our results. So as we have just seen that it is showing up whether it's a positive tweet, negative tweets and all. So this is where your output is getting stored. I've just shown you up. The output will appear like this. Okay, this is just like your output tweets and sentiments. It will also tell whether it's a neutral one, positive one, negative one. Everything we have done it with the help of Spark streaming only. Now we have done it for Trump, as I just explained you, right? We have put in our program itself Trump, like we have put everything up here, and based on that only we are getting all this output. Now we can apply all the sentiment analysis and like this, like we have learned. So I hope you have found all this, especially this use case, very much useful for you to kind of getting at that. Yes, it is getting done by hashtag. Right now we have put Trump here, but if you want, you can keep on putting your hashtag as well, because that's how we are doing it. You can keep on changing your tags. Maybe you can kind of put for, let's say, for FIFA World Cup is going on, a cricket match will be going on. You can just put the tweets according to that. Just tweak in that place, instead of Trump, you can put any player name or maybe a team name, and you will see all that trending tweet coming accordingly. Okay, so that's how you can play with this. Now, there are multiple examples with it which we can play, and this use case can be even evolved for multiple other type of use cases. You can just keep on transforming it according to your own use cases.
Let's say we have a scenario wherein professional working in a software company checks inbox for new mails or updates and often gets frustrated after seeing unnecessary emails that we call as a spam. We do get a lot of them. You have credit card available, you have personal loan, and these days those spams have even become innovative by saying your current credit card statement or this is your credit card number, 16 digit. So you might be tempted to open that and just to realize that it made no sense. However, dealing with these kind of mails in a real world by organizations like Gmail and Yahoo is not an easy task. It requires a lot of testing. It requires a lot of confidence on the process wherein these organizations do not end up specifying something as a spam that could otherwise have shown up in your inbox, and it could potentially have a business impact. They have to make their algorithms a bit lenient to even allow some percentage of spams when there is an element of ambiguity in identifying whether this is actually a spam or an actual email. So I'll go through some of these scenarios. especially in the context of this problem, the challenge that the organization faces is they are receiving a lot of unnecessary and disturbing emails from quite a long time. So if this happens within an organizational email network or within your organizational domain, then this really becomes a challenge. So you would have noticed that the organizations have very strong filters implemented through which you often do not get to see such nuisance emails. Only the relevant ones show up, or only on portals where you have explicitly allowed your professional or official mail ID to be used as subscription. Only then you get to see notifications from them. So there are a lot of challenges that need to be addressed as part of this problem, and you often get to know from IT support and help desk that these are spam mails which can even corrupt your system. So they try to find a solution most of the times, and these days every organization tries to explore if the solution can be implemented using machine learning because of the fact that these systems are smart enough to adapt to the changes as well. They not only get expert in classifying something as a spam which has already been seen in the past, but they have a pattern based learning through which they also try to identify if any new mail can potentially be flagged as a spam and can be thrown out of the inbox. So spam mails like this, lottery emails or phishing emails that allow that say your bank account has been compromised, or it might even appear to come from your organization by saying you did not go through these compliance check, or this process is pending, you did not submit your expense on time. There could be so many things. So you potentially require a system that has the ability to properly classify these emails as a spam or not a spam. So who can help address these problems? It's mostly data scientists these days in combination with data engineers who try to address this problem. And since you are learning Spark, you can also become either a data engineer or a data scientist solving such problems in future. So it is important to understand how to solve a problem in machine learning. And for that, we must know what kind of problem it is. So let's say the solution looks like this, wherein you have labeled data. Now within labeled data, you could see there are three types of envelopes that are shown here. One is red, one is yellow, one is blue. Each one of these can have a special meaning. Red could be something that is confidential, yellow could be something that is a spam, and blue could be something that is not a spam but not confidential at the same time. And all of these, so let's say red and blue shows up in your inbox and yellow is classified as a spam. And for you to build a model around this data, you would like to know what email was classified as a spam in the past and what email was considered as a genuine email. So you'll require millions of emails for your algorithm to be trained to understand what is spam and what is not a spam. So machine is programmed to learn from labeled data to create rules based on which we are able to classify the mails. So by labeled data, we mean we not only provide emails, but along with every email, we provide a tag that says this is a spam or this is not a spam. So something that is not a spam, it goes to inbox, and something that has the tag as a spam, it goes to spam box. So the solution lies in the fact you need to apply machine learning, and for that you must understand what it is and what are different types of problems within machine learning. Machine learning is a method of data analysis that automates analytical model building. Using algorithms that iteratively learn from data, machine learning allows computers to find hidden insights without being explicitly programmed where to look. Now, this is a definition, but it has a lot of important terms embedded in it, like data analysis and automated model building. So, until now, or prior to the advent of machine learning, we were still analyzing data. However, we were doing it as a one time activity wherein we said we got this data from client, analyze this, find gaps in data, find fraud in data, depending on what the objective was and what the problem was. We used to analyze data from that perspective and then come up with the result of analysis in textual form, in the form of spreadsheets, or in the form of visualizations. Now, on top of that, a new process that is often being followed these days is to apply a machine learning model that not only applies that data analysis techniques in a repetitive fashion over and over on historical data as well as on new data that shows up in the system, and often has the ability to improve its analysis, the outcome of analysis. And based on that outcome, it also has the ability to take a decision similar to a decision that is taken by humans. So as part of that, we need to implement an algorithm or use an existing algorithm that has the ability to continuously learn from data. And machine learning is one such process that allows computers to perform that learning instead of humans. and find hidden insights without being explicitly programmed where to look for. So this is very similar to the way we have been learning any subject as a human being. We used to learn something, appear for an exam. If we did not get good score, we used to go back and then again spend more time on that subject, or avail an extra class, or avail an external help in the form of a tuition or an online resource to get a better understanding on that subject. And we did that continuously, iteratively, until we got a good score in that exam. However, that again was driven by the fact if you wanted to improve. If you did not want to improve, you can let that continue as it is. So, assuming that we want to improve in every aspect, that is the process we follow. And similar to that, that machines that we train, they also have to go through a similar process wherein they not only have the ability to learn, but there is also a process that measures that ability continuously through some standard checks. Again, those checks are applicable to respective algorithms in a different mathematical formulae. And based on the outcome from those tests, if an algorithm does not perform well, it is severely penalized. If it performs well, it continues to improve its accuracy, and its score at detecting things in a right way also continues to improve. So, what are some of the features of machine learning that are part of this process? So first of all, it requires data to detect patterns in the data in a data set and accordingly adjust program actions. Second, it focuses on the development of computer programs that can teach themselves to grow and change when exposed to new data. So as part of these two features, first of all, the algorithm requires some knowledge. So for us to learn a subject, we required a book. A book was written by a person who was expert at that subject. Similarly, machine learning requires data. That data is provided by a person, an organization, set of people who have analyzed that data manually or through some process, and they very well know that, let's say if this data is email data, they know that this email is a spam or not a spam. So they come up with the accurate data. Now if your data itself has problems, then even the machine learning algorithm cannot do justice to the problem. So if you come up with a large number of emails that are spam, but you classify them as not a spam, then you cannot blame the algorithm to automatically say these are a spam. And especially this brings me to another important or an interesting topic of conversation. So recently there was news that over last couple of years, Amazon was building an algorithm to deal with the appraisal process within their organization. Once that algorithm was ready, they also started applying it to identify if there was a possibility of attrition from an employee. While they were using it, after a period of year or so, they identified that this algorithm was continuously biased towards men, and it wasn't yielding better appraisal percentages for women. So one thing they initially concluded was even the algorithm was biased. But then how did algorithm get biased automatically? When it has to rely on data, then that means if data has bias, only then that will get percolated to the model as well. So when they looked at the data that was supplied to the model, they realized that the historical data itself was biased towards men. And because of that, they had to stop using that model and rather implement manual processes. So they eventually stepped on a plan wherein they said over last couple of years, the data that they have accumulated will not be supplied to the algorithm, and rather they will start using the algorithm 2 or 3 years down the line when they have manually implemented and improved some of the processes that get rid of that bias, so that the data that they share to the model is more balanced. So if you have such inherent gaps in the data itself, even the algorithms cannot improve because the knowledge base itself is corrupted for the algorithm. So first of all, it uses data to detect patterns, and it accordingly adjusts its actions based on the understanding that it gains from that data set. Second, it focuses on the development of programs. As part of machine learning, you need either write algorithms or use existing algorithms that we refer as computer programs here. And these algorithms have the ability to teach themselves. Wherein, if you have 1 million records to be supplied as data set to the algorithm today, probably 3 months down the line, you might have 6 million. So you need not change the process or rewrite the algorithm, but rather run it again over the 6 million data set for it to understand the newer data in a better way, or to even get more expertise on the complexity of the variety of scenarios. So when we say higher the data, the better is the performance of machine learning. It's because of the reason, and for the same reason as we humans say that the more books you read, the better experience you have. That's because you would have intercepted the thought process of multiple writers who would have written in the same topic in a different perspective. Similarly, if you have more and more data to be supplied to the algorithm, it will give the algorithm more scenarios to deal with. Wherein in one scenario, an employee might be a male employee working out of San Francisco, having experience as a data engineer and might be earning 100,000. At the same time, they could be a female employee working out of New York as a data engineer with the same experience, earning 120,000. Let's say the initial data set that is part of the 1 million records that we discussed. What if 3 months down the line there are more data engineers that are hired? And then that also brings up the cases wherein few of the male data engineers in New York they earn higher than the female data engineers or vice versa. So there could be a variety of combinations that can be introduced in the data set. So the higher the volume of data set, the wider is a variety of complex scenarios, and better is the ability of machine learning to say, I know at least these 20 scenarios, and for sure I can do justice to these 20 scenarios. And probably if I come up with a 21st scenario that is largely a combination of the factors that are seen in the existing 20 scenarios, I'll be able to come up with an accurate result in that case as well. So that way they continue to teach themselves and grow and change when exposed to new data. So we have a question wherein a person wonders how machine learning is useful in industry. So there are several industries. I would say every industry is using machine learning these days, and none of them is an exception. So we have tools like Siri from Apple. We have marketing and sales campaigns driven by machine learning algorithms. We have a lot of improvement showing up in healthcare. One example is Google recently came up with a lens, or I think it was again embedded as part of the Google Lens, wherein they have a feature through which they can do a retina scan, and through your retina scan they can identify whether you have diabetes or not, or what is the potential of you being diabetic in future. And for implementing this algorithm, they hired several doctors and PhD scholars in the healthcare to provide them information as to what patterns can be deciphered from retina scan veins and images to potentially come to a point wherein someone can be labeled as a diabetic person or a non-diabetic person. Then we have application financial services. Financial services often is the industry that drives most of the innovation because of the money factor being involved there. We have biometrics making use of machine learning. It is being applied in transformation. All of us know about Google cars and Uber cars that are being tried in US. But then the good part is, irrespective of the industry wherein the machine learning techniques are applied or the problems are encountered, the process to approach that problems remain the same, and there is a structured approach to that. And if we get familiar with that, then potentially we could also solve several problems using machine learning in future. So let's get familiar with the different phases of machine learning to understand that structured process and see what steps it entails. So first of all, we have training data. That is the actual data that is supplied to the algorithm on which it has to train itself. This is the knowledge base for the algorithm. That data is run through the algorithm and we come up with a model. So the outcome of the algorithm is actually a model. This again depends on what programming language you use to build this model. These are often available in the form of objects created within that programming language. So in Python, you will have linear regression model. Again, that will be a Python object. You will have a logistic regression model, random forest model. All these will be objects if you are using scikit-learn library. So objects of that library. If you start using Spark ML, the objects that we create here will be Spark Mlib objects. Once we have the model ready, we run it through test data. Now you would notice there is one pointer on top that says training data is 70 to 80% of the data set. So what if the data that we come across, we run all of that for the purpose of training and supply that as a knowledge base? We also need to think of the process wherein we should be able to test the model, evaluate the accuracy before rolling it in production. So you need to have some confidence and some benchmarks to say your algorithm has certain level of accuracy. Otherwise, your model will never be allowed to be rolled in production. To do that, often the best way is the knowledge base or the data set that you have. Why not set aside 70 to 80% only to be supplied to the model for the purpose of learning, and then remaining 30 to 20% that remains. So this 30 to 20%, you have the actual labels in place, the actual output available with you. When you supply this for the purpose of testing in this step, so when this goes in here for the purpose of testing, you would actually be able to come up with the predictions from the model and compare those predictions with the actual output. So only when you have actual output for the purpose of comparison against predictions, you will be able to know the accuracy of your model. So often this is a good rule of thumb, wherein if you have very high volume of data, you would set aside 30% for the purpose of testing. And if the volume is not too high, you will set aside approximate 15 to 20% for the purpose of testing. And once you have tested your model and tweaked it, improved its accuracy, you can again supply entire data as a training data set. And that way, now your model is ready to be rolled in production because you have already assessed the accuracy benchmarks. And post accuracy, the only step that remains is to apply that in production. Now, there is another new method that is being followed these days, wherein since organizations observe that data is increasing crazily year over year, they have the process of retraining their model every few months or every year, probably depending on the volumes of the data and the process that an organization wants to follow. So when it comes to implementing the entire model that we have just seen, these are the standard steps that are followed in machine learning. First is we need to collect data. So in some areas, especially in the areas of research, you might not have all data available. So that way you will have to identify what are the relevant sources from which you can collect data. However, in other areas wherein you already have the data and you need to apply machine learning, collection is merely a process of setting connectors that can pull data from those data sources and then run that through a pipeline that has the ability to cleanse that data or to start analyzing that data. So step two is about data wrangling, and you could see there are four steps within that. One is you do a data discovery, identify the structure of the data. So while we were dealing with employee data set or with the people data set, we would have observed many files did not have a header. So what if you get a CSV that is of size 1 gig and you don't have a header? What do we do with that? So it is difficult to identify or say what is name, what is age, what is salary. Age and salary could easily be distinguished. Similarly, names can be distinguished. But what if you have such attributes that are numeric in nature, but then you are not able to make out whether this is the age of the person or the number of months spent by a person within the organization or something else? So data discovery comes as the first thing. You need to discover the attributes. If header is not known to you, you'll try to generalize the attributes. If header is known to you, then you will see what are some of the things that does not make sense. Like if I have a housing price data set, wherein I say I have a list of houses in a given locality, and there are certain properties related to a house, like the area of the house in a square foot, the number of bedrooms in the house, whether it has a swimming pool or not, how many washrooms it has, and whether it's a corner plot, whether it's in a posh locality, what is the proximity of that house to markets. There could be several factors. But then one thing to note when going through this data set is, what if the size of the house is specified 5 times? Once in a square foot, then in square meters, then in square yards, then in another two units of measurement. So in that case, size of the house can be specified only in one unit of measurement, and I do not require the other four because other four have direct relationship to the one that I choose in the form of a mathematical formula, wherein a square feet can be converted to a yard and yard can be converted to a meter. So I don't require the other four features, because if I include all five of them and build a model, then out of 20 features, 5 features are related to the size of the house. So my model will be more biased towards size of the house than taking into account other features that also might have an equally important role to play. So discovery is just taking a look at the data, applying some thought to it, say, is this actually required? And once you go past that exercise, you also uncover the structure in data wherein something can be directly related, can be derived in the form of a formula, can be linearly related. So getting rid of these features. Then third process is cleansing. Machine learning models require everything to be in numeric format. So what if you have a data set that has the gender of the person is specified as male or female? Male or female cannot be interpreted as a number. But then you could very well say, why not represent all males as 0 and all females as 1, or anything as 10 or 20, any two numbers. So that is the process of cleansing. Second, what if there are null values? Would you want to substitute all null values with averages or something equivalent? So all that is part of the cleansing process, and there can be many more things that can be done in that step. And the last process in step two would be enriching the data. You have a data set that has latitude and longitude in it. Let's say you're talking of Uber rides, and we want to assess what are the cities in the world that have the highest Uber rides at any given hour. And to get to that, when we take a look at the data, we say there are no city and country information specified as part of the data set, but we do have latitude and longitude. So using latitude, longitude, we can very well arrive at city and country related to that geo coordinate. So that is a process of enrichment wherein you might want to say, I do have the information, but the form in which it is available, that is not relevant to the analysis that I want to perform, because I later on want to aggregate data based on city or based on country. So to get to that point, you will have to convert geo coordinates to respective information that you want to derive from. So that is all involved in data wrangling. Third is data analysis, wherein you might want to see if there are some things that cannot be interpreted, like the description of a product. Is that really clean? Is that consistent? So what if you were to analyze products that are listed on Amazon or Flipkart websites and go through the description of those products? So that will require data analysis, data cleansing, data wrangling, all three of them put together. And on top of that, you'll also require data quality to make sure that a shoe listed on Amazon does not have the description of a dress or a kid's apparel. So you might want to match that as well as part of the data analysis. Why do we do that? Because once we start training the algorithm, we don't want our algorithm to learn something that is not correct. Like in the case of Amazon hiring process, it wasn't correct to feed biased data towards algorithm itself. So all these pre-steps need to be performed on any given data set, not only from the perspective of statistics. We really need to think what problem we are dealing with, what kind of complexities can come in the form of scenarios in the data set, and in addition to technically cleansing the features, did we pay attention to the business context to see if the data is free from bias and if it has sufficient variance in terms of variety of factors to be supplied to the algorithm? So in this case as well, we don't want shoe to carry description of an apparel or an eatable item to carry description of a hammer or a tool. So all that will be part of the data analysis. And once you are done with the data analysis, you will start training the algorithm. For training, you'll use 70 to 80% of the data set, remaining for testing. And once you're done testing, you will deploy the model, provided it meets the level of accuracy that is expected from it. So these are the steps in nutshell. Collection of data might involve data collection from multiple sources, could be PDF, Excel, YouTube, data source, databases, Twitter, and many more. Data wrangling, you will do data filtering, data cleansing, convert raw data to some semi-structured format, especially if you talk of machine logs or cybersecurity events. They're all in textual form. So you'll have to run them through a regular expression to always extract tokens out of the data for that data to make some sense. And those expressions again should have some label wherein you will say this piece of information is time stamped from position X to position Y. From position A to B, we have the user ID of the person. From position C to D, we have the IP address of the machine. So you label the data and you also extract data as part of wrangling. Then you analyze data to identify, do I require all columns in the data set? Are there any repetitive columns? Should I get rid of some of them, or do I still need to retain them? And are records consistent wherein the name of the record matches the description attribute, or all names are sanitized, are standardized, all product descriptions are in a standardized format? There are a lot of things that you might want to do. And finally, you would train the model. You'll define the training algorithm, run your data set through that to come up with a model, and use that model to assess the accuracy of that model by supplying test data through it. And we'll compare the predicted output with the actual output as part of the accuracy measurement. And finally, once you have the acceptable speed and accuracy derived from the model, then you will roll that out in the production environment. So what are the different types of machine learning that we would have to go through and follow the steps that we have just learned? Unfortunately, supervised learning is the only learning that follows all these steps. Unsupervised learning does follow majority of the steps that we have learned, but not all. There are few that might not be applicable in unsupervised learning. And reinforcement learning has its own way and own process to follow when it comes to implementing it. So we'll now take a look at all three different types of machine learning. And to begin with, what is a supervised learning? So let's say you were to detect the face of a person. So what you would require in that case, exercise is to identify the image that we are going through. Is that a face of a person or is that something else? So all it requires is you need to have a bunch of images Along with that, you need to have a label that says this image has a face and this image does not have a face. These algorithms essentially are computer programs. They have no intelligence of their own, but they are smart enough to learn from our dataset. So we need to provide the intelligence. So we need to tell them initially that from a human's perspective and from our eyes, these are faces that we say here on top, the first 12 images, and then followed by that, the remaining 9 images, they are not faces. So we will tag the first 12 with the label as face and the second with the label as non-face. So this is the input raw data. This goes through the algorithm, and I mean, you would have performed the requisite steps for cleansing the data, analyzing the data, and collecting it. At the time of it being fed to the algorithm, it goes through the training data set. There is a supervisor within the model that governs process of getting familiar with the data set and learn the data set in a better way. So this process yields a model through the processing that it follows internally, and it comes up with this model that we call as a trained model that has the ability to identify what is face and what is not a face. And when we feed a new input to this model, it is able to tell us whether it's a face or not a face in that model. So this is supervised learning. But what are few things that are visible in this process? First of all, supervised learning algorithms are trained using labeled examples, such as the input where desired output is known. Or if you were told at a school in a standard 6 or standard 7 when you started learning science, teacher said, go and learn physics, go and learn biology, or go and learn chemistry without specifying the curriculum. You would have no idea as to what is expected from you and what you would expect in the exam if that had been so vaguely defined. Similarly, there are problems in machine learning wherein you might not know what are the labels associated with the data. So, what if you are given a salary of 2 million people across the world from different regions? And you are asked to come up with three groups: high, medium, low salary groups by country. For you, what matters is you need to understand what is high, medium, low. Is that defined by a threshold wherein you say low salaries are 0 to 100,000 and middle salaries are 100,000 to 5,000 and so on? And will that be applicable across all currencies universally? That is one. Second, if not, then how do I identify these categories? So machine learning algorithms in this case, when they do not have labeled data, they have the ability to group data together into groups wherein they say that most of the objects or elements in this group have similar properties. And that's what we call as clustering or unsupervised learning. So in supervised learning, we already have labels wherein we do know in the historical data set what is high, medium, and low. But in unsupervised learning, probably that information will be lacking, and we will have to identify programmatically, algorithmically, what is high, medium, and low. So the learning algorithm in supervised learning is a set of inputs along with corresponding outputs, and the algorithm learns by comparing its output with correct outputs to find errors. It says inputs will be provided in the form of training dataset, and then you will set aside a part of training dataset for the purpose of testing, wherein you will compare actual output with correct outputs. So your output will be the actual output from model in testing process, and correct output will already be known to you. So you'll be able to find on how many records your model is actually showing in a different output and is not close to the actual output. And that will help you find errors and inaccuracies in your model. If it finds inaccuracies, it modifies the model accordingly through methods. No, I wouldn't agree with this. So actually, it does modify the model accordingly, but not through these methods. So internally, there is a process of penalizing the model, and something that we calculate internally is known as cost using gradient descent. Gradient descent again is a technique that says as and when the model progresses, it tries to identify the importance of features in the model. So if you're talking about of housing price data set, size of the house will definitely have a very good level of importance as opposed to the number of washrooms in the house, or whether a house has a swimming pool or not. That might not be important to us in India, at least. In US and some cities, that might be a governing factor. Based on that, as and when it identifies the importance of features, there are certain records that really do not match that importance, and on those records it will say, it will come up with a different output, and on that output, if you try to assess the accuracy which does not match the actual output, you will come up with a cost. Now this cost is to say that because you made a wrong prediction, this is your penalty. And the same thing happened to us when we appeared for exams. If you wrote something completely out of topic, you either earned zero, and at times the teachers had a unique way to even highlight that by saying, I'm giving you negative marks because you're really not performing well in the subject and not paying attention to my subject. So that it could be highlighted to our parents, and then we pay extra attention to those subjects. Algorithms internally do exactly the same thing. So higher the inaccuracy, higher the penalty, and higher the penalty, higher is the overall inaccuracy of the model to say that this further requires refinement or improvement. Lastly, supervised learning uses pattern to predict values of the label on additional unlabeled data. So once the model has been trained and a new record comes to it, so new record will not have label. So if you talk of emails, emails keep flowing every day in our inboxes. Does it mean that we have to train model every day in the morning for it to know what has to be classified as a spam or not a spam by the end of the day? So once it has been trained, as and when new email comes, it has to start applying intelligence in classifying that as a spam or a not a spam email. So that is supervised learning, and supervised learning requires labels to be specified. So first of all, try to go through the problem. What exactly is the problem that you're dealing with? How can we detect faces? And what do faces come in the form of? So faces come in the form of a picture and a label. But then we learned that machine learning algorithms require everything in numeric form. So those pictures that we get as input have to be converted in the form of pixels. Pixels have a numeric representation in the form of RGB values, red, green, blue, wherein you have 256 over 256 over 256 three-dimensional arrays laid one over the other. And if you convert the picture into that form, you will come up with a three-dimensional numeric array. So that can serve as an input that can be fed to the model because it's in numeric. Then human brain has been taught what a face looks like, so it can easily distinguish face from non-faces. So we will serve picture, and along with that we will also tag what is a face and what is not a face. So that will teach the machine as to what we treat as face and what we do not treat as face. That goes as input. And then features like eyes, nose, lips, they are all common to a face. So there are even algorithms to identify if there is a human nose in a picture or a human lip in a picture. So these days, organizations like Google, they have improved to the extent of saying when you pass a picture to them, they will tell you this is a street, it has an address on it, it has a direction on it, there are vehicles on the street, there are people on the street. It has the ability to come up with multiple labels related to an image. And if you are interested in reading more about it, there is a competition that is currently going on from Google. Search for Google Cloud competition on Kaggle. So it deals with the same problem wherein they want to improve their algorithm to come up with additional labels if it can identify any new labels in addition to what Google already identifies. So they basically want to improve what already exists. And once we have the models trained, what do we get in the form of results? The remaining 20-30% of the images are used for testing purposes, and these images are provided to the model to get desired results and assess the accuracy. Now, in comparison to supervised learning, we have reinforcement learning. So, as opposed to supervised learning, this is a very complex learning. It takes input in the form of raw data, and it has reward, state, selection of algorithm, best action, all these contributing to environment and again contributing back to agent. So you would see it has a cyclic flow in between, wherein data has a state, that state is supplied to an agent. That agent has the responsibility of training the model. So internally it selects an algorithm. Algorithm takes a best action. Action is reported back to an environment where all this is captured. Environment identifies if that action was correct or not. It comes up with a reward, and then again that reward changes the state of the data that again goes back to the agent. The problem with this model is it only tells you what whether an outcome is a correct outcome or not a correct outcome. It does not have the ability to tell us how to improve if something is incorrect. So in supervised learning, you do have mathematical formula associated with every problem, every algorithm to identify what are the inaccuracies and how to improve on those inaccuracies and overcome them. But in reinforcement learning, we lack all of that.
So reinforcement learning is learning how to map situations to actions so as to maximize a reward, and often used for robotics, gaming, and navigation. With reinforcement learning, the algorithm discovers through trial and error method which actions yield the greatest reward. And the algorithm provides information about whether the answer is correct or not, but it does not tell us how to improve it. So environment is everything the agent interacts with, and the agent is the learner or the decision maker, whose job is to choose actions that maximize expected reward over a given point in time. So actions are what the agent can do, and action will be the actual output that has to be mapped to a situation to maximize the reward. So as and when the action is taken, it contributes back to the environment. Environment comes up with the reward associated with that action that is reported back to the agent. And then the agent again takes another action. So agent must know whether it has to take another action or not until we ask that action to be stopped and considered as the final action. So it's all through trial and error the entire model is driven. So one of the use cases for reinforcement learning is Uber as well. So let's say Uber has this automated car which has all these features in it. It has a cooling system, location, beams, antennas, auto lock system, and remote access as well. And then there is an agent at the customer care center who takes your call and based on that call takes a decision that needs to be conveyed to the car that is running without any human. So it's an unmanned car. So we have an environment where the car actually operates, and because it is unmanned, it has to operate on its own. So it would have been trained on multiple situations based on its understanding through camera, sensor, where it has to stop and what situations it might has to stop. But that situations might not always be the entire set of situations that the car might encounter. There could be newer areas as well, especially if I talk of Indian roads. The traffic situation is not that great. And in that case, if such cars are launched in India, or especially in cities like Bangalore, Delhi, where there is a lot of traffic on roads, then probably these cars might not be able to cope up even if you add another 20 cameras to it. That's because these cars have tried to learn in the past through years of experimentation that they have to stop in such certain situations, and that has come through trial and error. But that will not be the entire set of situations that these cars will actually encounter. That is the reason even till date we get to know while testing a car, Uber car met with an accident or Google car met with an accident and it was about to hit a person or a kid maybe. So these are some of the areas where reinforcement learning is still applied, wherein the process is driven by trial and error approach and actions have an associated reward that tell that this was an appropriate action taken by the car. But it has no guarantee that the model will perform well in all situations. Now, coming to the third piece of learning in the category of machine learnings, that is unsupervised learning. So, unsupervised learning is used against the data that has no historical labels. So, there will be certain number of features associated with the house. So, in that problem itself, we know that there were certain features of the house like the size, number of bedrooms, locality, and many other things. And then the label in that case was the price of the house. That was the actual output that we wanted to expect or predict in cases wherein when we encounter new houses against which the price is not known, and we had to build model around that. But there'll be many areas wherein we will not have the final output known to us. Like as I mentioned in the case of categorization of people based on their income. And you have been asked to come up with three categories: high, medium, and low. So high, medium, and low is something that you can still work by coming up with some thresholds. So that will not require machine learning. But what if you are completely unaware of the data set that you are dealing with and you have been asked to categorize objects in that data set? That could be people, that could be items sold on any e-commerce portal or something else. So let's say we are again talking of people and we don't know what is the data all about. Could contain a list of students, it might have a list of working professionals. All you need to do is come up with categories. And when we say you have to derive the categories, that means you have to somehow group together few records in the data set so that they are similar. They could be similar on one or more than one aspects, but then that will depend on the data set that you are dealing with. So if you're talking of students, and if you try to group together students, you may group together based on age, based on the courses pursued by them, based on the university they are pursuing that course from. So all this information can be taken into account when it comes to grouping together the students. And then if you do a survey on the students and ask them what is their favorite subject, then even from that you can identify what the students can be grouped together. So when in problems wherein we don't know what is the final label, and in this case the group that we form is the final label, we don't know what will be the actual meaningful name of that group. There could be students in biology, physics, accounting, mathematics. So all these are labels, names of subjects. But when we group them together, we don't know what these labels will be. But we will know that there will be a group called C1, C2, C3, C4, and then C1 will have all similar students. And when you manually start looking at the data, then you'll realize that C1 was the group of students from accounting background. C2 was a group of students from mathematics background. So the onus of the exercise is only to come up with C1 and C2 kind of group numbers and not to get to the actual labels. Labels could be anything more meaningful. But as long as you are able to say out of 1 million records that I encountered, probably 100,000 can have this label and another 500,000 can have another label from the perspective of being similar. So unsupervised learning helps in achieving that kind of an output. It is used against data wherein the labels are not known. The system is not told the right answer. The algorithm must figure out what is being shown. So the goal is to explore the data and find some structure within it. And unsupervised learning works well on transactional data, wherein you have more details about the data. It might have some time series factor associated with it. But transactional data does not mean it has to be financial transactional data or e-commerce transactional data. It means something that has similar kind of a behavior like a transactional data, wherein you have properties of products or properties of people well defined. So that kind of data can very well be learned through supervised learning. So one good example of unsupervised learning that you encounter every day these days, especially if you go through some of the online journals and portals, they are again smart enough to take into account your preferences, and often you get a summary of new topics in your inbox that, let's say, you are more interested in research related topics, then you might probably get news on who won the Nobel Prize this time. If you are interested in politics, then you might get to know what changes are happening in the political space, how new parties are coming up. Is there a candidate challenging another candidate? Are there any change in the visa rules by Mr. Trump? Something similar to that. So all that comes as an outcome of unsupervised learning, wherein this learning takes a look at the historical pattern of you visiting different news articles. And then based on that, it has identified few categories that you often bump on. And based on that, it tries to identify what are the new articles that could be mapped to one of those categories that you might be interested in. Even in the context of looking at advertisements, that's the same. In YouTube, based on your last played videos, you get similar videos being shown up as the suggestions. And if you have tried Chromecast, probably if you play a video on YouTube on Chromecast, you will see very similar videos being lined up after the one that you have selected. If you go for instrumental, you will have more instrumental music being listed below that. So it tries to identify your preference or your category and comes up with suggestions. So that is actually an extension of unsupervised learning, wherein it not only has identified what you like, but also has come up with something called as recommendation. And you still have an option to say, okay, out of these recommendations, not all of them, but few of them, and get rid of the remaining. So this is being applied in several areas on right from e-commerce to finance to entertainment. You take any industry, and a supervised and unsupervised learning are being heavily used and applied. So popular techniques that are used unsupervised learning are self-organizing maps, nearest neighbor mapping, k-means clustering, singular value decomposition. There are many more. So these algorithms are used to segment text topics and recommend items and identify data outliers. When you think of text topics, probably when you look for a shoe next time on Amazon, Macy's, Walmart, Flipkart, any website, you will see a ton of suggestions below that will say probably a similar shoe from the same brand or similar shoe from other brands as well. I mean, if brand is not if you have not selected brand in the filter, so it is smart enough to also check if you opted for Adidas in the filter, it will probably not show you Reebok and Nike at the bottom. It will show you other variants of the Adidas itself. So that's how recommendation engines usually work, and they mine a lot of text that they go through to understand what could be the similar matching items that the user might be interested in. A case of unsupervised learning, let's say you give a basket of fruits to a kid and ask them to identify the fruits or keep all the fruits that are of a similar nature together. Then probably kid might keep green apple and red apples together, calling both as apples. That's what the kids usually learn until they have the ability to identify what is green apple and what is red apple as separate. They might just say both are apple for me. And then you might have banana or a similar shaped fruit. Then you may have grapes, and along with grapes, you might have green grapes or black grapes again that can be kept together. So we do clustering every day, unsupervised learning every day, wherein we do segment out items that are similar in nature. And that's what machine learning, unsupervised learning is all about. So these items could be separated out based on the name or based on the color or based on the property of the fruit. So you will have an input raw data that is fed to a model which does not have any labels associated with it. So there is some interpretation on the data set that is run through the algorithm. The algorithm processes that data and comes up with the output segmenting these input raw data. And by this time, we call the model to be a trained model. So in this case, regular steps that we have identified in machine learning, unsupervised learning does not have to perform training. Training was only required in cases wherein we had labeled output. In this case, we don't have labeled output, so it directly gets into the process of identifying data. And if you look closely at it, at times we call unsupervised learning as automated supervised learning. For the reason, in supervised learning, we already had labels available. In unsupervised learning, we first arrive at the labels on our own and then get down to the process of identifying what in the input data can have this label associated with them. So these are the three broad categories of problems in machine learning, and we are going to try all of that in Spark ML. So all these algorithms will be part of the Mahout and Spark MLlib or just MLlib in Spark since we are not using Mahout. So what is MLlib? MLlib is Spark's machine learning library or the ML library. It consists of common learning algorithms and utilities. So these algorithms do actually come under the three categories that we have learned. Classification, regression come under supervised learning, clustering comes under unsupervised learning, collaborative filtering again is part of unsupervised learning. Then we have dimensionality reduction that is often used to identify which features in the dataset might not be relevant and whether we want to use all of them or just a few of them as a combination to be fed to the model. As well as, in addition to these, it also has lower level optimization primitives and high level pipeline APIs. Now, lower level optimization primitives point to algorithms of features that help you convert probably string data to numeric data. Like if you have gender, you might want to encode the gender, say encode male as 1 or 0 and then female as any other number. It could be 2, it could be 0, it could be 10. Then it has high level APIs wherein you will have to just define the steps that you want to be applied on the model, because at the end of the day, we must not forget that Spark works on the model of lazy evaluation. And if we have to try that in machine learning, then even machine learning problems would have to go through a similar model wherein we should have the flexibility or ability to define the steps that need to be applied on the model. And once those steps are ready, we just say start pulling in data and run through these steps. We will see in some of the exercises wherein we will set up a pipeline wherein we will say cleanse data, do this exercise, y activity on data, and then followed by that, run it through this machine learning model. We'll combine all these steps in a pipeline, and then the data flows through this pipeline. So this MLlib is divided into two broad packages: Spark MLlib that contains the original API built on top of RDDs, and Spark ML that provides higher level API that is built on top of data frames for constructing ML pipelines. So we will get familiar with Spark ML, wherein we will prepare data in the form of data frames and run that through Spark ML library. Spark ML also has the recent advancements. Nowadays, more and more models are being added to Spark ML module and not to Spark ML lib. That was the earlier version of the Spark ML. So why do we require ML? First of all, for the reasons of simplicity and compatibility, it provides a simple API that is familiar to data scientists who are more accustomed to using tools like R and Python. Second, it has scalability. It has the ability to run same ML code on your laptop and on a bigger cluster seamlessly without breaking it down. So you could essentially set up a local Spark on your system, test model on your system with a very small data set, improve the model continuously. Then, even before rolling into production, you might set it up on a bigger cluster and see how it performs on bigger data set. And post that, you may finally confirm whether this model is good to be used in production or not. Third, it offers faster processing. So, leveraging the power of a Spark and Hadoop, it has the ability to run programs up to 100 times faster than Hadoop MapReduce in memory or 10 times faster on disk. So, this brings out the benefit of using a machine learning on a Spark. And lastly, the process is streamlined from end to end, wherein we can build a machine learning model on top of a Spark, and that makes it possible to handle different needs with a single tool instead of many disjointed ones. So by single tool, we mean if you were to implement this model that has to run on data in a distributed fashion using multi-processing or multi-threading models, then it would have been very difficult to come up with a model that has the ability to collate inputs from multiple parallel threads. However, Spark overcomes that limitation. So if you think down deeper, how different workers contribute to the training or the learning ability of the model, it's really very complex. But somehow Spark manages it elegantly without us worrying about the internals of the process. So Spark Mlib tools actually comprises several features of the ML library. First of all, we have a bunch of algorithms for supervised and unsupervised learning and recommendations. Then you have featureization tools that help you play with features, transform features, reduce them, increase them. Thirdly, we have the ability to create pipelines wherein we define the steps of the process and then combine them together or join them together using a pipeline to be run over the or defined over the data set. In addition to these, it also has persistence abilities that are generically available in Spark. You will require caching and persistence while building machine learning models because many times you may want to cache the model that is returned by the Spark algorithms. You might want to use that cached version of the learning model to be applied on test dataset or on validation dataset to see how the model actually performs. So this is a very classic use of persistence in the context of machine learning. Lastly, it has utilities for linear algebra, stats, and data handling. Linear algebra and stats are required in cases wherein you might want to build a model of your own and do not want to pick something that is readily available in Spark MLM. So most of the models in machine learning, they do require linear algebra, calculus, and statistics to be used in combination. So this should actually have been a title of ML, but it tries to actually emphasize the fact that we are dealing with ML library in Spark. So it has data types, basic stats that can be performed on dataset. It has classification and regression models that help in supervised learning. It has collaborative filtering, clustering models, dimensionality reduction, feature extraction transformation that we have already learned about, some of the techniques, and optimization. These are for the developer to actually improve the performance of their models and do that using a stochastic gradient descent or the limited memory model. The concepts that we take home as part of this discussion, we will use data frames as Spark ML will, as it takes data frames as input. So you can actually construct a data frame from a Spark SQL and supply that as an input to a machine learning model. So if you try to visualize it, you can have an end-to-end process specified wherein you stream data or you read data from a file, cleanse it, transform it, convert it to a data frame for the purpose of analysis. Once you're done with the analysis using SQLs or data frame related operations, you could come up with a final data frame that can be fed to machine learning. So all these steps that we have seen in the process of building, training, testing a model, all of that can be performed using the combination of techniques that we have learned in Spark. Then it has a transformer. Transformer will be an algorithm that can transform data frame into another data frame. So many times we may want to say that this data frame has 20 columns, but out of these 20 columns, are we going to use all of them? So columns are features in datasets, and we might want to say these are not all the relevant features that we want to use and run them through a process like transformer that has the ability to get rid of features that might not be of importance to the model. Then we have an estimator that is used to assess the accuracy of the model. It is an algorithm which can be fit on DataFrame to produce a transformer. A learning algorithm is an estimator which trains on a DataFrame and produces a model. Then we have a pipeline that chains multiple transformers and estimators together. And finally, we have a parameter wherein all transformers and estimators will now share a common API for specifying parameters. Parameters play a very significant role in machine learning process wherein the entire algorithm can have a significant performance boost based on few changes to parameters, or it may really become so worse that you may not want to use it. So it's all driven by the inputs that are required by the model, and at times these inputs also demand some statistical explanation wherein you might have to dive deeper to understand what that parameter actually means and what is the internal impact of that parameter on the dataset. So typical steps in pipeline would look like this, wherein you will have training data. You might want to featureize the data, come up with feature vectors, that is set of features that you want to use, run that through the training process of the model. You come up with the final model that has trained itself on this data set. You evaluate the model. In this process, you may not only test a single model, but you may at times test multiple models as well to see which one performs better, and then you pick the best model to be applied on a percentage of the training data set for the purpose of testing.
So we'll start with basics of graph. So graphs are basically made up of two sets called vertices and edges. The vertices are drawn from some underlying type, and the set can be finite or infinite. Now each element of the edge set is a pair consisting of two elements from the vertices set. So your vertex is V1, then your vertex is V3, then your vertex is V2 and V4, and your edges are V1 comma V3, then next is V1 comma V2, then you have V2 comma V3, and then you have V2 comma V4. So basically we represent vertices set as closed in curly braces all the name of vertices. So we have V1, we have V2, we have V3, and then we have V4, and we'll close the curly braces. And to represent the edge set, we use curly braces again, and then in curly braces we specify those two vertex which are joined by the edge. So for this edge we will use a V1 comma V3, and then for this edge we'll use V1 comma V2, and then for this edge again we'll use V2 comma V4, and then at last for this edge we'll use V2 comma V3, and at last I'll close the curly braces. So this is your vertices set and this is your edge set. Now one more important thing, that is if a edge set is containing u comma v, or you can say that our edge set is containing v1 comma v3, so v1 is basically adjacent to v3. Similarly, your v1 is adjacent to v2, then v2 is adjacent to v4, and looking at this edge we can say v2 is adjacent to v3. Now let's quickly move ahead and we'll look at different types of graph. So first we have undirected graphs. So basically in an undirected graph, we use straight lines to represent the edges. Now the order of the vertices in the edge set does not matter in undirected graph. So the undirected graph usually are drawn using straight lines between the vertices. Now it is almost similar to the graph which we have seen in the last slide. Similarly, we can again represent the vertices set as 5, 6, 7, 8, and the edge set as 5, 6, then 5, 7. Now talking about directed graphs, so basically in a directed graph, the order of vertices in the edge set matters. So we use arrow to represent the edges, as you can see in the image, as which was not the case with the undirected graph where we were using the straight lines. So in directed graph, we use arrow to denote the edges. And the important thing is the edge set should be similar. It will contain the source vertex, that is 5 in this case, and the destination vertex, which is 6 in this case. And this is never similar to 6 comma 5. You cannot represent this edge as 6 comma 5 because the direction always matters in the directed graph. Similarly, you can say that 5 is adjacent to 6, but you cannot say that 6 is adjacent to 5. So for this graph, the vertices set would be similar as 5, 6, 7, 8, which was similar in undirected graph. But in directed graph, your edge set should be your first tuple, this one will be 5, 6. Then your second edge, which is this one, would be 5, 7. And at last, your this set would be 7, 8. But in case of undirected graph, you can write this edge as 8, 7, or in case of undirected graph, you can write this one as 7, 5. But this is not the case with your directed graph. You have to follow the source vertex and the destination vertex to represent the edge. So I hope you guys are clear with the undirected and directed graph. Now let's talk about vertex labeled graph. Now in a vertex labeled graph, each vertex is labeled with some data in addition to the data that identifies the vertex. So basically, we say this 6 or this 5 as the vertex ID. So there will be data that would be added to this vertex. So let's say this vertex would be 6 comma, and then we are adding the color. So it would be purple. Next, this vertex would be 8 comma, and the color would be green. Next, we will say this as 7 comma red, and then this one is as 5 comma blue. Now, this 6 or this 5 or 7 or 8, these are vertex ID, and the additional data which is attached is the color like blue, purple, green or red. But only the identifying data is present in the pair of edges, or you can say only the ID of the vertex is present in the edge set. So here the edge set is again similar to your directed graph. That is your source ID, this which is 5, and then destination ID, which is 6 in this case. Then for this case, it's similar as 5 comma 7. Then for this case, it's similar as 7 comma 8. So we are not specifying this additional data which is attached to the vertices, that is the color. We only specify the identifiers of the vertex, that is the number. But your vertex set would be something like this vertex would be 5 comma blue, then your next vertex will become 6 comma purple, then your next vertex will become 8 comma green, and at last your last vertex will be written as 7 comma red. So basically, when you are specifying the vertices set in the vertex label graph, you attach the additional information in the vertices set. But while representing the edge set, it is represented similarly as directed graph, where you have to just specify the source vertex identifier, and then you have to specify the destination vertex identifier. Now I hope that you guys are clear with undirected, directed and vertex labeled graph. So let's quickly move forward. Next, we have cyclic graph. So a cyclic graph is a directed graph with at least one cycle. And the cycle is the path along with the directed edges from a vertex to itself. So once you see over here, you can see that from this vertex 5, it's moving to vertex 7, then it's moving to vertex 8, then with arrow it's moving to vertex 6, and then again it's moving to vertex 5. So there should be at least one cycle in a cyclic graph. There might be a new component, let's say vertex 9, which is attached over here. Again, so it would be a cyclic graph because it has one complete cycle over here. And the important thing to notice is that the arrows should make the cycle, like from 5 to 7, and then from 7 to 8, and then 8 to 6, and 6 to 5. And let's say that there is an arrow from 5 to 6, and then there is an arrow from 6 to 8. So we have flipped the arrows. So in that situation, this is not a cyclic graph because the arrows are not completing the cycle. So once you move from 5 to 7 and then from 7 to 8, you cannot move from 8 to 6. And similarly, once you move from 5 to 6 and then 6 to 8, you cannot move from 8 to 7. So in that situation, it's not a cyclic graph. So let's clear all this thing. So we'll represent this cycle as 5, Then using double arrows, we'll go to 7, and then we'll move to 8, and then we'll move to 6, and at last we'll come back to 5. Now we have edge label graph. So basically, a edge label graph is a graph where the edges are associated with labels. So one can basically indicate this by making the edge set as be a set of triplets. So for example, let's say this edge in this edge label graph will be denoted as the source, which is 6, then the destination, which is 7, and then the label of the edge, which is blue. So this edge would be defined something like 6, 7, blue. And then for this edge, similarly, the source vertex, that is 7, the destination vertex, which is 8, then the label of the edge, which is white. Next, similarly for this edge, it's 5, 7, and then blue, red. And at last for this edge, it's 5, 6, and then it would be yellow, green, which is the label of the edge. So all these 4 edges will become the edge set for this graph, and the vertices set is almost similar, that is 5, 6, 7, 8. Now to generalize this, I would say x, y. So x here is the source vertex, then y here is the destination vertex, and then a here is the label of the edge. Then edge label graph are usually drawn with the labels written adjacent to the arcs specifying the edges. As you can see, we have mentioned blue, white, and all those label adjacent to the edges. So I hope you guys are clear with the edge label graph, which is nothing but labels attached to each and every edge. Now let's talk about weighted graph. So a weighted graph is an edge labeled graph basically, where the labels can be operated on by usually arithmetic operators or comparison operators like less than or greater than symbol. Usually these are integers or floats, and the idea is that some edges may be more expensive, and this cost is represented by the edge labels or weights. Now in short, weighted graphs are a special kind of edge labeled graphs where your edge is attached to a weight, generally which is a integer or a float, so that we can perform some addition or subtraction or different kind of arithmetic operations, or it can be some kind of conditional operations like less than or greater than. So we'll again represent this edge as 5, 6, and then the weight as 3. And similarly, we'll represent this edge as 6, 7, and the weight is again 6. So similarly, we'll represent these two edges as well. So I hope that you guys are clear with the weighted graphs. Now let's quickly move ahead and look at this directed acyclic graph. So this is a directed acyclic graph, which is basically without cycles. So as we just discussed in cyclic graphs, here you can see that it is not completing the graph from the directions, or you can say the direction of the edges, right? We can move from 5 to 7, then 7 to 8, but we cannot move from 8 to 6. And similarly, we can move from 5 to 6, then 6 to 8, but we cannot move from 8 to 7. So this is not forming a cycle, and these kind of graphs are known as directed acyclic graph. Now they appear as special cases in CS application all the time, and the vertices set and the edge set are represented similarly as we have seen earlier. Now talking about the disconnected graph, so vertices in a graph do not need to be connected to other vertices. It is basically legal for a graph to have disconnected components or even lone vertices without a single connection. So basically this disconnected graph which has 4 vertices but no edges. Now let me tell you something important, that is what are sources and sinks. So let's say we have one arrow from 5 to 6 and one arrow from 5 to 7. Now vertices with only in arrows are called sink. So the 7 and 6 are known as sinks, and the vertices with only out arrows are called sources. So as you can see in the image, this 5 only have out arrows to 6 and 7. So these are called sources. Now we'll talk about this in a while, guys, once we are going through the PageRank algorithm. So I hope that you guys know what are vertices, what are edges, how vertices and edges represents the graph, then what are different kinds of graph. So I hope you guys are clear with all of these concepts. Saurav says all clear. Sumit says yes. Okay, thanks for the confirmation, guys. Let's move to the next topic. So next, let's know what is Spark GraphX. So talking about GraphX, GraphX is a new component in Spark for graphs and graph parallel computation. Now at a high level, GraphX extends the Spark RDD by introducing a new graph abstraction, that is a directed multigraph, that is properties attached to each vertex and edge. Now to support graph computation, GraphX basically exposes a set of fundamental operators like finding subgraph or joining vertices or aggregating messages, as well as it also exposes an optimized variant of the Pregel API. In addition, GraphX also provides you a collection of graph algorithms and builders to simplify your Spark analytics task. So basically, your GraphX is extending your Spark RDD, then your GraphX is providing an abstraction, that is a directed multigraph with properties attached to each vertex and edge. So we'll look at this property graph in a while. Then again, GraphX gives you some fundamental operators, and then it also provides you some graph algorithms and builders, which makes your analytics easier. Now, to get started, you first need to import Spark and GraphX into your project. So as you can see, we are importing first Spark and then we are importing Spark GraphX to get those GraphX functionalities. And at last, we are importing Spark RDD to use those RDD functionalities in our program. But let me tell you that if you are not using Spark Shell, then you will need a Spark context in your program. So I hope that you guys are clear with the features of GraphX and the libraries which you need to import in order to use GraphX. So let us quickly move ahead and look at the property graph. Now, property graph is something, as the name suggests, property graph have properties attached to each vertex and edge. So the property graph is a directed multigraph with user-defined objects attached to each vertex and edge. Now you might be wondering what is a directed multigraph. So a directed multigraph is a directed graph with potentially multiple parallel edges sharing the same source and same destination vertex. So as you can see in the image that from San Francisco to Los Angeles, we have two edges, and similarly from Los Angeles to Chicago, there are two edges. So basically in a directed multigraph, the first thing is the directed graph. So it should have a direction attached to the edges. And then talking about multigraph, so between a source vertex and a destination vertex, there could be two edges. So the ability to support parallel edges basically simplifies the modeling scenarios where there can be multiple relationships between the same vertices. For an example, let's say these are two persons, so they can be friends as well as they can be co-workers, right? So these kind of scenarios can be easily modeled using directed multigraph. Now each vertex is keyed by a unique 64-bit long identifier, which is basically the vertex ID, and it helps in indexing. So each of your vertex contains a vertex ID, which is a unique 64-bit long identifier. And similarly, edges have corresponding source and destination vertex identifiers. So this edge would have this vertex identifier as well as this vertex identifier, or you can say a source vertex ID and the destination vertex ID. So as we discussed, this property graph is basically parameterized over the vertex and edge types. And these are the types of object associated with each vertex and edge. So your GraphX basically optimizes the representation of vertex and edge types, and it reduces the in-memory footprint by storing the primitive data types in a specialized array. Now, in some cases, it might be desirable to have vertices with different property types in the same graph. Now, this can be accomplished through inheritance. So, for an example, to model a user and product in a bipartite graph, or you can see that we have user property and we have product property. Okay, so let me first tell you what is a bipartite graph. So a bipartite graph is also called a bigraph, which is a set of graph vertices decomposed into two disjoint sets such that no two graph vertices within the same set are adjacent. So as you can see over here, we have user property and then we have product property, but no two user property can be adjacent, or you can say there should be no edges that is joining any of the two user property, or there should be no edge that should be joining product property. So in this scenario, we use inheritance. So as you can see here, we have class Vertex property. Now basically what we are doing, we are creating another class with user property, and here we have name, which is again a string, and we are extending, or you can say we are inheriting the Vertex property class. Now again, in the case of product property, we have name, that is name of the product, which is again string, and then we have price of the product, which is double, and we are again extending this Vertex property graph. And at last, we are creating a graph with this Vertex property and then string. So this is how we can basically model user and product as a bipartite graph. So we have created user property as well as we have created this product property, and we are extending this Vertex property class. Now talking about this property graph, it's similar to your RDD. So like your RDD, property graph are immutable, distributed and fault tolerant. So changes to the values or structure of the graph are basically accomplished by producing a new graph with the desired changes, and the substantial part of the original graph, which can be your structure of the graph or attributes or indices, these are basically reused in the new graph, reducing the cost of inherent functional data structure. So basically your property graph, once you're trying to change values or structure, so it creates a new graph with a changed structure or changed values, and your substantial part of original graph are reused multiple times to improve the performance, and it can be your structure of the graph which is getting reused, or it can be your attributes or indices of the graph which is getting reused. So this is how your property graph provides efficiency. Now the graph is partitioned across the executors using a range of vertex partitioning rules, which are basically loosely defined, and similar to RDD, each partition of the graph can be recreated on different machines in the event of failure. So this is how your property graph provides fault tolerance. So as we already discussed, logically the property graph corresponds to a pair of typed collections encoding the properties for each vertex and edge. And as a consequence, the graph class contains members to access the vertices and the edges. So as you can see, we have graph class, then you can see we have vertices and we have edges. Now this vertex RDD VD is extending your RDD, which is your RDD and then your vertex ID and then your vertex property. Similarly, your edge RDD is extending your RDD with your edge property. So the classes, that is vertex RDD and edge RDD, extends and are optimized version of your RDD, which includes vertex ID and vertex property, and your RDD, which includes your edge property. And both this vertex RDD and edge RDD provides additional functionality built on top of graph computation and leverages internal optimizations as well. So this is the reason we use this vertex RDD or edge RDD, because it already extends your RDD containing your vertex ID and vertex property or your edge property. It also provides you additional functionalities built on top of graph computation. And again, it gives you some internal optimizations as well. Now let me clear this and let's take an example of property graph where the vertex property might contain the username and occupation. So as you can see in this table that we have ID of the vertex and then we have property attached to each vertex, that is the username as well as the occupation of the user, or you can say the profession of the user. And we can annotate the edges with the string describing the relationship between the users. So as you can see, first is Thomas, who is a professor, then second is Frank, who is also a professor. Then as you can see, third is Jenny, she's a student, and fourth is Bob, who is a doctor. Now Thomas is a colleague of Frank. Then you can see that Thomas is an academic advisor of Jenny. Again, Frank is also academic advisor of Jenny. And then the doctor is the health advisor of Jenny. So the resulting graph would have a signature of something like this. So I'll explain this in a while. So there are numerous ways to construct a property graph, from raw files or RDDs or even synthetic generators. and we'll discuss it in graph builders. But the very probable and most general method is to use graph object. So let's take a look at the code first. So first over here, we are assuming that Spark context has already been constructed. Then we are giving the SCS Spark context. Next, we are creating an RDD for the vertices. So as you can see, for users, we have specified IDD and then Vertex ID. And then these are two strings. So first one would be your username and the second one would be your profession. Then we are using SC parallelize and we are creating an array where we are specifying all the vertices. So 1L, that is this one, and we are giving the name as Thomas and the profession is professor. Similarly for 2L, Frank, professor, then 3L, Jenny, she is student, then 4L, Bob, doctor. So here we have created the vertex. Next, we are creating an RDD for edges. So first we are giving the value as relationship, then we are creating an RDD with edge string, and then we are using SC parallelize to create the edge. And in the array, we are specifying the source vertex, then we are specifying the destination vertex, and then we are giving the relation, that is colleague. Similarly for next edge, the source is 1, then the destination is 1, and then the profession is academic advisor. And then it goes so on. So in this line, we are defining a default user in case there is a relationship between missing users. Now we have given the name as default user and the profession is missing. Next, we are trying to build the initial graph. So for that, we are using this graph object. So we have specified users, that is your vertices. Then we are specifying the relations, that is your edges. And then we are giving the default user, which is basically for any missing user. So now as you can see over here, we are using edge case class, and edges have a source ID and a destination ID, which is basically corresponding to your source and destination vertex. And in addition to the edge class, we have an attribute member which stores the edge property, which is the relation over here, that is colleague, or it is academic advisor, or it is health advisor, and so on. So I hope that you guys are clear about creating a property graph, how to specify the vertices, how to specify edges, and then how to create a graph. Okay, thanks for the confirmation. Now we can deconstruct a graph into respective vertex and edge views by using a graph.vertices and graph.edges members. So as you can see, we are using graph.vertices over here and graph.edges over here. Now what we are trying to do, so first over here, the graph which we have created earlier, so we have graph.vertices.filter. Now using this case class, we have this vertex ID, we have the name, and then we have the position, and we are specifying the position as doctor. So first we are trying to filter the profession of the user as doctor, and then we are trying to count it. Next, we are specifying graph.edges.filter, and we are basically trying to filter the edges where the source ID is greater than your destination ID, and then we are trying to count those edges. We are using a Scala case expression, as you can see, to deconstruct the tuple, or you can say to deconstruct the result. On the other hand, graph.edges returns a edge RDD, which is containing edge string object. So we could also have used the case class type constructor, as you can see here. So again, over here we are using graph.edge.filter, and over here we have given case edge, and then we are specifying the property, that is source, destination, and then property of the edge which is attached, and then we are filtering it, and then we are trying to count it. So this is how using edge class, either you can see with edges or you can see with vertices, this is how you can go ahead and deconstruct them, right? Because your graph.vertices or your edge.vertices returns a vertex RDD or a edge RDD. So to deconstruct them, we basically use this case class. So I hope you guys are clear about transforming property graph and how to use this case class to deconstruct the vertex RDD or edge RDD. Okay, so now let's quickly move ahead. Now, in addition to the vertex and edge views of the property graph, GraphX also exposes a triplet view. Now you might be wondering, what is a triplet view? So the triplet view logically joins the vertex and edge properties, yielding an RDD edge triplet with vertex property and your edge property. So as you can see, it gives an RDD with edge triplet, and then it has vertex property as well as edge property associated with it, and it contains an instance of edge triplet class. Now I'm taking an example of a join. So in this join, we are trying to select source ID, destination ID, source attribute, then this is your edge attribute, and then at last you have destination attribute. So basically your edges has alias E, then your vertices has alias as source, and again your vertices has alias as destination. So we are trying to select source ID, destination ID, then source attribute and destination attribute, and we are also selecting the edge attribute, and we are performing left join. The edge source ID should be equal to source ID and the edge destination ID should be equal to destination ID. And now your edge triplet class basically extends your edge class by adding your source attribute and destination attribute members, which contains the source and destination properties. And we can use the triplet view of a graph to render a collection of strings describing relationship between users. So this is vertex 1, which is again denoting your user 1, that is Thomas, and who is a professor. And this is vertex 3, which is denoting your Jenny, and she is a student. And this is your edge, which is defining the relationship between them. So this is a edge triplet, which is denoting the both vertex as well as the edge, which denote the relation between them. So now looking at this code, first we have already created the graph. Then we are taking this graph, we are finding the triplets, and then we are mapping each triplet. We are trying to find out the triplet dot source attribute, in which we are picking up the username. Then over here we are trying to pick up the triplet attribute, which is nothing but the edge attribute, which is your academic advisor. Then we are trying to pick up the triplet destination attribute. It will again pick up the username of destination attribute, which is username of this vertex 3. So for an example, in this situation, it will print Thomas is the academic advisor of Jenny. So then we are trying to take this facts, we are collecting the facts using this for each, we are printing each of the triplet that is present in this graph. So I hope that you guys are clear with the concepts of triplet. So now let's quickly take a look at graph builders. So as I already told you that GraphX provides several ways of building a graph from a collection of vertices and edges. Either it can be stored in RDD or it can be stored on disks. So in this graph object, first we have this apply method. So basically this apply method allows creating a graph from RDD of vertices and edges, and duplicate vertices are picked up arbitrarily, and the vertices which are found in the edge RDD and are not present in the vertices RDD are assigned the default attribute. So in this apply method, first we are providing the vertex RDD, then we are providing the edge RDD, and then we are providing the default vertex attribute. So it will create the vertex which we have specified, then it will create the edges which are specified, and if there is a vertex which is being referred by the edge but it is not present in this vertex RDD, so what it does, it creates that vertex and assigns them the value of this default vertex attribute. Next we have from edges. So graph.from edges allows creating a graph only from the RDD of edges, which automatically creates any vertices mentioned in the edges and assigns them the default value. So what happens over here, you provide the edge RDD and all the vertices that are present in the edge RDD are automatically created and the default value is assigned to each of those vertices. So graph.from edges tuples basically allows creating a graph from only the RDD of edge tuples, and it assigns the edges as value 1, and again the vertices which are specified by the edges are automatically created and the default value which we are specifying over here will be allocated to them. So basically your from edge tuple supports deduplicating of edges, which means you can remove the duplicate edges. But for that, you have to provide a partition strategy in the unique edges parameter, as it is necessary to co-locate the identical edges on the same partition. Duplicate edges can be removed. So moving ahead, none of the graph builders repartitions the graph edges by default. Instead, edges are left in their default partitions. So as you can see, we have a graph loader object, which is basically used to load the graph from the file system. So graph.groupEdges requires the graph to be repartitioned because it assumes that identical edges will be co-located on the same partition. And so you must call graph.partitionBy before calling group edges. So now you can see the edge list file method over here, which provides a way to load a graph from the list of edges which is present on the disk, and it parses the adjacency list, that is your source vertex ID and the destination vertex ID pairs, and it creates a graph. So now for an example, let's say we have 2 and 1, which is one edge. Then you have 4, 1, which is another edge, and then you have 1, 2, which is another edge. So it will load these edges and then it will create the graph. So it will create 2, then it will create 4, and then it will create 1. And for 2, 1, it will create the edge, and then 4, 1, it will create the edge, and at last it will create an edge for 1 and 2. So it will create a graph something like this. It creates a graph from specified edges where automatically vertices are created which are mentioned by the edges, and all the vertex and edge attribute are set by default 1, and as well as 1 will be associated with all the vertices. So it would be 4, 1, then again for this it would be 1, 1, and similarly it would be 2, 1 for this vertex. Now let's go back to the code. So then we have this canonical orientation. So this argument allows reorienting edges in the positive direction, that is from the lower source ID to the higher destination ID. Now, which is basically required by your connected components algorithm. We'll talk about this algorithm in a while, guys. But before this basically helps in reorienting your edges, which means your source vertex should always be less than your destination vertex. So in that situation, it might reorient this edge. So it will reorient this edge and basically it will reverse the direction of the edge. Similarly over here, so with the vertex which is coming from 2 to 1 will be reoriented and will be again reversed. Now then, talking about the minimum edge partition, this minimum edge partition basically specifies the minimum number of edge partitions to generate, but there might be more edge partitions than specified. So let's say the HDFS file has more blocks, so obviously more partitions will be created, but this will give you the minimum edge partitions that should be created. So I hope that you guys are clear with this graph loader, how this graph loader works, how we can go ahead and provide the edge list file and how it will create the graph from this edge list file. And then this canonical orientation where we are again going and reorienting the graph. And then we have minimum edge partition, which is giving the minimum number of edge partitions that should be created. So now I guess you guys are clear with the graph builder. So how to go ahead and use this graph object and how to create graph using apply from edges and from edge tuples method. And then I guess you might be clear with the graph loader object and where you can go ahead and create a graph from edge list. Now let's move ahead and talk about vertex and edge RDD. So as I already told you that GraphX exposes RDD views of the vertices and edges stored within the graph. And however, because GraphX again maintains the vertices and edges in optimized data structure, and these data structure provide additional functionalities as well. Now let us see some of the additional functionalities which are provided by them. So let's first talk about Vertex RDD. So I already told you that Vertex RDD is basically extending this RDD with Vertex ID and the Vertex property, and it adds an additional constraint that each Vertex ID occurs only once. Now, moreover, a Vertex RDD A represents a set of vertices, each with an attribute of type A. Now, internally, what happens, this is achieved by storing the vertex attribute in an reusable hash map data structure. So suppose this is our hash map data structure. So suppose if two vertex RDD are derived from the same base vertex RDD. Suppose these are two vertex RDD which are basically derived from this vertex RDD. So they can be joined in constant time without hash evaluations. So you don't have to go ahead and evaluate the properties of both the vertices. You can easily go ahead and you can join them without the evaluations. And this is one of the way in which this vertex RDD provides you the optimization. Now to leverage this indexed data structure, the vertex RDD exposes multiple additional functionalities. So it gives you all these functions, as you can see here. It gives you filter, map values, then minus, difference, left join, inner join, and aggregate using index functions. So let us first discuss about these functions. So basically, a filter function filters the vertex set but preserves the internal index. So based on some condition, it filters the vertices that are present. Then in map values, it is basically used to transform the values without changing the IDs, and which again preserves your internal index. So it does not change the ID of the vertices, and it helps in transforming those values. Now talking about the minus method, it shows only vertices unique in the set based on their vertex IDs. So what happens if you are providing two set of vertices? First contains v1, v2 and v3, and second one contains v3. So it will return v1 and v2 because they are unique in both the sets, and it is basically done with the help of vertex ID. So next we have diff function. So it basically removes the vertices from this set that appears in another set. Then we have left join and inner join. So join operators basically take advantage of the internal indexing to accelerate join. So you can go ahead and you can perform left join or you can perform inner join. Next, you have aggregate using index. So basically, this aggregate using index is nothing but reduce by key, but it uses index on this RDD to accelerate the reduce by key function, or you can say reduce by key operation. So again, filter is actually implemented using bit set and thereby reusing the index and preserving the ability to do fast joins with other vertex RDD. Now, similarly, the map values operator as well do not allow the map function to change the vertex ID. And this again helps in reusing the same hash map data structure. Now, both of your left join as well as your inner join is able to identify that whether the two vertex RDD which are joining are derived from the same hash map or not. And for this, they basically use linear scan. They again don't have to go ahead and search for costly point lookups. So this is the benefit of using vertex RDD. So to summarize, your vertex RDD uses hash map data structure, which is again reusable. They try to preserve your indexes so that it would be easier to create a new vertex RDD or derive a new vertex RDD from them. Then again, while performing some joining operations, it is pretty much easy to go ahead, perform a linear scan, and then you can go ahead and join those two vertex RDD. So it actually helps in optimizing your performance. Now moving ahead, let's talk about Edge RDD. Now again, as you can see, your Edge RDD is extending your RDD with property Edge. Now it organizes the edge in block partition using one of the various partitioning strategies, which is again defined in your partition strategies attribute, or you can say partition strategy parameter. Within each partition, each attribute and adjacency structure are stored separately, which enables the maximum reuse when changing the attribute values. So basically what it does, while storing your edge attributes and your source vertex and destination vertex, they are stored separately, so that changing the values of the attributes either of the source vertex or destination vertex or edge attribute, so that it can be reused as many times as we need by changing the attribute values itself, so that once the vertex ID is changed of an edge, it could be easily changed and the earlier part can be reused. Now, as you can see, we have three additional functions over here, that is map values, reverse and inner join. So in Edge RDD, basically map values is to transform the edge attributes while preserving the structure. It is helpful in transforming, so you can use map values and map the values of your Edge RDD. Then you can go ahead and use this reverse function, which reverses the edge reusing both attribute and structure. So the source becomes destination and the destination becomes source. Now talking about this inner join, so it basically joins two edge RDDs partitioned using the same partitioning strategy. Now, as we already discussed, that same partition strategy is required because again, to co-locate, you need to use same partition strategy, and your identical vertex should reside in same partition to perform join operation over them. Now, let me quickly give you an idea about optimization performed in this GraphX. So GraphX basically adopts a vertex cut approach to distribute graph partitioning. So suppose you have 5 vertex and then they are connected. Let's not worry about the arrows right now, or let's not worry about the direction right now. So either it can be divided from the edges, which is one approach, or again it can be divided from the vertex. So in that situation it would be divided something like this. So rather than splitting graphs along edges, GraphX partitions the graph along vertices, which can again reduce the communication and storage overhead. So logically, what happens that your edges are assigned to machines and allowing your vertices to span multiple machines. So your vertices is basically divided into multiple machines and your edges is assigned to a single machine, right? Then the exact method of assigning edges depends on the partition strategy. So the partition strategy is the one which basically decides how to assign the edges to different machines, or you can say different partitions. So user can choose between different strategies by partitioning the graph with the help of this graph.partition by operator. Now, as we discussed that this graph.partition by operator repartitions and then it divides or reallocates the edges, and basically we try to put the identical edges on a single partition so that different operations like join can be performed on them. So once the edges have been partitioned, the main challenge is efficiently joining the vertex attributes with the edges, right? Now, because real world graphs typically have more edges than vertices, so we move vertex attributes to the edges. And because not all the partitions will contain edges adjacent to all vertices, we internally maintain a routing table. So the routing table is the one who will broadcast the vertices and then will implement the join required for the operations. So I hope that you guys are clear how vertex RDD and edge RDD works, and then how the optimizations take place and how vertex cut optimizes the operations in GraphX. Okay, Frank says yes. Saurav says all clear. Okay, thanks for the confirmation, guys. Let's quickly move ahead. Now let's talk about graph operators. So just as RDD have basic operations like map, filter, reduce by key, property graph also have collection of basic operators that take user-defined functions and produce new graphs with transform properties and structure. Now the core operators that have optimized implementation are basically defined in graph class, and convenient operators that are expressed as a composition of the core operators are basically defined in your GraphOps class. But in Scala, it implicits the operators in GraphOps class. They are automatically available as a member of graph class. So you can use them using the graph class as well. Now, as you can see, we have a list of operators like property operator, then you have structural operator, then you have join operator, and then you have something called neighborhood operator. So let's talk about them one by one. Now talking about property operators, like RDD has map operator, the property graph contains map vertices, map edges, and map triplets operators, right? Now each of this operator basically yields a new graph with the vertex or edge property modified by the user-defined map function. Based on the user-defined map function, it basically transforms or modifies the vertices if it's map vertices, or it transform or modify the edges if it is map edges method or map edges operator, and so on for map triplets as well. Now the important thing to note is that in each case the graph structure is unaffected, and this is a key feature of these operators basically, which allows the resulting graph to reuse the structural indices of the original graph. Each and every time you apply a transformation, so it creates a new graph and the original graph is unaffected, so that it can be used So you can say it can be reused in creating new graphs, right? So your structural indices can be used from the original graph. Now talking about this map vertices, let me use the highlighter. So first we have map vertices. So it maps the vertices, or you can say transform the vertices. So you provide vertex ID and then vertex property, and you apply some of the transformation function using which, so it will give you a graph with new vertex property, as you can see. Now same is the case with map edges. So again you provide the edges, then you transform the edges. So initially it was ed and then you transform it to ed2, and then the graph which is given, or you can say the graph which is returned, is the graph with a changed edge attribute. So you can see here the attribute is ed2. Same is the case with map triplets. So using map triplets, you can use the edge triplet, where you can go ahead and target the vertex properties, or you can say vertex attributes, or to be more specific, source vertex attribute as well as destination vertex attribute and the edge attribute. And then you can apply transformation over those source attributes or destination attributes or the edge attributes. So you can change them, and then it will again return a graph with the transformed values. Now I guess you guys are clear with the property operators. So let's move to the next operator, that is structural operator. So currently GraphX supports only a simple set of commonly used structural operators, and we expect more to be added in future. Now you can see in structural operator we have reverse operator, then we have subgraph operator, then we have mask operator, and then we have group edges operator. So let's talk about them one by one. So first, reverse operator. So as the name suggests, it returns a new graph with all the edge directions reversed. So basically it will change your source vertex into destination vertex, and then it will change your destination vertex into source vertex. So it will reverse the direction of your edges, and the reverse operation does not modify vertex or edge properties or change the number of edges. It can be implemented efficiently without data movement or duplication. So next we have subgraph operator. So basically subgraph operator takes the vertex and edge predicates, or you can say vertex or edge condition, and returns the graph containing only the vertex that satisfy those vertex predicates, and then it returns the edges that satisfy the edge predicates. So basically you will give a condition about edges and vertices, and those predicates which are fulfilled, or those vertex which are fulfilling the predicates, will be only returned. And again same is the case with your edges, and then your graph will be connected. Now the subgraph operator can be used in a number of situations to restrict the graph to the vertices and edges of interest and eliminate the rest of the components, right? So as you can see, this is the edge predicate, this is the vertex predicate, then we are providing the edge triplet with the vertex and edge attributes, and we are waiting for the boolean value. Then same is the case with vertex. We're providing the vertex properties over here, or you can say vertex attribute over here, and then again it will yield a graph which is a subgraph of the original graph, which will fulfill those predicates. Now the next operator is mask operator. So mask operator construct a subgraph by returning a graph that contains the vertices and edges that are also found in the input graph. Basically you can treat this mask operator as a comparison between two graphs. So suppose we are comparing graph 1 and graph 2, and it will return the subgraph which is common in both the graphs. Again, this can be used in conjunction with the subgraph operator, basically to restrict a graph based on properties in another related graph, right? So I guess you guys are clear with the mask operator. So over here we're providing a graph, and then we are providing the input graph as well, and then it will return a graph which is basically a subset of both of these graphs. Now talking about group edges, so the group edges operator merges the parallel edges in the multigraph, right? So what it does, the duplicate edges between pair of vertices are merged, or you can say can be aggregated or perform some action. And in many numerical application, parallel edges can be added and their weights can be combined into a single edge, right? Which will again reduce the size of the graph. So for an example, you have two vertex v1 and v2, and there are two edges with weight 10 and 15. So actually what you can do, you can merge those two edges if they have same direction, and you can represent the weight with 25. So this will actually reduce the size of the graph. Now looking at the next operator, which is join operator. So in many cases, it is necessary to join data from external collection with graphs, right? For example, we might have an extra user property that we want to merge with the existing graph, or we might want to pull vertex property from one graph to another, right? So these are some of the situations where you go ahead and use these join operators. So now, as you can see over here, the first operator is join vertices. So the join vertices operator joins the vertices with the input RDD and returns a new graph with the vertex properties obtained after applying the user defined map function. Now the vertices without a matching value in the RDD basically retains their original value. Now talking about outer join vertices, so it behaves similar to join vertices except that the user defined map function is applied to all the vertices and can change the vertex property type. So suppose that you have a old graph which has a vertex attribute as old price, and then you created a new graph from it, and then it has the vertex attribute as new price. So you can go ahead and join two of these graphs, and you can perform an aggregation of both the old and new prices in the new graph. So in this kind of situation, join vertices are used. Now moving ahead, let's talk about neighborhood aggregation. Now key step in many graph analytics is aggregating the information about the neighborhood of each vertex. For an example, we might want to know the number of followers each user has, or the average age of the follower of each user. Now many iterative graph algorithms like PageRank, shortest path, then connected components repeatedly aggregate the properties of neighboring vertices. Now it has four operators in neighborhood aggregation. So the first one is your aggregate messages. So the core aggregation operation in GraphX is aggregate messages. Now this operator applies a user defined send message function, as you can see over here, to each of the edge triplet in the graph, and then it uses merge message function to aggregate those messages at the destination vertex. Now the user defined send message function takes an edge context, as you can see, and which exposes the source and destination attributes along with the edge attribute, and functions like send to source or send to destination is used to send messages to source and destination attributes. Now you can think of send message as the map function in MapReduce, and the user defined merge function which actually takes the two messages which are present on the same vertex, or you can say the same destination vertex, and it again combines or aggregates those messages and produces a single message. Now you can think of the merge message as reduce function in the MapReduce. Now the aggregate messages operator returns a vertex RDD. Basically, it contains the aggregated messages at each of the destination vertex, and vertices that did not receive a message are not included in the returned vertex RDD. So only those vertex are returned which actually have received the message, and then those messages have been merged. If any vertex which haven't received the message will not be included in the returned RDD, or you can say a returned vertex RDD. Now in addition, as you can see, we have a triplet fields. So aggregate messages takes an optional triplet fields which indicates what data is accessed in the edge content. So the possible options for the triplet fields are defined in triplet fields. The default value of triplet fields is triplet fields.all, as you can see over here. This basically indicates that user defined send message function may access any of the fields in the edge content. So this triplet field argument can be used to notify GraphX that only these part of the edge content will be needed, which basically allows GraphX to select the optimized joining strategy. So I hope that you guys are clear with the aggregate messages. Let's quickly move ahead and look at the second operator. So the second operator is MapReduce triplet transition. Now in earlier versions of GraphX, neighborhood aggregation was accomplished using the MapReduce triplets operator. This MapReduce triplet operator is used in older versions of GraphX. This operator takes the user-defined map function which is applied to each triplet and can yield messages which are aggregating using the user-defined reduce functions. This one is the user-defined map function, and this one is your user-defined reduce function. So it basically applies the map function to all the triplets, and then they aggregate those messages using this user defined reduce function. Now the newer version of this map reduce triplets operator is the aggregate messages. Now moving ahead, let's talk about computing degree information operator. So one of the common aggregation tasks is computing the degree of each vertex, that is the number of edges adjacent to each vertex. Now in the context of directed graph, it is often necessary to know the in degree, out degree, then the total degree of vertex. These kind of things are pretty much important, and the graph ops class contain a collection of operators to compute the degrees of each vertex. So as you can see, we have maximum input degree, then maximum output degree, then maximum degrees. Maximum in degree will tell us the number of maximum incoming edges. Then max out degree will tell us maximum number of output edges. And this max degree will actually tell us the number of input as well as output edges. Now moving ahead to next operator, that is collecting neighbors. In some cases, it may be easier to express the computation by collecting neighboring vertices and their attribute at each vertex. Now, this can be easily accomplished using the collect neighbors ID and the collect neighbors operator. So basically, your collect neighbor ID takes the edge direction as the parameter, and it returns a vertex RDD that contains the array of vertex ID that is neighboring to the particular vertex. Now similarly, the collection neighbors again takes the edge directions as the input, and it will return you the array with the vertex ID and the vertex attribute both. Now let me quickly open my VM and let us go through the Spark directory first. Let me first open my terminal. So first I'll start the Hadoop daemons. So for that I'll go to Hadoop home directory. Then inside sbin I have start all.sh script file. So let me check if the Hadoop daemons are running or not. So as you can see that name node, data node, secondary name node, the node manager and resource manager, all the daemons of Hadoop are up. Now I'll navigate to Spark home. Let me first start the Spark daemons. Now as the Spark daemons are running, I'll first minimize this and let me take you to the Spark home. And this is my Spark directory, so I'll go inside. Now let me first show you the data which is by default present with your Spark. So we'll open this in a new tab. So you can see we have two files in this GraphX data directory. Meanwhile, let me take you to the example codes. So this is example, and inside source, main, Scala, you can find the GraphX directory, and inside this GraphX directory, you have some of the sample codes which are present over here. So I'll take you to this aggregate messages example.scala. Now, meanwhile, let me open the data as well, so you'll be able to understand. Now, this is followers.txt file. So basically, you can imagine these are the edges which are representing the vertex. So this is vertex 2 and this is vertex 1, then this is vertex 4 and this is vertex 1, and similarly so on. These are representing those vertex. And if you can remember, I have already told you that inside graph loader class, there is a function called edge list file, which takes the edges from a file and then it constructs the graph based on that. Now, second, you have this user.txt. So these are basically the edges with the vertex ID. So vertex ID for this vertex is 1, then for this is 2, and so on. And then this is the data which is attached, or you can say the attribute of the edges. So these are the vertex ID, which is 1, 2, 3 respectively, and this is the data which is associated with your each vertex. So this is username and this might be the name of your user, and so on. Now you can also see that in some of the cases the name of the user is missing. So as in this case, the name of the user is missing. These are the vertices, or you can say the vertex ID and vertex attributes. Now let me take you through this aggregate messages example. So as you can see, we are giving the name of the package as org Apache Spark examples.graphx. Then we are importing GraphX. In that, we are importing graph class as well as this vertex RDD. Next, we are using this graph generator. I'll tell you why we are using this graph generator. And then we are using the Spark session over here. So this is an example where we are using the aggregate messages operator to compute the average age of the more senior followers of each user. Okay. So this is the object of aggregate messages example. Now this is the main function where we are first initializing the Spark session, then the name of the application. So you have to provide the name of the application, and this is get or create method. Now next you are initializing the Spark context as SC. Now coming to the code, so we are specifying a graph, then this graph is containing double and int. Now I just told you that we are importing graph generator. So this graph generator is to generate a random graph for simplicity. So you would have multiple number of edges and vertices. Then you are using this log normal graph. You are passing the Spark context and you're specifying the number of vertices as 100. So it will generate 100 vertices for you. Then what you're doing, you are specifying the map vertices and you're trying to map ID to double. So what this would do, this will basically map your ID to double. Then in next you are trying to calculate the older followers, where you have given it as Vertex RDD and the input is int and double. So your Vertex RDD has int as your Vertex ID and your data is double, which is associated with each of the vertex, or you can say the vertex attribute. So you have this graph which is basically generated randomly, and then you are performing aggregate messages. So this is the aggregate messages operator. Now if you can remember, we first have the send messages, right? So inside this triplet, we are specifying a function that if the source attribute of the triplet is more than the destination attribute of the triplet, so basically it will return if the follower's age is greater than the age of person whom he is following. This tells the follower's age is greater than the age of whom he is following. So in that situation, it will send message to the destination with vertex containing counter, that is 1, and the age of the source attribute, that is the age of the follower. So first, so you can see the age of the destination is less than the age of source attribute. So it will tell you if the follower is older than the user or not. So in that situation, we'll send 1 to the destination and we'll send the age of the source, or you can say the age of the follower. Then second, I have told you that we have merge messages. So here we are adding the counter and the age in this reduce function. So now what we are doing, we are dividing the total age of the number of older followers to get an average age of older followers. So this is the reason why we have passed the attribute of source vertex. First, we are specifying this variable, that is average age of older followers, and then we are specifying the vertex RDD. So this will be double, and then this older followers, that is the graph which we are picking up from here, and then we are trying to map the value. So in the vertex we have ID and we have value. So in this situation, we are using this case class about count and total age. So what we are doing, we are taking this total age and we are dividing it by count, which we have gathered from this send message, and then we have aggregated using this reduce function. We are again taking the total age of the older followers and then we are trying to divide it by count to get the average age, and at last we are trying to display the result, and then we are stopping this Spark. So let me quickly open the terminal. So I'll go to examples. So inside the examples, I took you through the source directory where the code is present inside Scala, and then inside there is a Spark directory where you will find the code. But to execute the example, you need to go to the jars directory. Now this is the Scala example jar which you need to execute. But before this, let me take you to the HDFS. So the URL is localhost:5070. And we'll go to utilities, then we'll go to browse the file system. So as you can see, I have created a user directory in which I have specified the username, that is Edureka, and inside Edureka I have placed my data directory where we have this GraphX, and inside the GraphX we have both the file, that is followers.txt and users.txt. So in this program, we are not referring to these files, but in coming examples, we'll be referring to these files. So I would request you to first move it to this HDFS directory so that Spark can refer the files in data graphics. Now let me quickly minimize this. And the command to execute is spark-submit. And then I'll pass this jars parameter and I'll provide the Spark example jar. So this is the jar, then I'll specify the class name. So to get the class name, I'll go to the code. I'll first take the package name from here, and then I'll take the class name, which is aggregate messages example. So this is my class, and as I told you, I have to provide the name of the application. So let me keep it as example, and I'll hit enter. So now you can see the result. So this is the followers, and this is the average age of followers. So it is 34, then we have 52, which is the count of follower, and the average age is 76.8. That is, it has 96 senior followers, and then the average age of the followers is 99.0. Then it has 4 senior followers and the average age is 51. Then this vertex has 16 senior followers with the average age of 57.55, and so on. You can see the result over here. So I hope now you guys are clear with aggregate messages, how to use aggregate messages, how to specify the send message, then how to write the merge message. So let's quickly go back to the presentation. Now let us quickly move ahead and look at some of the graph algorithms. So the first one is PageRank. So PageRank measures the importance of each vertex in a graph, assuming that an edge from U to V represents an recommendation or support of V's importance by U. For an example, let's say if a Twitter user is followed by many others, user will obviously rank high. GraphX comes with the static and dynamic implementation of PageRank as methods on PageRank object, and static PageRank runs a fixed number of iterations which can be specified by you, while the dynamic PageRank runs until the ranks converge. What we mean by that is it stops changing by more than a specified tolerance. So it runs until it have optimized the page rank of each of the vertices. Now GraphOps class allows calling these algorithms directly as methods on graph class. Now let's quickly go back to the VM. So this is the page rank example. Let me open this file. So first we are specifying this GraphX package, then we are importing the graph loader. So as you can remember, inside this graph loader class, we have that edge list file operator, which will basically create the graph using the edges. And we have those edges in our followers.txt file. Now coming back to PageRank example, now we're importing the Spark SQL Spark session. Now this is PageRank example object, and inside which we have created a main class, and we have similarly created the Spark session, then builder, then we are specifying the app name which is to be provided. Then we have get or create method. So this is where we are initializing the Spark context. As you can remember, I told you that using this edge list file method, we are basically creating the graph from the followers.txt file. Now we are running the page rank over here. So in rank, it will give you all the page rank of the vertices that is inside this graph, which we have just loaded using graph loader class. So if you're passing an integer as an argument to the page rank, it will run that number iterations. Otherwise, if you're passing a double value, it will run until the convergence. So we are running page rank on this graph, and we have passed the vertices. Now after this, we are trying to load the users.txt file, and then we are trying to split the line by comma, then the field 0 to long, and we are storing the field 1. So basically field 0 in your user.txt is your vertex ID, or you can say the ID of the user, and field 1 is your username. So we are trying to load these two fields. Now we are trying to rank by username. So we are taking the users and we are joining the ranks. So this is where we are using the join operation. So ranks by username, we are trying to attach those username or put those username with the page rank value. So we are taking the users, then we are joining the ranks, which is again we are getting from this page rank, and then we are mapping the ID, username and rank. So it will take some time, run some iterations over the graph, and we'll try to converge it. So after converging, you can see the user and the rank. So the maximum rank is with Barack Obama, which is 1.45. Then with Lady Gaga, it's 1.39, and then with Odyssey, and so on. Let's go back to the slide. So now after page rank, let's quickly move ahead to connected components. The connected components algorithm labels each connected component of the graph with the ID of its lowest numbered vertex. So let's quickly go back to the VM. Now let's go inside the GraphX directory, and now we'll open this connect components example. So again, it's the same. We're importing graph loader and Spark session. Now this is the connect components example object. Next, this is the main function. And inside the main function, we are again specifying all those Spark session, then app name, then we have Spark context. So it's similar. So again, using this graph loader class and using this edge list file, we are loading the followers.txt file. Now in this graph, we are using this connected components algorithm, and then we are trying to find the connected components. Now at last, we are trying to again load this user file, that is users.txt, and we are trying to join the connected components with the username. So over here, it is also the same thing which we have discussed in PageRank, which is taking the field 0 and field 1 of your user.txt file. And at last, we are joining this users. And at last, we are trying to join this users to connect component, that is from here. Now we are printing the cc by username collect. So let us quickly go ahead and execute this example as well. So let me first copy this object name. Let's name this as example2. So as you can see, Justin Bieber has one connected component, then you can see this has three connected component, then this has one connected component, then Barack Obama has one connected component, and so on. So this basically gives you an idea about the connected components. Now let's quickly move back to the slide. We'll discuss about the third algorithm, that is triangle counting. So basically a vertex is a part of a triangle when it has two adjacent vertices with an edge between them. So it will form a triangle, right? And then that vertex is a part of a triangle. Now GraphX implements a triangle counting algorithm in the triangle count object. Now that determines the number of triangles passing through each vertex, providing a measure of clustering. So we can compute the triangle count of the social network dataset from the PageRank section. One more thing to note is that triangle count requires the edges to be in a canonical orientation, that is your source ID should always be less than your destination ID, and the graph to be partitioned using graph.partitionBy method. Now let's quickly go back. So let me open the GraphX directory again, and we'll see the triangle counting example. So again, it's the same, and the object is triangle counting example. Then the main function is same as well. Now we are again using this graph loader class, and we are loading the followers.txt, which contains the edges. As you can see here, we are using this partition by argument, and we are passing the random vertex cut, which is the partition strategy. So this is how you can go ahead and you can implement a partition strategy. We are loading the edges in canonical order and partitioning the graph for triangle count. Now we are trying to find out the triangle count for each vertex. So we have this try count variable, and then we are using this triangle count algorithm, and then we are specifying the vertices. So it will execute triangle count over this graph which we have just loaded from followers.txt file. And again, we are basically joining usernames. So first we are taking the usernames. So again, here we are performing the join between users and try counts. So try counts is from here, and then we are again printing the value from here. So again, this is the same. Let us quickly go ahead and execute this triangle counting example. So let me copy this. I'll go back to the terminal. I'll name it as example3 and change the class name, and I'll hit enter. So now you can see the triangle associated with Justin Bieber is 0, then Barack Obama is 1, with Odorski it's 1, and with Jerisic it's 1. So for better understanding, I would recommend you to go ahead and take this followers.txt and you can create a graph by yourself, and then you can attach these usernames with them, and then you will get an idea about why it is giving the number as 1 or 0. So again, the graph which is connecting 1, 2 and 4 is disconnect and it is not completing any triangles. So the value of these three are 0. And next, your second graph, which is connecting your vertex 3, 6 and 7, is completing one triangle. So that's the reason why these three vertices have values 1. Now, let me quickly go back. So now I hope that you guys are clear with all the concepts of graph operators, then graph algorithms. So now is the right time and let us look at a Spark GraphX demo where we'll go ahead and we'll try to analyze the Ford score by data. So let me quickly go back to my VM. So let me first show you the website where you can go ahead and download the Ford score by data. So over here you can go to download the Ford bikes trip history data. So you can go ahead and download this 2017 Ford's trip data. So I have already downloaded it. So to avoid the typos, I have already written all the commands. So first let me go ahead and start the Spark shell. So I'm inside the Spark shell. Now let me first import GraphX and Spark RDD. So I have successfully imported GraphX and Spark RDD. Now let me create a Spark SQL context as well. So I have successfully created the Spark SQL context. So this is basically for running SQL queries over the data frames. Now let me go ahead and import the data. So I am loading the data in DataFrame. So the format of file is CSV. Then in option, the header is already added. So that's why it's true. Then it will automatically infer the schema. And then in the load parameter, I have specified the path of the file. So I'll quickly hit enter. So the data is loaded in the data frame. To check, I'll use df.count. So it will give me the count. So you can see it has 5,19,700 rows. Now let me quickly go back and I'll print this schema. So this is the schema, the duration in second, then we have the start time, end time, then you have start station ID, then you have start station name, then you have start station latitude, longitude, then end station ID, end station name, then end station latitude, end station longitude, then your bike ID, user type, then the birth year of the member and the gender of the member. Now I'm trying to create a data frame that is just stations. So it will only create the station ID and station name, which I'll be using as vertex. So here I'm trying to create a data frame with the name of just stations, where I'm just selecting the start station ID and I'm casting it as float, and then I'm selecting the start station name, and then I'm using the distinct function to only keep the unique values. So I'll quickly go ahead and hit enter. So again, let me go ahead and use this just stations and I'll print the schema. So you can see there is station ID and then there is start station name. It contains the unique values of stations in this just station data frame. So now again I'm taking this stations where I'm selecting the start station ID and end station ID. Then I'm using RDD distinct, which will again give me the unique values. Then I'm using this flat map where I'm specifying the iterables, where we are taking the x0, that is your start station ID, and I'm taking x1, which is your end station ID. And then again I'm applying this distinct function that it will keep only the unique values. And then at last we have to df function which will convert it to data frame. So let me quickly go ahead and execute this. So I'm printing this schema. So as you can see, it has one column that is value and it has data type long. So I have taken all the start and end station ID, and using this flat map, I have iterated over all the start and end station ID, and then using the distinct function, I'm taking the unique values and converting it to data frames. So I can use these stations, and using the station, I'll basically keep each of the stations in a vertex. So this is the reason why I'm taking the stations, or you can say why I'm taking the unique stations from the start station ID and end station ID, so that I can go ahead and I can define vertex as the stations. And so now we are creating our set of vertices and attaching a bit of metadata to each one of them, which in our case is the name of the station. So as you can see, we are creating this station vertices, which is again an RDD with vertex ID and string. So we are using the stations, which we have just created. We are joining it with just stations, and the station value should be equal to just station ID. So as we have created stations and just station, so we are joining it, and then we are selecting the station ID and start station name. Then we are mapping row 0 and row 1. So your row 0 will basically be your vertex ID and row 1 will be the string, that is the name of your station. So let me quickly go ahead and execute this. So now let us quickly print this using collect for each println. So over here we are basically attaching the edges, or you can say we are creating the trip edges to all our individual rides, and then we'll get the station values, and then we'll add a dummy value of 1. So as you can see that I am selecting the start station and end station from the DF, which is the first data frame which we have loaded, and then I am mapping it to row 0 and row 1, which is your source and destination, and then I'm attaching a value 1 to each one of them. So I'll hit enter. Now let me quickly go ahead and print this station edges. So it is taking the source ID of the vertex and destination ID of the vertex, or you can say source station ID or vertex station ID, and it is attaching value 1 to each one of them. So now you can go ahead and build your graph. But again, as we discussed, that we need a default station. So you can have some situations where your edges might be indicating some vertices, but that vertices might not be present in your vertex RDD. So for that situation, we need to create a default station. So I'll create a default station as missing station. So now we are all set. We can go ahead and create the graph. So the name of the graph is station graph. Then the vertices are station vertices, which we have created, which basically contains the station ID and station name. And then we have station edges. And at last we have default station. So let me quickly go ahead and execute this. So now I need to cache this graph for faster access. So I'll use cache function. So let us quickly go ahead and check the number of vertices. So these are the number of vertices. Again, we can check the number of edges as well. So these are the number of edges. And to get a sanity check, so let's go ahead and check the number of records that are present in the data frame. So as you can see that the number of edges in our graph and the count in our data frame is similar, or you can say same. So now let's go ahead and run PageRank on our data. So we can either run a set number of iterations, or we can run it until the convergence. So in my case, I'll run it till convergence. So it's rank, then station graph, then page rank. So I have specified the double value. So it will run till convergence. So let's wait for some time. So now that we have executed the page rank algorithm, so we got the ranks which are attached to each vertices. So now let us quickly go ahead and look at the ranks. So we are joining ranks with station vertices, and then we are sorting it in descending values, and we are taking the first 10 rows and then we are printing them. So let's quickly go ahead and hit enter. So you can see these are the top 10 stations which have the most page rank values. So you can say it has more number of incoming trips. Now, one question would be, what are the most common destinations in the dataset from location to location? So we can do this by performing a grouping operator and adding the edge counts together. So basically this will give a new graph, except each edge will now be the sum of all the semantically same edges. So again, we are taking the station graph, we are performing group by edges, edge 1 and edge 2. So we are basically grouping edges edge 1 and edge 2. So we are aggregating them, then we are using triplet, and then we are sorting them in descending order again. And then we are printing the triplets from the source vertex and the number of trips. And then we are taking the destination attribute, or you can say destination vertex, or you can say destination station. So you can see there are 1933 trips from San Francisco ferry building to the station. Then again you can see there are 1411 trips from San Francisco to this location. Then there are 1025 trips from this station to San Francisco, and it goes so on. So now we have got a directed graph. That means our trips are directional from one location to other. So now we can go ahead and find the number of trips that go into a specific station and then leave from a specific station. So basically we are trying to find the inbound and outbound values, or you can say we are trying to find in degree and out degree of the stations. So let us first calculate the in degree. So I'm using station graph and I'm using in degree operator. Then I'm joining it with the station vertices, and then I'm sorting it again in descending order, and then I'm taking the top 10 values. So let's quickly go ahead and hit enter. So these are the top 10 station, and you can see the in degrees. So there are these many trips which are coming into these stations. Now similarly we can find the out degree. Now again you can see the out degrees as well. So these are the stations and these are the out degrees. So again you can go ahead and perform some more operations over this graph. So you can go ahead and find the station which has most number of trip sinks. That is, most number of people coming into that station, but less people are leaving that station. And again on the contrary, you can find out the stations where there are more number of edges, or you can say trip, leaving those stations, but there are less number of trips coming into those stations. So I guess you guys are now clear with Spark GraphX. Then we discussed the different types of graphs. Then moving ahead, we discussed the features of GraphX. Then we discussed something about property graph. We understood what is property graph, how you can create vertex, how you can create edges, how to use Vertex RDD, Edge RDD. Then we looked at some of the important vertex operations. And at last, we understood some of the graph algorithms. So I guess now you guys are clear about how to work with Spark GraphX.
What is Spark with Java? Spark Java is an effective programming language in the world of big data development. In simple terms, Spark Java is a combined programming approach for solving the day-to-day problems in big data using Spark in Java environment. Spark framework is written in Java and uses JVM or Java Virtual Machine to compile the codes which are written in Scala. We know that Spark supports many programming languages like Hive, Pig, Python, PySpark, and many more. But Scala is the most prominent programming languages ever built for Spark applications. But majority of the software developers feel comfortable with Java at an enterprise level, and they hardly prefer Scala or any other such type of programming languages. So Spark Java is one such approach where the software developers can run all the Scala programs and applications in Java environment with ease. It is practically running the logically same code with Java extensions such that it is easy for the developers to understand and deploy Spark applications. Now we have a brief understanding of Spark Java. Let us now move on to our next stage where we shall learn about setting up the environment for Spark Java. I'll explain the procedure in the form of steps. So let's begin with our first step. Our first step would be downloading the JDK and JRE from the official Java website and installing them onto your local system and setting the environment for Java. We have now landed on the official site for Java Development Kit. Here, we shall select the latest version of Java Development Kit and download it for our local system. Once after the JDK has been downloaded, our next step would be downloading the JRE for our local system. Now we are on the official Java website for Java Runtime Environment or JRE. Here, we shall select the updated JRE version which is suitable for our local system. Once after we have downloaded both the files which are JDK and JRE, the next step in our procedure would be setting up the Java environment. For setting up the Java environment, we need to edit the system environment variables. Here I have opened the system properties and here I'll be editing my environment variables. As you can see, I have set my Java home and I've provided the location of my JDK file. The next step would be setting up the path for my Java environment. Here you can select the path and edit the path variables. As you can see, I have already set the path for my Java home. Now, the next step would be saving the Java home and Java path files. By clicking OK, the Java home and Java path both are set. Now the next step would be installing Spark. Now we are on the official site for Apache Spark where we can download the required official version of Spark. You need to follow this particular link in order to download the Spark of the latest version which is suitable for your local system. Once the Spark has been downloaded, the next step would be setting up the environment for Spark. I'll explain how to set the environment for Spark in a step-by-step procedure. Once the Spark zip file is been downloaded, I have shifted that zip file into C drive and have saved the zip file into the new folder called Spark. Inside the Spark folder, I have extracted the contents of Spark zip file. Now you can see all the files which are present in Spark zip folder. Amongst all these folders, we have bin folder. Inside this bin folder, you have the access for Spark shell. Now we shall set the environment for Spark. Similar to setting up the Java environment, we shall set the Spark environment also. Here enter into environment variables and you can find my Spark home is already set. I'll show you it. As you can see, I have set Spark home with the location where the Spark folder is been located. Now, similarly, you have to set path for Spark. You must choose path for this and edit the variables present in path. As you can see, I have already set the path to my Spark environment and I have provided the location of the bin so that you can access the Spark shell through it. Now I'll be selecting OK in order to set the Spark home as well as the Spark path. Now our next step would be installing WinUtils. We have now landed on GitHub in order to find our winutils.exe folder. You must follow this link in order to download the exe folder and set up Hadoop environment through this. Once after the winutils.exe folder has been downloaded, you can copy that into the C drive into the new folder by name winutils, inside which you have to create a new folder again by the name bin. Inside that, you have to save your winutils.exe file. Now we shall set Hadoop environment. As you can see, in a similar procedure, I have also set Hadoop home environment. Now the next step in our procedure will be setting up the path for Hadoop home. Once after the Hadoop home has been set, you have to set Hadoop path in a similar procedure how we have followed Java and Spark. Now our next step would be installing Eclipse into our host system. Now we are on the official site for Eclipse where you can download the latest version of Eclipse IDE. I am using Eclipse Enterprise version And this is the link to install Eclipse installer. Once after you download the Eclipse installer file, you need to run it in order to select the Eclipse Enterprise version to get downloaded onto your host system. Now the next step would be downloading the Maven file and installing Maven into your host system and set the environment for Apache Maven. Let us see how does it work. We have now landed on the official site for downloading Maven. You need to follow this particular link in order to download the latest Apache Maven version. Once after you download Apache Maven, you need to set environment for Maven as well. Here you can see that I have set home for Maven. Once after the home is been set for Maven, you need to provide the path for Maven as well. You can do it by editing the path variables here. As you can see, I have already set the path for Maven as well. This is the path for my Maven. Now by pressing OK, I'll be setting home for Maven and path for Maven. The next step in our procedure would be installing the Scala IDE for Eclipse. We are now on the official site for downloading Scala IDE for Eclipse. You need to follow this particular link to download the IDE for Eclipse. Once after we have downloaded all the prerequisites we needed and setting up the environment for all the softwares, our next step would be running a sample Spark Java program on Eclipse. Let's begin with it. In our example program, we shall load a text file into our Eclipse environment and find out the number of repetitions of a particular alphabet in the text file. Now, before we get started with actually executing a Spark example program in Java environment, we need to achieve some prerequisites which I'll mention below as steps for better understanding of the procedure. The first step would be, for starting Spark as a master, you need to follow this particular command where you'll be starting your Spark as a master. Once your Spark is being started as a master, as you can see, the Spark is being deployed as a master. Now we shall start our local host in order to check the Spark status. As you can see, the Spark is being loaded as a master. Now our next step would be starting Spark as a worker. For that, you need to open a new command prompt and run Spark as a worker. Here, as you can see, I have started a new command prompt and I'm running Spark as a worker along with the Spark's IP address. You can get the IP address of Spark from the local host. So this is the IP address of Spark. You can copy this and you can run Spark as a worker in a new command prompt. Once after you have set Spark as a master and worker, now you need to start Spark shell in a new command prompt. You can see I have opened a new command prompt which is the third command prompt, and here I'm starting Spark shell as a master along with the Spark's IP address. Now you can see Spark master is alive. Along with it, the Spark's worker is also alive, and this is the worker ID of Spark. Once after the Spark has been set, now you need to start your Eclipse. Once after you have started the Eclipse IDE, you need to reach File in order to create a new Maven project. Here I have selected project and now I'm searching for Maven. Here you can find Maven, open the Maven file and you can select Maven project. Next, here you need to tick on the option called Create a Simple Project. Next, you need to provide the group ID and artifact ID. Let me create a new group ID and artifact ID. Click on Finish in order to create a new Maven project. Your new Maven project has been successfully created. As you can see, it is available here. You can see the pom.xml file here. Now the first step before running a program would be loading all the Spark libraries involved. To add up all the Spark libraries, you need to right-click on the JRE system library and select Build Path and go into Configure Build Path. You can see a dialog box here and you need to select Add External Jars. Now you need to find the location where your Spark is been located. I have located my Spark file in C drive. I'll select my Spark, inside which I'll select bin. Here you can see all the jar files and library files which you require for running a Spark Java program. You need to select all and you need to select open to load all these documents onto your Eclipse environment. By selecting apply and close, you'll have all the jar and library files in order to run your Spark Java example. Once after all the Spark libraries and jar files are been loaded onto your Eclipse environment, you need to set Scala nature onto your program. You can do that by selecting sample program and going into properties. Once after you load all the Spark libraries and jar files, you need to set Scala nature to your program. You can do that by right-clicking on sample program and selecting configure. And now add Scala nature. Once after all the prerequisites are finished, you need to open your POM file, and here you need to add dependencies. You can get all the dependencies from Maven repository. Now we are on the page of Maven repository, where you have to search for Spark and search for the dependencies. Here for our example, we need Spark project core. You can select the version of your Spark. In my host system, I'm having the Spark version of 2.43 and Scala version of 2.12. Here I can get my dependency file. I can take this and use it in my Eclipse environment. As you can see, I have set the dependencies for my Spark Java program here. Once after your POM folder is set, you can get into your source folder where you have to create your package, inside which you can run your Scala application. So this is my sample Scala application where I'm loading a text file into the application, and I'll be counting the lines which have the alphabet A and the lines which have the alphabet B. Let me run this program as a Scala application. The application has successfully run, and now we have the output here, which says we have 62 lines with the alphabet A and 31 lines with the alphabet B. Now we have a brief understanding of Spark Java. Let us move into our use case on students' academic performance so as to learn Spark Java in a much better way. Similar to our previous example, let us set up our prerequisites and then we shall begin with our use case. First, you need to start up a new Maven project, then get into pom.xml in order to write all your dependencies here using Maven repository, then adding Scala nature to your project. Once after the pom.xml is set, you need to add all the Spark libraries and jars using the JRE system library. Later, you need to set Scala nature to your program, then create a new package inside which you have to run your Scala application. Now, let us begin with our use case. Here, I'll be loading a CSV file called Students Performance, which will be having the following columns: gender, race, parental level of education, lunch, test preparation course, math score, reading score, and writing score. So this is the CSV file which we are loading into our Eclipse IDE to perform our Spark SQL operations. So let us run our SQL queries one by one. As you can see, our application has been started. We have started from this point where I have displayed a text called "We are starting from here." Then moving on to the first stage where my first command was to print all the contents in our CSV file. So the output for the same is here. As you can see, all the rows and columns have been printed here. And my next command was to print the schema which I have designed here using my customized schema where I have provided the data type for each and every column. So using this command, I'm printing my customized schema here, and the output for the same is been displayed here. So this is my output for print schema, and later my next command is to print all the data from my CSV file where the gender is equals to female. As you can see, the data has been printed out successfully in the form of a data frame. Now let us execute our second statement. Here I have used select command in order to print the data which is present in our CSV file in the form of a data frame. Now let us move into our next code in which I'll be using the command where to print the specified data of male candidates in our CSV file. As you can see, our code is been successfully loaded and the output is also been generated. I have used select command in order to print the data which is present in our CSV file in the form of a data frame. So this is our result for the first command, which is select. Now let us execute the next command using the function where to print the data of the students who have scored more than 75 in maths. So this is the output for our command, and these are the students who have scored more than 75 in maths. As you can see, this is the output. Now let us move on to the next function where we shall use group by and count operations to find out the number of students in each group. So this is the output for our command, and we have all the groups here which are A, B, C, D and E, and also the number of students in each group. Now let us move on to the next operation where we'll use filter function in order to find out the students who are proven to be the best in reading. So this is the output for our operation. We have the data here of the students who have scored more than 90 marks in reading. Now let us move on to the next operation where we'll use distinct function to find out the distinct values in our data. So this is the output for our distinct operation, which will display only the distinct values present in our data. Now let us use AND function in order to compare the multiple entities in our data. Here I am applying AND operation upon two entities, which is math score and reading score. The math score must be above 75 and the reading score must be above 90. So we'll have the data displayed here of the students who have scored more than 75 in maths and more than 90 in reading. So this is the output.
I will help you compare two major big data platforms, that is Hadoop MapReduce and Apache Spark. We are going to use few parameters like performance, cost, ease of use, data processing, security, and fault tolerance that will be the benchmark for our comparison. Before I differentiate these terms for you guys, let me first tell you about the current stats of these trending frameworks. According to the market research by Forbes in 2017, big data adoption reached 53% in the IT industry. Out of that, Spark overtook the big data adoption rate by 47%, whereas MapReduce took only 14% of the market. So current market stats is not the only metric through which we can compare these two frameworks. In today's hyper-growing industries, Spark and MapReduce play their own role to benefit us with its features. So guys, let's explore the various other parameters through which we can compare these two frameworks. The first on the list we have is performance. As you can see in this picture, in case of Hadoop MapReduce, the data moves between disk and network. But in case of Spark, the data is cached in the memory. So now let me explain this to you. Hadoop MapReduce passes data back to the disk after a map or reduce action. But Apache Spark processes data in the memory. So let me tell you one thing. Spark needs a lot of memory. Much like the standard databases, it loads a process into the memory and keeps it there until the further notice. On the other hand, MapReduce, however, kills its processes as soon as the job is done so that it can run easily alongside other services with minor performance differences. So I can say that Spark performs better when all the data fits in the memory. So consider an example where you want to store 32 GB of data and the RAM size that you have is just 16 GB. So what happens when the data size is more than the size of the memory? In case of this, when the memory is full, Spark automatically starts using the disk space to store the data. So this is how Spark performs better when compared to Hadoop MapReduce. Now let's move further and see ease of use. Talking about Spark, it has comfortable APIs for Java, Scala, Python, and also includes Spark SQL for the SQL savvy. It's very easy to write user-defined functions as it has enriched APIs and that supports interactive mode in real time. On the other hand, Hadoop MapReduce is written in Java and is infamous for being very difficult to program. Though you have Pig that makes it easier, it requires some time to learn the syntax. And one more thing to tell you, Hadoop MapReduce does not support real-time data processing. So one can say that Spark is easier to program and includes an interactive mode. On the other hand, Hadoop MapReduce is more difficult to program, but it is very useful for batch processing systems. Next, let's see how cost influences both Hadoop MapReduce and Apache Spark. To tell you, both are open source, but money needs to be spent on machining and staff. In case of Spark, the memory should be at least as large as the amount of data that you need to process, because the data has to fit in the memory for optimal performance. So if you need to process really big data, Hadoop will definitely be the cheaper option since the hard disk space comes at a much lower rate than memory space. Not only that, there is also a wide array of Hadoop as a service offerings and Hadoop-based services which will help to skip the hardware and staffing requirements. So based on these considerations, I can say Spark is more cost-effective according to the benchmarks, whereas Hadoop MapReduce could be cheaper as it provides Hadoop as a service offerings. But yes, one important thing to keep in mind is that Spark's technology reduces the number of required systems. That is, it needs significantly few systems that actually cost more. So there will be a point at time where Spark reduces the cost per unit of computation even with the additional RAM requirement. So in this case, Both are actually having their own cost benefits in their own ways. Now, coming to data processing, Apache Spark can do more than plain data processing. That is, it can process graphs and use the existing machine learning libraries. Not only that, Spark can also do real-time data processing as well as the batch processing. This presents an interesting opportunity to use one platform for everything instead of having to split tasks across different platforms. On the other hand, Hadoop MapReduce is great for batch processing. If you want a real-time option, you will need to use another platform like a Storm or Impala. And for graph processing, you can use Giraffe. So by this, we can say that Spark is a Swiss Army knife of data processing, whereas Hadoop MapReduce is a commando knife of batch processing. So let me tell you, if you want to process real-time data with 100 times faster than MapReduce, then you can opt for Apache Spark. And if you just want to do batch processing or plain data processing, you can go with Hadoop MapReduce. Now let's see how both these frameworks play a fair role in case of security aspect. Coming to Spark, it is bit bare at the moment when it comes to security. Authentication is supported via a shared secret, and the web user interface can be secured via Java X servlet filters, and event logging is also included. Whereas Hadoop MapReduce can enjoy all the Hadoop security benefits and integrate with Hadoop security projects like Knox Gateway and Sentry. So I can say in terms of security, Spark is still in its infancy, but Hadoop MapReduce has more inbuilt security features and projects. As MapReduce is very old in the big data playground, I can say in case of security, Hadoop MapReduce is a pro, whereas Apache Spark is a learner in terms of security in the big data playground. Now let's look at the last parameter, that is fault tolerance. Talking about Spark, it has retries per task and speculative execution, but MapReduce relies on hard drives. I can say if a process crashes in the middle of execution, it could continue wherever it is left off, and this can actually save time. That is, we can say it uses replication for fault tolerance. In case of Spark, we all know that the resilient distributed datasets are the building blocks of Apache Spark, and they provide the fault tolerance to Spark. They can refer to any dataset present in the external storage system like HDFS, HBase, shared file system, and many more, and they can then be operated parallelly. One interesting thing to know is that RDDs can persist a dataset in the memory across operations, which makes future actions 10 times much faster. So if an RDD is lost, it will automatically be recomputed by using the original transformations. This is how Spark provides fault tolerance. Now that we have compared MapReduce and Spark based on these parameters, let's see a real-time example of each of them. First, let's see a use case of MapReduce. So now let's see how MapReduce is used in ETL and data analytics, that is extract, transform, load, and data analytics. MapReduce programming can be used to transform data, files, or records from one system to another using distributed models. Say you have two data centers, one is located in Europe and the other one in US. And you have 10 terabytes of data in data center 1, and you want to transform all the data to data center 2. So if you try to extract, transform, and load all these files from data center 1 to data center 2 using the traditional way of bulk copy, do you think it will work? An obvious no, right? So in this case, MapReduce programming model plays a vital role to build a distributed system for copying files from data center 1 to data center 2. We can use the map function to locate a specific file and then break it down into chunks for transfer, while the reduce function can combine the chunks of a related file and then perform checksum to ensure data integrity and so on. We can use MapReduce programming for analyzing large volumes of data from databases, data warehouses, or logs while implementing specific business logic to derive insights. It can also be used for building extract, transform, and load systems, that is ETL systems, for moving data from one data store to another. So this is how MapReduce is useful for ETL and data analytics. Now let's see a use case of Apache Spark. So let's try to understand how Spark is used in credit card fraud detection. Credit card transaction can be captured over time based on the behavior of the cardholder spending incidents. The events are stored as transaction history, which would be used to analyze the possible detection of fraud. The big data fraud detection techniques analyze the data to find out the relationship between the historical data and the data which is learned over the period. The techniques will help in extracting meaningful evidence of frauds from large data sets. In this example, let's consider the credit card holder is from India and all the transaction is above the spending limit and the transaction is made in US. The stream of data is injected through the Kafka through various topics and is processed in the Spark engine. It is then analyzed to detect the fraud, which is written to the fraud topic. If the transaction is over the limit of regular spending or if the transaction is made in a different city, then the transaction is written to the fraud topic. So now let me tell you what happens in Spark engine and how does Spark streaming works. Spark streaming can process unstructured and structured data. Spark reads all the data straight from a file and converts it to a resilient distributed datasets, that is the RDDs. Spark streaming receives the data streams and splits data into batches. After the division, data is processed by the core of the Spark, that is Spark engine, which will generate the final stream of results in batches from the specified interval of time, which is called as windowing. When these streams of the data come to the Spark streaming as D streams, that is the decriticized stream, they are sequenced internally as RDDs. The RDD operations are performed in parallel when the credit card data is passed to get the necessary information. So in this case, events that are related to fraud are published to fraud topics, and likewise, non-fraud events are published to enrich topics. So this is how Spark is used to identify the fraud topics in credit card fraud detection. Now that we have analyzed and compared all the factors of MapReduce and Spark, let's answer the burning question that is there in all of your minds. Which framework to choose, Hadoop MapReduce or Apache Spark? Well, to give you a tailored response, I would say it's your particular business needs that determines the choice of a framework. Linear processing of huge data sets is the advantage of Hadoop MapReduce, while Spark delivers fast performance, iterative processing, real-time analytics, graph processing, machine learning, and many more. In many cases, Spark may outperform Hadoop MapReduce. The best part is that Spark is fully compatible with the Hadoop ecosystem and also works smoothly with Hadoop distributed file system, Apache Hive, etc. By this analysis, I can conclude that Apache Spark is the shiny new toy in the big data playground. But for batch processing applications, MapReduce still plays a key role in its field. So which framework do you think is the winner? You can put your choice of winner in the comment section below.
So in a real-time scenario, we have different systems or services which will be communicating with each other. And the data pipelines are the ones which are establishing connection between two servers or two systems. Now let's take an example of e-commerce website where it can have multiple servers at front end like web or application server for hosting application. It can have a chat server for the customers to provide chat facilities. Then it can have a separate server for payment, etc. Similarly, organization can also have multiple servers at the back end, which will be receiving messages from different front end servers based on their requirements. Now they can have a database server which will be storing the records. Then they can have security systems for user authentication and authorization. Then they can have real-time monitoring server, which is basically used for recommendations. So all these data pipelines becomes complex with the increase in number of systems, and adding a new system or server requires more data pipelines, which will again make the data flow more complicated and complex. Now managing these data pipelines also become very difficult as each data pipeline has their own set of requirements. For example, data pipelines which handles transactions should be more fault tolerant and robust. On the other hand, clickstream data pipeline can be more fragile, So adding some pipelines or removing some pipelines becomes more difficult from the complex system. So now I hope that you would have understood the problem due to which messaging systems was originated. Let's move to the next slide and we'll understand how Kafka solves this problem. Now, messaging system reduces the complexity of data pipelines and makes the communication between systems more simpler and manageable. Using messaging system, now you can easily establish remote communication and send your data easily across network. Now your different systems may use different platform and languages, and messaging system provides you a common paradigm independent of any platform or language. So basically it decouples the platform on which your front end server as well as your back end server is running. You can also establish an asynchronous communication and send messages so that the sender does not have to wait for the receiver to process the messages. Now, one of the benefit of messaging system is that you can ensure reliable communication. So even when the receiver and network is not working properly, your messages wouldn't get lost. Now, talking about Kafka, Kafka decouples the data pipelines and solves the complexity problem. The applications which are producing messages to Kafka are called producers, and the applications which are consuming those messages from Kafka are called consumers. Now, as you can see in the image, the front end server, then your application server 1, application server 2, and chat server are producing messages to Kafka, and these are called producers. And your database server, security systems, real-time monitoring server, then other services and data warehouse, these are basically consuming the messages and are called consumers. So your producer sends the message to Kafka, and then Kafka store those messages, and consumers who want those messages can subscribe and receive them. Now you can also have multiple subscribers to a single category of messages. So your database server and your security system can be consuming the same messages which is produced by application server 1. And again, adding a new consumer is very easy. You can go ahead and add a new consumer and just subscribe to the message categories that is required. So again, you can add a new consumer, say consumer 1, and you can again go ahead and subscribe to the category of messages which is produced by application server 1. So let's quickly move ahead. Let's talk about Apache Kafka. So Apache Kafka is a distributed publish subscribe messaging system. Messaging traditionally has two models, queuing and publish subscribe. In a queue, a pool of consumers may read from a server and each record only goes to one of them. Whereas in publish subscribe, the record is broadcasted to all consumers, so multiple consumers can get the record. The Kafka cluster is distributed and have multiple machines running in parallel, and this is the reason why Kafka is fast, scalable, and fault tolerant. Now let me tell you that Kafka is developed at LinkedIn and later it became a part of Apache project. Now let us look at some of the important terminologies. So we'll first start with topic. So topic is a category or feed name to which records are published, and topic in Kafka are always multi-subscriber. That is, a topic can have 0, 1 or multiple consumers that can subscribe to the topic and consume the data written to it. For an example, you can have sales record getting published in sales topic, you can have product records which is getting published in product topic, and so on. This will actually segregate your messages and consumer will only subscribe to the topic that they need. And again, your consumer can also subscribe to 2 or more topics. Now let's talk about partitions. So Kafka topics are divided into a number of partitions, and partitions allow you to parallelize a topic by splitting the data in a particular topic across multiple brokers, which means each partition can be placed on separate machine to allow multiple consumers to read from a topic parallelly. So in case of sales topic, you can have three partition, partition 0, partition 1 and partition 2, from where three consumers can read data parallelly. Now moving ahead, let's talk about producers. So producers are the one who publishes the data to topics of their choice. Then you have consumers. So consumers can subscribe to one or more topic and consume data from that topic. Now consumers basically label themselves with a consumer group name, and each record published to a topic is delivered to one consumer instance within each subscribing consumer group. So suppose you have a consumer group, let's say consumer group 1, and then you have three consumers residing in it, that is consumer A, consumer B and consumer C. Now from the sales topic, each record can be read once by consumer group 1 and it can either be read by consumer A or consumer B or consumer C, but it can only be consumed once by the single consumer group, that is consumer group 1. But again, you can have multiple consumer groups which can subscribe to a topic, where one record can be consumed by multiple consumers, that is one consumer from each consumer group. So now let's say you have a consumer group 1 and consumer group 2. In consumer group 1 we have two consumers, that is consumer A and consumer B, and consumer group 2 we have two consumers, consumer C and consumer D. So if consumer group 1 and consumer group 2 are consuming messages from topic sales, so the single record will be consumed by consumer group 1 as well as consumer group 2, and a single consumer from both the consumer group will consume the record once. So I guess you are clear with the concept of consumer and consumer group. Now consumer instances can be a separate process or separate machines. Now talking about brokers, brokers are nothing but a single machine in the Kafka cluster. And Zookeeper is another Apache open source project. It stores the metadata information related to Kafka cluster like brokers information, topics details, etc. So Zookeeper is basically the one who is managing the whole Kafka cluster. Now let's quickly go to the next slide. So suppose you have a topic, let's assume this is topic sales, and you have four partition. So you have partition 0, partition 1, partition 2 and partition 3. Now you have 5 brokers over here. Now let's take the case of partition 1. So if the replication factor is 3, it will have 3 copies which will reside on different brokers. So one replica is on broker 2, next is on broker 3 and next is on broker 5. And as you can see, REPL 5, so this 5 is from this broker 5. So the ID of the replica is same as the ID of the broker that hosts it. Now moving ahead, one of the replica of partition 1 will serve as the leader replica. So now the leader of partition 1 is replica 5, and any consumer coming and consuming messages from partition 1 will be served by this replica. And these two replica is basically for fault tolerance, so that once your broker 5 goes off or your disk becomes corrupt, so your replica 3 or replica 2, one of them will again serve as a leader, and this is basically decided on the basis of most in sync replica. So the replica which will be most in sync with this replica will become the next leader. So similarly, this partition 0 may reside on broker 1, broker 2 and broker 3. Again, your partition 2 may reside on broker 4, broker 5 and say broker 1. And then your third partition might reside on these 3 brokers. So suppose that this is the leader for partition 2, this is the leader for partition 0, this is the leader for partition 3, this is the leader for partition 1, right? So you can see that 4 consumers can consume data parallelly from these brokers. So it can consume data from partition 2, this consumer can consume data from partition 0, and similarly for partition 3 and partition 1. Now by maintaining the replica basically helps in fault tolerance, and keeping different partition leaders on different brokers basically helps in parallel execution, or you can say parallelly consuming those messages. So I hope that you guys are clear about topics, partitions and replicas. Now let's move to our next slide. So this is how the whole Kafka cluster looks like. You have multiple producers, which is again producing messages to Kafka. Then this whole is the Kafka cluster, where you have 2 nodes. Node 1 has 2 broker, broker 1 and broker 2, and the node 2 has 2 brokers, which is broker 3 and broker 4. Again, consumers will be consuming data from these brokers, and Zookeeper is the one who is managing this whole Kafka cluster. Now let's look at some basic commands of Kafka and understand how Kafka works, how to go ahead and start Zookeeper, how to go ahead and start Kafka server, and how to again go ahead and produce some messages to Kafka and then consume some messages to Kafka. So let me quickly open my VM. So now let me quickly open the terminal. Let me quickly go ahead and execute sudo jps so that I can check all the daemons that are running in my system. So you can see I have name node, data node, resource manager, node manager, job history server. So now as all the HDFS daemons are running, let us quickly go ahead and start Kafka services. So first I'll go to Kafka home. So let me show you the directory. So my Kafka is in user lib. Now let me quickly go ahead and start Zookeeper service. But before that, let me show you zookeeper.properties file. So the client port is 2181. So my Zookeeper will be running on port 2181. And the data directory in which my Zookeeper will store all the metadata is /temp/Zookeeper. So let us quickly go ahead and start Zookeeper. And the command is bin zookeeper server start. So this is the script file, and then I'll pass the properties file which is inside config directory, and I'll hit enter. Meanwhile, let me open another tab. So here I'll be starting my first Kafka broker, but before that let me show you the properties file. So we'll go in config directory again, and I have server.properties. So this is the properties of my first Kafka broker. So first we have server basics. So here the broker ID of my first broker is 0. Then the port is 9092 on which my first broker will be running. So it contains all the socket server settings. Then moving ahead, we have log basics. So in that log basics, this is log directory, which is /tem/kafka-logs. So over here, my Kafka will store all those messages or records which will be produced by the producers. So all the records which belongs to broker 0 will be stored at this location. Now the next section is internal topic settings, in which the offset topic replication factor is 1, then transaction state log replication factor is 1. Next we have log retention policy. So the log retention hours is 168. So your records will be stored for 168 hours by default, and then it will be deleted. Then you have Zookeeper properties, where we have specified zookeeper.connect. And as we have seen in zookeeper.properties file, that our Zookeeper will be running on port 2181. So we are giving the address of Zookeeper, that is localhost 2181. And at last we have group coordinator setting. So let us quickly go ahead and start the first broker. So the script file is Kafka server start.sh. And then we have to give the properties file, which is server.properties for the first broker. I'll hit enter, and meanwhile let me open another tab. Now I'll show you the next properties file, which is server1.properties. So the things which you have to change for creating a new broker is, first you have to change the broker ID. So my earlier broker ID was 0, the new broker ID is 1. Again, you can replicate this file, and for a new server you have to change the broker ID to 2. Then you have to change the port, because on 9092 already my first broker is running, that is broker 0. So my broker 1 should connect to a different port, and here I have specified 9093. Next thing what you have to change is the log directory. So here I have added a -1 to the default log directory. So all the records which is stored to my broker 1 will be going to this particular directory, that is /tem/kafka logs -1. And rest of the things are similar. So let me quickly go ahead and start second broker as well. And let me open one more terminal. And I'll start broker 2 as well. So the Zookeeper started, then broker 1 is also started, and this is broker 2 which is also started, and this is broker 3. So now let me quickly minimize this, and I'll open a new terminal. Now first let us look at some commands related to Kafka topics. So I'll quickly go ahead and create a topic. So again, let me first go to my Kafka home directory. Then the script file is Kafka topic.sh. Then the first parameter is create. Then we have to give the address of Zookeeper, because Zookeeper is the one who is actually containing all the details related to your topic. So the address of my Zookeeper is localhost 2181. Then We'll give the topic name. So let me name the topic as Kafka-Spark. Next, we have to specify the replication factor of the topic. So it will replicate all the partitions inside the topic that many times. So replication hyphen factor, as we have 3 brokers, so let me keep it as 3. And then we have partitions, so I'll keep it as 3 because we have 3 brokers running and our consumer can go ahead and consume messages parallelly from 3 brokers. And let me press enter. So now you can see the topic is created. Now let us quickly go ahead and list all the topics. So the command for listing all the topics is /bin. Again, will open Kafka topic script file, then hyphen list, and again will provide the address of zookeeper. So to again list the topic, we have to first go to the Kafka topic script file, then we have to give hyphen list parameter, and next we have to give the zookeeper's address, which is localhost 2181. I'll hit enter. And you can see I have this Kafka-Spark. The Kafka Spark topic has been created. Now let me show you one more thing. Again, we'll go to bin Kafka topics.sh and we'll describe this topic. I'll pass the address of zookeeper, which is localhost 2181, and then I'll pass the topic name, which is Kafka-Spark. So now you can see here the topic is Kafka Spark, the partition count is 3, the replication factor is 3, and the config is as follows. So here you can see all the 3 partitions of the topic, that is partition 0, partition 1, and partition 2. Then the leader for partition 0 is broker 2, the leader for partition 1 is broker 0, and leader for partition 2 is broker 1. So you can see we have different partition leaders residing on different brokers. So this is basically for load balancing, so that different partition could be served from different brokers and it could be consumed parallelly. Again, you can see the replica of this partition is residing in all the 3 brokers. Same with partition 1 and same with partition 2. And it's showing you the in-sync replica. So in-sync replica, the first is 2, then you have 0, and then you have 1. And similarly with partition 1 and 2. So now let us quickly go ahead. I'll reduce this to half. Let me open one more terminal. The reason why I'm doing this is that we can actually produce message from one console and then we can receive the message in another console. So for that, I'll start Kafka console producer first. So the command is /bin Kafka console producer.sh, and then in case of producer you have to give the parameter as broker-list, which is localhost 9092. You can provide any of the brokers that is running and it will again take the rest of the brokers from there. So you just have to provide the address of one broker. You can also provide a set of brokers, so you can give it as localhost :9092 comma localhost :9093 and similarly. So here I am passing the address of the first broker. Now next I have to mention the topic. So topic is Kafka Spark and I'll hit enter. So my console producer is started. Let me produce a message saying hi. Now in the second terminal I'll go ahead and start the console consumer. So again the command is Kafka console consumer.sh, and then in case of consumer you have to give the parameter as bootstrap server. So this is the thing to notice, guys, that in case of producer you have to give the broker list, while in case of consumer you have to give bootstrap server, and it is again the same, that is localhost 9092, which is the address of my broker 0, and then I'll give the topic, which is Kafka Spark. Now adding this parameter, that is from -beginning, will basically give me messages stored in that topic from beginning. Otherwise, if I'm not giving this parameter -- from beginning, I'll only consume the recent messages that has been produced after starting this console consumer. So let me hit enter, and you can see I'll get a message saying hi first. Oh, I'm sorry guys, the topic name I have given is not correct. Sorry for my typo. Let me quickly correct it and let me hit enter. So as you can see, I'm receiving the messages. I received hi, then let me produce some more messages. So now you can see all the messages that I am producing from console producer is getting consumed by console consumer. Now this console producer as well as console consumer is basically used by the developers to actually test the Kafka cluster. So what happens if there is a producer which is running and which is producing those messages to Kafka, then you can go ahead and you can start console consumer and check whether the producer is producing the messages or not, or you can again go ahead and check the format in which your messages are getting produced to the topic. Those kind of testing part is done using console consumer, and similarly using console producer, you do something like you are creating a consumer, so you can go ahead, you can produce a message to Kafka topic, and then you can check whether your consumer is consuming that message or not. This is basically used for testing. Now let us quickly go ahead and close this. Now let us get back to our slides. Now I have briefly covered Kafka and the concepts of Kafka, but if you want a detailed Kafka tutorial, you can go to Edureka YouTube channel and you can watch Kafka tutorial. I'll share the link in the description section. So you can go in the video description and you can click on the Kafka tutorial link and you can go through the whole part and you can easily brush up all your concepts related to Kafka. So here basically I'm giving you a small brief idea about what Kafka is and how Kafka works. Now, as we have understood why we need messaging systems, what is Kafka, what are different terminologies in Kafka, how Kafka architecture works, and we have seen some of the basic Kafka commands. So before moving to Kafka Spark streaming demo, so I have just given you a brief intro to Apache Spark. If you want a detailed tutorial on Apache Spark or different components of Apache Spark like Apache Spark SQL, Spark DataFrames, or Spark Streaming, Spark GraphX, Spark Mlib, so you can go to Edureka's YouTube channel again, and I'll also leave the video links in the description of this video. So now we are here guys. I know that you guys are waiting for this demo from a while. So now let's go ahead and look at Kafka Spark streaming demo. So let me quickly go ahead and open my virtual machine and I'll open a terminal. So let me first check all the daemons that are running in my system. So my zookeeper is running, name node is running, data node is running, and then my resource manager is running. All the three Kafka brokers are running. Then node manager is running and job history server is running. So now I have to start my Spark daemons. So let me first go to the Spark home, and to start the Spark daemon, the command is spin start all.sh. So let me quickly go ahead and execute sudo jps to check my Spark daemons. So you can see master and worker daemons are running. So let me close this terminal. Let me go to the project directory. So basically I have two projects. This is Kafka Transaction Producer and the next one is the Spark Streaming Kafka Master. So first we will be producing messages from Kafka Transaction Producer, and then we'll be streaming those records which is basically produced by this producer using the Spark Streaming Kafka Master. So first let me take you through this Kafka Transaction Producer. So this is our pom.xml file. Let me open it with gedit. So basically this is a Maven project, and I have used Spring Boot Server. So I have given Java version as 8. You can see Kafka client over here and the version of Kafka client. Then you can see I'm importing Jackson data bind, then JSON, and then I'm packaging it as a WAR file, that is web archive file. And here I am again specifying the Spring Boot Maven plugins, which is to be downloaded. So let me quickly go ahead and close this, and we'll go to this source directory and then we'll go inside main. So basically this is the file, that is sales jan 2009 file. So let me show you the file first. So these are the records which I'll be producing to the Kafka. So the fields are transaction date, then product, price, payment type, then name, city, state, country, account created, then last login, latitude and longitude. So let me close this file. And then the application.yml is the main property file. So in this application.yml, I'm specifying the bootstrap server, which is localhost 9092. Then I'm specifying the brokers, which again resides on localhost 9092. So here I have specified the broker list. Now next I have product topic. So the topic of the product is transaction. Then the partition count is 1. So basically your ACKS config controls the criteria under which requests are considered complete. And the all setting we have specified will result in blocking on the full commit of the record. It is the slowest but the most durable setting. Now talking about retries, so it will retry thrice. Then we have minimum pool size and we have maximum pool size, which is basically for implementing Java threads. And at last we have the file path. So this is the path of the file which I have shown you just now. So messages will be consumed from this file. Let me quickly close this file and we'll look at application.properties. So here we have specified the properties for our Spring Boot server. So we have server context path, that is /Edureka. Then we have Spring application name, that is Kafka producer. We have server port, that is 9988, and the Spring events timeout is 20. So let me close this as well. Let's go back. Let's go inside Java, com, Edureka, Kafka. So we'll explore the important files one by one. So let me first take you through this DTO directory. And over here we have transaction.java. So basically here we are storing the model. So basically you can see these are the fields from the file which I have shown you. So we have transaction date, we have product, price, payment type, name, city, state, country, and so on. So we have created variable for each field. So what we are doing, we are basically creating a getter and setter function for all these variables. So we have get transaction ID, which will basically return the transaction ID. Then we have set transaction ID, which will basically set the transaction ID. Similarly, we have get transaction date for getting the transaction date. Then we have set transaction date and it will set the transaction date using this variable. Then we have get product, get price, set price, and all the getter and setter methods for each of the variable. This is the constructor. So here we are taking all the parameters like transaction date, product, price, and then we are setting the value of each of the variables using this operator. So we are setting the value for transaction date, product, price, payment, and all of the fields that is present over there. Next, we are also creating a default constructor. And then over here, we are overriding the toString method. And what we are doing, we are basically returning the transaction details. And we are returning transaction date and then the value of transaction date, product, then value of product, price, then value of price, and so on for all the fields. So basically, this is the model of the transaction. So we can go ahead and we can create object of this transaction and then we can easily go ahead and send the transaction object as the value. So this is the main reason of creating this transaction model. Now let me quickly go ahead and close this file. Let's go back and let's first take a look at this config. So this is Kafka properties.java. So what we did, again, as I have shown you the application.yml file, so we have taken all the parameters that we have specified over there. That is your bootstrap, product topic, partition count, then brokers, file name, and thread count. So all these properties, then you have file path, then all these properties we have taken, we have created a variable, and then what we are doing, again, we are doing the same thing as we did with our transaction model. We are creating a getter and setter method for each of these variables. So you can see we have get file path and we are returning the file path. Then we have set file path where we are setting the file path using this operator. Similarly, we have get product topic, set product topic. Then we have getter and setter for thread count. We have getter and setter for bootstrap and all those properties. Now we can again go ahead and call this Kafka properties anywhere, and then we can easily extract those values using getter methods. So let me quickly close this file and I'll take you to the configurations. So in this configuration, what we are doing, we are creating the object of Kafka properties, as you can see. So what we are doing, then we are again creating a properties object, and then we are setting the properties. So you can see that we are setting the bootstrap server config, and then we are retrieving the value using the Kafka properties object, and this is the get bootstrap server function. Then you can see we are setting the acknowledgement config, and we are getting the acknowledgement from this get acknowledgement function, and then we are using this get retries method. So from all these Kafka properties object, we are calling those getter methods and retrieving those values and setting those values in this property object. So then we have partitioner class. So we are basically implementing this default partitioner, which is present in org Apache Kafka client producer internals package. Then we are creating a producer over here, and we are passing this props object, which will set the properties. So over here we are passing the key serializer, which is the string key serializer, and then this is the value serializer in which we are creating new custom JSON serializer, and then we are passing transaction over here, and then it will return the producer. And then we are implementing thread. We are again getting the get minimum pool size from Kafka properties and get maximum pool size from Kafka properties. So over here we are implementing Java threads. Now let me quickly close this Kafka producer configuration where we are configuring our Kafka producer. Let's go back. Now let us quickly go to this API, which have event producer API.java file. So here we are basically creating a event producer API which has this dispatch function. So we'll use this dispatch function to send the records. So let me quickly close this file. Let's go back. We have already seen this config and configurations in which we are basically retrieving those values from application.yml file, and then we are setting the producer configurations. Then we have constants. So in Kafka constants.java, we have created this Kafka constant interface where we have specified the batch size, account limit, checksum limit, then read batch size, minimum balance, minimum account, maximum account. Then we are also implementing date time for matter. So we are specifying all the constants over here. Let me close this file. Let's go back. Then this is performance. So we'll not look at these two files, but let me tell you what does these two files do. These two files are basically to record the metrics of your Kafka, like time in which your 1,000 records have been produced in Kafka, or you can say time in which records are getting published to Kafka. It will be monitored, and then you can record those stats. So basically it helps in optimizing the performance of your Kafka producer, right? You can actually know how to tweak or how to adjust those configuration factors, and then you can see the difference, or you can actually monitor the stats and then understand how you can actually make your producer more efficient. So these are basically for those factors, but let's not worry about this right now. Let's go back. Next, let me quickly take you through this file utility. So you have file utility.java. So basically what we are doing over here, we are reading each record from the file using buffer reader. So over here you can see we have this list, and then we have buffered reader, then we have file reader. So first we are reading the file, and then we are trying to split each of the fields present in the record, and then we are setting the value of those fields over here. And then we are specifying some of the exceptions that may occur, like number format exception or parse exception. All those kind of exception we have specified over here, and then we are closing this. So in this file we are basically reading the records. Now let me close this. Let's go back. Now let's quickly look at the serializer. So this is custom JSON serializer. So in serializer, we have created a custom JSON serializer. Now this is basically to write the values as bytes. So the data which you will be passing will be written in bytes, because as we know that data is sent to Kafka in form of bytes, and this is the reason why we have created this custom JSON serializer. So now let me quickly close this. Let's go back. This file is basically for my Spring Boot web application. So let's not get into this. Let's look at event thread.java. So basically over here we have event producer API. So now we are trying to dispatch those events, and to show you how dispatch function works, let me go back, let me open services and event producer IMPL, that is implementation. So let me show you how this dispatch works. So basically over here what we are doing, first we are initializing. So using the file utility, we are basically reading the files, and to read the file we are getting the path using this Kafka properties object, and we are calling this getter method of file path. Then what we are doing, we are basically taking the product list and then we are trying to dispatch it. So in dispatch we are basically using Kafka producer, and then we are creating the object of the producer record. Then we are using the get topic from this Kafka properties. We are getting this transaction ID from the transaction, and then we are using event producer.send to send the data. And finally we are trying to monitor this, but let's not worry about the monitoring and cache and monitoring and stats part, so we can ignore this part. Let's quickly go back and look at the last file, which is producer. So let me show you this event producer. So what we are doing here, we are actually creating a logger. So in this on completion method, we are basically passing the record metadata, and if your E exception is not null, then it will basically throw an error saying this and recorded metadata. Else it will give you the sent message to topic, partition and offset, and then the record metadata and topic, and then it will give you all the details regarding topic, partitions and offsets. So I hope that you guys have understood how this Kafka producer is working. Now is the time we need to go ahead and we need to quickly execute this. So let me open a terminal over here. Now first, to build this project, we need to execute mvn clean install. This will install all the dependencies. So as you can see, our build is successful. So let me minimize this, and this target directory is created after you build a Maven project. So let me quickly go inside this target directory, and this is the root.war file, that is root.webarchive file, which we need to execute. So let's quickly go ahead and execute this file. But before this, to verify whether the data is getting produced in our Kafka topics, so for testing, as I already told you, we need to go ahead and we need to open a console consumer so that we can check that whether the data is getting published or not. So let me quickly minimize this. So let's quickly go to Kafka directory, and the command is /bin Kafka console consumer, and then hyphen bootstrap server. It's 9092. Okay, let me check the topic. What's the topic? Let's go to our application.yml file. So the topic name is transaction. Let me quickly minimize this, specify the topic name, and I'll hit enter. So now let me place this console aside, and now let's quickly go ahead and execute our project. So for that, the command is java-jar, and then we'll provide the path of the file, that is inside target, and the file is root.war, and here we go. So now you can see in the console consumer, the records are getting published, right? So there are multiple records which have been published in our transaction topic, and you can verify this using the console consumer. So this is where the developers use the console consumer. So now we have successfully verified our producer. So let me quickly go ahead and stop the producer. Let me stop consumer as well. Let's quickly minimize this. And now let's go to the second project, that is Spark Streaming Kafka Master. Again, we have specified all the dependencies that is required. Let me quickly show you those dependencies. Now again, you can see over here we have specified Java version. Then we have specified the artifacts, or you can see the dependencies. So we have Scala compiler, then we have Spark streaming, Kafka, then we have Kafka clients, then JSON data binding, then we have Maven compiler plugin. So all those dependencies which are required, we have specified over here. So let me quickly go ahead and close it. Let's quickly move to the source directory, main, then let's look at the resources again. So this is application.yml file. So we have port 8080, then we have bootstrap server over here, then we have brokers over here, then we have topic is as transaction, the group is transaction, partition count is 1, and then the file name. So we won't be using this file name. Then let me quickly go ahead and close this. Let's go back to Java directory, com spark demo. Then this is the model, so it's same. So these are all the fields that are there in the transaction. You have transaction date, product, price, payment type, then name, city, state, country, account created, and so on. And again, we have specified all the getter and setter methods over here. And similarly, again, we have created this transaction DTO constructor where we have taken all the parameters and then we are setting the values using this operator. Next, we are again overriding this toString function, and over here we are again returning the details like transaction date and then value of transaction date, product, and then value of product, and similarly all the fields. So let me quickly close this model. Let's go back. Let's look at Kafka first. Then we have serializer. So this is the JSON serializer which was there in our producer, and this is transaction decoder. Let's take a look. Now you have decoder, which is again implementing decoder, and we are passing this transaction DTO. Then again, you can see we have this from bytes method, which we are overriding, and we are reading the values using this bytes and then transaction DTO class. Again, if it is failing to pass, we are giving JSON processing failed for object this. And you can see we have this transaction decoder constructor over here. So let me quickly again close this file. Let's quickly go back. And now let's take a look at Spark Streaming app, where basically the data which the producer project will be producing to Kafka will be actually consumed by Spark Streaming application. So Spark Streaming will stream the data in real time and then will display the data. So in the Spark Streaming application, we are creating conf object, and then we are setting the application name as Kafka Sandbox. The master is local star. Then we have Java Spark context. So here we are specifying the Spark context, and then next we are specifying the Java streaming context. So this object will basically be used to take the streaming data. So we are passing this Java Spark context over here as a parameter, and then we are specifying the duration, that is 2000. Next we have Kafka parameters. So to connect to Kafka, you need to specify those parameters. So in Kafka parameters, we are specifying the meta broker list, that is localhost 9092. Then we have auto offset reset, that is smallest. Then in topics, the name of the topic from which we will be consuming messages is transaction. Next, Java, we're creating a Java pair input D streams. So basically this D stream is discrete stream, which is the basic abstraction of Spark streaming and is a continuous sequence of RDDs representing a continuous stream of data. Now D stream can either be created from live data, from Kafka, HDFS or Flume, or it can be generated from transforming existing D streams using operations. So over here we are again creating a Java input D stream. We are passing string and transaction DTOs parameters, and we are creating direct Kafka stream object. Then we are using this Kafka utils, and we are calling the method create direct stream, where we are passing the parameters as SSC, that is your Spark streaming context. Then you have string.class, which is basically your key serializer. Then transaction class, that is basically your value serializer. Then string decoder, that is to decode your key, and then transaction decoder, basically to decode your transaction. Then you have Kafka parameters, which you have created here, where you have specified broker list and auto offset reset. And then you are specifying the topics, which is your transaction. So next, using this Kafka D stream, you are actually continuously iterating over the RDD, and then you are trying to print your new RDD with then RDD partition and size, then RDD count and the record. So RDD for each record. So you are printing the record, and then you are starting the Spark streaming context, and then you are waiting for the termination. So this is the Spark streaming application. So let's first quickly go ahead and execute this application. Let me close this file. Let's go to the source. Now let me quickly go ahead and delete this target directory. So now let me quickly open the terminal, mvn clean install. So now as you can see, the target directory is again created, and this Spark streaming Kafka snapshot jar is created. So we need to execute this jar. So let me quickly go ahead and minimize it. Let me close this terminal. So now first I'll start this Spark streaming job. So the command is java-jar, and inside the target directory we have this Spark streaming Kafka jar. So let's hit enter. So let me now quickly go ahead and start producing messages. So I'll minimize this and I'll wait for the messages. So let me quickly close this Spark streaming job, and then I'll show you the consumed records. So you can see the record that is consumed from Spark streaming. So here you have got record and transaction DTO, and then transaction date, products, all the details which we have specified. You can see it over here. So this is how Spark streaming works with Kafka. Now it's just a basic job. Again, you can go ahead and you can take those transactions, you can perform some real-time analytics over there, and then you can go ahead and write those results. So over here we have just given you a basic demo in which we are producing the records to Kafka, and then using Spark streaming we are streaming those records from Kafka. Again, you can go ahead and you can perform multiple transformations over the data, multiple actions, and produce some real-time results using this data. So this is just a basic demo where we have shown you how to basically produce records to Kafka and then consume those records using Spark streaming. So let's quickly go back to our slide. Now, as this was a basic project, let me explain you one of the Kafka Spark streaming project, which is at Edureka. So basically there is a company called techreview.com. So this techreview.com basically provides reviews for your recent and different technologies like your smartwatches, phones, different operating systems, and anything new that is coming into market. So what happens is the company decide to include a new feature which will basically allow users to compare the popularity or trend of multiple technologies based on the Twitter feeds. And second, for the USP, they are basically trying this comparison to happen in real time. So basically they have assigned you this task so that you have to go ahead, you have to take the real-time Twitter feeds, then you have to show the real-time comparison of various technologies. So again, the company is asking you to identify the minutely trend between different technologies by consuming Twitter streams and writing aggregated minutely count to Cassandra, from where again a dashboarding team will come into picture, and then they will try to dashboard that data, and it can show you a graph where you can see how the trend of two different, or you can say various technologies are going ahead. Now the solution strategy which is there, so you have to continuously stream the data from Twitter, then you will be storing those tweets inside a Kafka topic. Then second, again you have to perform Spark streaming, So you will be continuously streaming that data, and then you will be applying some transformations which will basically give you the minute trend of the two technologies. And again, you will write it back to a Kafka topic. And at last, you'll write a consumer that will be consuming messages from the Kafka topic, and that will write the data in your Cassandra database. So first you have to write a program that will be consuming data from Twitter and write it to Kafka topic. Then you have to write a Spark streaming job, which will be continuously streaming that data from Kafka and perform analytics to identify the minutely trend. And then it will write the data back to a Kafka topic. And then you have to write the third job, which will be basically a consumer that will consume data from that Kafka topic and write the data to a Cassandra database.
In a world where data is being generated at an alarming rate, the correct analysis of the data at the correct time can be very useful. Now, one of the most amazing framework to handle big data in real time and perform analysis is Apache Spark. And if we talk about the programming languages being used nowadays for different purposes, I'm sure Python will top this chart as it is being used almost everywhere. So, talking about the features of Apache Spark, starting off with the most important feature, that is speed. It is almost 100 times faster than the traditional data processing tools and frameworks. It has powerful caching. The simple programming layer provides powerful caching and disk persistent capabilities. Now coming to deployment, Apache Spark can be deployed through Mesos or Hadoop via Yarn or via Spark's own cluster. The most important feature that helps Spark achieve the fast speed in real-time computation and low latency is the use of in-memory computation, the lazy evaluation of transformations, the didactic acyclic graphs, and much more. Now, Spark is polyglot, which means it can be programmed in various languages like Python, Scala, Java, and R. And it is one of the reasons why Apache Spark has taken over machine learning and exploratory analysis. Now, let's have a look at the various companies that use Apache Spark. Here we have Yahoo, Alibaba, Nokia, Netflix, NASA, Databricks, which is the official enterprise distributor of Apache Spark. We have TripAdvisor and we have eBay. So you can see Spark is being used in the industry a lot. Now let's have a look at the various industry use cases. First of all, starting with healthcare. As healthcare providers look for novel ways to enhance the quality of healthcare, Apache Spark is slowly becoming the heartbeat of many healthcare applications. Many healthcare providers are using Apache Spark to analyze patient records along with the past clinical data to identify which patients are likely to face health issues after being discharged from the clinic. This helps hospitals prevent hospital readmittance as they can deploy home healthcare services to the identified patient, saving on costs for both the hospitals and the patient. Apache Spark is used in genome sequencing to reduce the time needed to process genome data. It took several weeks to organize all the chemical compounds with genes, but now with Apache Spark on Hadoop, it just takes few hours. Now coming to finance, banks are using Apache Spark to access and analyze the social media profiles, call recordings, complaint logs, emails, the forum discussion to gain insights which can help them make right business decisions for credit risk assessment, targeted advertising, and customer segmentation. One of the financial institutions that has retail banking and brokerage operations is using Apache Spark to reduce its customer churn by 25%. The financial institution has divided the platforms between retail, banking, trading, and investment. However, the bank wants a 360-degree view of the customer regardless of whether it is a company or an individual. To get the consolidated view of the customer, the bank uses Apache Spark as the unifying layer. The Spark helps the bank automate analytics with the use of machine learning by accessing the data from each repository for the customers. Now talking about media, Apache Spark is used in the gaming industry to identify patterns from the real-time in-game events and respond to them to harvest lucrative business opportunities like target advertising, auto-adjustment of gaming levels based on complexity, player retention, and many more. Now Conviva is another company, averaging about 4 million videos per month. It uses Apache Spark to reduce customer churn by optimizing video streams and managing live video traffic, thus maintaining a consistently smooth, high-quality viewing experience. Now you all might have heard about Netflix. Netflix uses Apache Spark for real-time stream processing to provide online recommendation to its customer. Streaming devices at Netflix send events which capture all member activities and play a vital role in personalization. It processes 450 billion events per day, which flow to the server-side application and are then directed to Apache Kafka. Now coming to the retail and e-commerce industry, one of the largest e-commerce platform, Alibaba, runs some of the largest Apache Spark shops in the world. in order to analyze hundreds of petabytes of data on its e-commerce platform. Some of the Spark jobs that perform feature extraction on image data run for several weeks. Millions of merchants and users interact with Alibaba e-commerce platform. Each of this interaction is represented as a complicated large graph, and Apache Spark is used for fast processing of sophisticated machine learning on this data. Now, eBay also uses Apache Spark to provide targeted offers, enhance customer experience, and optimize overall performance. Apache Spark is leveraged at eBay through Hadoop Yarn. Yarn manages all the clusters resources to run the generic tasks, and eBay Spark users leverage the Hadoop cluster in the range of 2000 nodes, 20,000 cores, and 100 TB of RAM through Yarn. Now, finally, coming to the travel industry, TripAdvisor, a leading travel website that helps plan a perfect trip, is using Apache Spark to speed up its personalized customer recommendation. TripAdvisor uses Apache Spark to provide advice to millions of travelers by comparing hundreds of websites to find the best hotel prices for its customers. The time taken to read and process the reviews of the hotels in a readable format is done with the help of Apache Spark. Now we all know Uber. Every day, this multinational online taxi dispatch company gathers terabytes of event data from its mobile users. By using Kafka, Spark Streaming, and HDFS to build a continuous ETL pipeline, Uber can convert unstructured event data into structured data as it is collected, and then use it for further and more complex analysis. So, as I was talking about Spark being a polyglot earlier, it basically means that programming in Spark can be done in various languages like Scala, Python, and R. Now you may ask which one should I go or choose to begin with. So Spark was developed in Scala, that you should know. It was the default language in which Spark was developed. It is very similar to Java. But the recent emergence of data analytics and machine learning has made it difficult for Scala to keep up. So instead, Spark came up with a Python API to use Python. So let's have a look at the reasons why one should go for Python to begin with. Firstly, it is easy to learn. For programmers, Python is comparatively easy to learn because of its syntax and standard libraries. Moreover, it is dynamically typed language, which means RDDs can hold objects of multiple types. Now we'll discuss more about RDDs coming up in this video. Now it's portable and it can be used with various operating systems like Windows, Solaris, Linux, we have the BEOS, PlayStation, and the macOS. And lastly, Scala does not have sufficient data science tools and libraries like Python for machine learning and natural language processing. Spark Mlib, the machine learning library, has only fewer ML algorithms, but they are ideal for big data processing. In summary, we can say that Scala lacks good visualization and local data transformation tools along with highly used machine learning libraries. Now, Edureka, as we know, provide a detailed and comprehensive training on Apache Spark in Python, that is the PySpark Developer Certification Training. Now, this course is designed to provide knowledge and skills to become a successful Spark developer using Python. You will get in-depth knowledge of concepts such as Hadoop distributed file system, the Hadoop cluster, Flume, Scoop, Apache Kafka. You'll learn about the APIs and the libraries which Spark offers, such as Spark Streaming, Mlib, Spark SQL. And this PySpark developer course is an integral part of a big data developer's career path. This course is designed to provide knowledge and skills to become a successful Hadoop and Spark developer and would help to clear the Spark and Hadoop developer, which is the CCA 175 examination. This course has in total 12 modules with one bonus module, and it focuses on Cloud Era's Hadoop and Spark Developer Certification Training. Now coming to Module 1, which is the Introduction to Big Data, Hadoop and Spark. In this module, you will understand big data, the limitation of existing solutions for big data problems, how Hadoop solves the big data problem, the Hadoop ecosystem, Hadoop architecture, SDFS, rack awareness, and replication. You will learn about the Hadoop cluster architecture, important configuration files in Hadoop cluster, and you will also get an introduction to Spark, why it is used, and understanding the difference between batch processing and real-time processing. Now coming to Module 2, which is Introduction to Python for Apache Spark. At the end of this module, you will be able to define Python, understand operands and expressions. You will be able to write your first Python program, understand command line parameters and flow control. You will understand how to take an input from the user and perform operations on it. And you'll also learn about numbers, strings, tuples, lists, dictionaries, and sets. Now coming to Module 3, which is basically the functions, oops, modules, error, and exceptions in Python. In this module, you will learn how to create generic Python scripts, how to address the errors and exceptions in the code, and finally how to extract and filter content using the regex. Now Module 4 is deep dive into Apache Spark framework. In this module, you will understand Apache Spark in depth, and you will also learn about the various Spark components. You will be creating and running various Spark applications, and at the end, you will learn how to perform data ingestion using Scoop. Now coming to Module 5, which is playing with Spark RDDs. In this module, you will learn about Spark RDDs, which are the resilient distributed datasets, and other RDD-related manipulations for implementing business logistics, like the transformations, actions, and the functions performed on RDD. Moving on to Module 6, which is the DataFrames and Spark SQL. In this module, you will learn about Spark SQL, which is used to process structured data with SQL queries. You will learn about the data frames and the data sets in Spark SQL, along with different kinds of SQL operations performed on the data frames. You will also learn about the Spark and Hive integration. Now, Module 7, which is machine learning using Spark Mlib. In this module, you will learn about why machine learning is needed, different machine learning techniques and algorithms, and their implementation using the Spark Mlib. Now, 8th module is deep dive into Spark Mlib. In this module, you will be implementing various algorithms supported by a machine learning library, which is the Mlib, such as linear regression, decision tree, random forest, and many more. Now coming to Module 9, which is understanding Apache Kafka and Apache Flume. In this module, you will understand Kafka and Kafka architecture. Afterwards, you will go through the details of Kafka cluster, and you will also learn how to configure different types of Kafka cluster. At last, you will see how messages are produced and consumed using Kafka APIs in Java. You will also get an introduction to Apache Flume, its basic architecture, and how it is integrated with Apache Kafka for event processing. Now, Module 10 is Apache Spark Streaming. In this module, you will work on Apache Spark Streaming, which is used to build scalable, fault-tolerant streaming application. You will learn about these streams and the various transformations performed on the streaming data. You will get to know about commonly used streaming operators such as sliding window operator and the stateful operators. Now, Module 11 is Apache Spark Streaming Data Sources. In this module, you will learn about the different streaming data sources such as Kafka and Flume. And at the end of this module, you will also be able to create a Spark streaming application. Now, Module 12 is the in-class project. Now, this project will comprise of all that we have learned till now. That is Hadoop, Spark, Kafka, Flume, and much more. And as a bonus, we have another module, which is the GraphX. In this module, you will be learning the key concepts of Spark GraphX, programming concepts, and operations along with the different GraphX algorithms and their implementations. Now that we have seen the training structure offered by Edureka, let's understand what exactly PySpark is. Now, Apache Spark is an open source cluster computing framework for real-time processing developed by Apache Spark Foundation. And PySpark is nothing but the Python API for Apache Spark. Now let's have a look at the various components of the Spark ecosystem. The core engine of the entire Spark framework provides utilities and architecture for other components. Spark Streaming enables analytical and interactive apps for live streaming data. The Mlib, which is machine learning library of Spark, it is built on top of Spark to support the various machine learning algorithms. GraphX, computational engine, which is similar to Graph, combines data parallel and graph parallel concepts. Spark R is the package for R language to enable R user to leverage Spark power from the R shell. Now finally, we have the PySpark, the API developed to support Python as a programming language for Spark. Now, PySpark shell links the Python API to the Spark core and initializes the Spark context. The Spark context is the heart of any Spark application. Spark context sets up internal services and establishes a connection to a Spark execution environment. The Spark context object in the driver program coordinates all the distributed processes and allows resource allocation. The cluster managers provides executors, which are JVM processes with logic. Spark context object sends the application to the executors, and then Spark context executes these tasks in each executors. Now, when you have installed Spark on your system, just by typing PySpark, you can enter the Spark shell, and it looks something like this. Just make sure that all the daemons of Spark are running in the background. So guys, looking at the system requirements. So guys, here I'll be explaining you the minimum system requirements. So the minimum RAM required is around 4 GB, but is advised to use an 8 GB RAM system. And minimum free disk space should be 25 GB, at least 25 GB. Now the minimum processor should be i3 or above to have a smooth programming experience. And most of all, the system should have a 64-bit operating system. And in case if you are using a virtual machine or the virtual box, and it should also support a 64-bit image of the operating system. Now these are all the hardware requirements. So coming at the software requirements, we need Java 8 or above. We need Hadoop 2.7 or above, as Spark runs on top of Hadoop. We need pip with version 10. Pip is a package management system used to install and manage software packages written in Python. You can use Conda as well. And finally, we need the Jupyter Notebook. This step is optional, but the programming experience in Jupyter Notebook is far more better than the shell. So let's go ahead and see how we can install PySpark on our systems. So here I have a Windows system, and in order to install PySpark, I'm using a virtual box, and I'll create a virtual machine inside the virtual box because most of the time PySpark is being used in the Linux environment. So that's what I'm going to use. So let's see how we can install the VirtualBox. All you need to do is go to the official website of VirtualBox, and on the download section, you'll find the latest version of VirtualBox. You need to click on the Windows host or Linux distribution. But if you have Linux, you don't need the VirtualBox. So for the Windows, you can click on this one and install. So I've already installed VirtualBox and I've created my VM. Now this VM has CentOS 7 as the base image, and now CentOS is Red Hat distribution operating system, so it also works on the Linux platform. Now firstly, what we need to do is check whether we have Hadoop or Java installed or not. So for that, we need to check the .bash rc file. Now the bash rc file contains the path to all the frameworks that are being used. So for example, as you can see, we have Hadoop installed on our system. We have all the path to the Hadoop. We have Java installed. So we can also check the Hadoop version which we are running. So as you can see, we have Hadoop 2.7.3. And to check the Java version, we need to type version. We have Java 8 running on the system. So now that we have Hadoop and Java installed in our system, we need to install Spark. To install Spark, we need to go to the Apache official website, and in that you need to go to spark.apache.org and /downloads. There you can select which version of Spark you want, the stable version. So the latest version here is of June 8, 2018, and it is pre-built for Apache Hadoop 2.7 and later versions. So as we saw earlier, we have Hadoop 2.7.3, so that's good. Now to download Apache Spark, you need to click on this link, and here you'll get various mirror sites and links from where you can download the tar file. So I've already downloaded it, so let me show you guys. So guys, as you can see here, it's a TGZ file, which is a tar file. Now we need to extract this file and place it in our specific location where we want. Let me just close this first. Now for that, first we need to go to downloads. As you can see, we have the Spark 2.3.1, Hadoop 2.7 TGZ. Now we need to untar this file. So we use the command tar-xvcf and Spark 2.3.1 name. So what it'll do, it will extract it, or I'd rather say untar the file in the download section. So now if we look at the elements, list the elements, we can see we have Spark 2.3.1 bin Hadoop 2.7, and we have the tar file also. So what we need to do is move this to any specified location where we want our frameworks to be. So what I usually do is keep all my frameworks like Hadoop, Spark, Kafka, we have Flume or Cassandra in my user library section. So the USR, LIB, as you can see, I have Cassandra, Flume, Hive, Maven, Storm, and here I have copied Spark. So now that we have copied Spark to a specific location, we need to put in its path in the bash rc file as well. So let me again open the bash rc file. So guys, as you can see here, I've put in the path for Apache Spark. So there are two paths you need to configure here, which is Spark Home and the path. Spark Home has the path for where Spark has been shifted after it has been untarred, or rather say extracted from the tar file. And we need to also provide the path of the bin folder, which resides inside the Spark folder as well. So after we have mentioned the path in the .bashrc file, we need to type in source and then .bashrc. So what happens is the moment when we add the path of a particular framework or any application in our bashrc file, it is not saved. So in order to save it, we use the command source.bashrc. So now in order to move to Spark, we just use cd and we use a $sign and we write Spark home. We are inside Spark. Now if we have a look at the elements inside Spark, we find there's a Python folder. If we go inside Python, here you can see we have all the different libraries and the set of files which are used to run PySpark, and there's a PySpark folder too. And inside here we have various libraries for which Python is being used and the various programs also. So now that you have installed Spark and mentioned its path in the bashrc file, now it's time to install Jupyter Notebook as well. So to install Jupyter Notebook, first we need to install pip or conda. As I mentioned earlier, pip, it's a package management system and it's used to install and manage software packages. So this is the command to install pip. Now make sure that the pip version is 10 or above to install the Jupyter Notebook. Now in order to install Jupyter after we have installed pip, we use the command pip install Jupyter. Now this will install the Jupyter Notebook in our system. And after it's been installed, if we need to use the Jupyter Notebook, we just type the Jupyter Notebook in our command line. And what it will do, it will open the Jupyter Notebook for us. So as you can see here in the news section, we have the Python 2. So we'll use this while writing programs for PySpark. Now one thing to keep in mind is that we have the Jupyter Notebook here and we have PySpark, but Jupyter and PySpark are not communicating in between. Now to make that happen, we need to again go to the bashrc file. And once we have given the path for Spark, we need to provide the path for PySpark driver, which is Jupyter Notebook as well. So one more important thing to note is if you are using Spark for Scala, you need to provide the path for Scala as well. And for using Jupyter Notebook, all you need to do is put in these two lines of codes, which is PySpark driver, Python, which is Jupyter, and the driver Python options, which is Notebook. Now that we have Spark installed, let's run Spark. For that, we need to go into the Spark home, and inside that we use the command /sbin /start-all.sh. Now what it'll do, it will start the master and the worker. But if you want to start the master separately and the worker separately, you can use start-master.sh and start-slave.sh. But generally I use start-all.sh as it starts both the master and the worker nodes. Okay, so now to check whether Spark is running or not, we use the command jps. As you can see here, we have master and worker running along with Hadoop's resource manager, name node, secondary name node, node manager, jps, and the data node. Now one more important thing is that after you have made changes to the .bashrc file, again you need to go to the command line and type in source.bashrc. That will save the path of the notebook as well as PySpark. So as you'll see here, the moment I type PySpark and press enter, PySpark starts running and I'm redirected to the Jupyter Notebook. Now what happens is that this Jupyter Notebook is communicating with the PySpark environment. So what we can do is go to Python 2, we'll create a new notebook, and we can start writing our programs here as well. But it ultimately comes to your choice whether you want to do all the programming in shell or you want to continue doing it in the Jupyter Notebook. Personally, I find Jupyter Notebook easy to work with as you have various options here to cut, copy, insert, stop the kernel, and much more. So let's see whether this workbook works or not. So here I'm creating an RDD, which are resilient distributed datasets, which are a key concept in PySpark. So as you can see, the star mark here shows us the process is being done in the background. And if I have a look at the RDD which I just created, as you can see, PySpark shell is absolutely working fine. So as you can see here in the shell, here we have the notebook app open, and it shows us some messages which are related to the notebook. As you can see, the last message is saving file at untitled.ipynb, which is the extension for a PySpark Jupyter notebook. So this is it, guys. I hope you understood how to install PySpark in your system, what all are the dependencies required, the hardware and the software requirements. Now keep in mind that you can use the Jupyter extension. It's an optional step. If you want to do all the programming in the shell itself, then no need of the Jupyter. But yeah, Jupyter adds a certain level of sophistication to the programming.
So let's take the first question and look into the answer, like how commonly this is covered. What is Apache Spark? And Spark, it's with Apache Foundation now. It's an open source, it's a cluster computing framework for real-time processing. So three main keywords over here. Apache Spark, it's an open source project. It's used for cluster computing and for in-memory processing. Along with real-time processing, it's going to support in-memory computing. So there are lots of projects which supports cluster computing. Along with that, Spark differentiates itself by doing the in-memory computing. It's a very active community, and out of the Hadoop ecosystem technologies, Apache Spark is very active. Multiple releases we got last year. It's a very active project among the Apache projects. Basically, it's a framework going to support in-memory computing and cluster computing. And you may face this specific question, how Spark is different than MapReduce, or how you can compare it with the MapReduce. MapReduce is the processing methodology within the Hadoop ecosystem, and within Hadoop ecosystem we have HDFS, Hadoop Distributed File System. MapReduce going to support distributed computing, and how Spark is different. So how we can compare Spark with the MapReduce. In a way, this comparison going to help us to understand the technology better, but definitely like we cannot compare these two or two different methodologies by which it's going to work. Spark is very simple to program, but MapReduce, there is no abstraction, or the sense like all the implementations we have to provide. And interactivity, it has an interactive mode to work with in Spark. In MapReduce, there is no interactive mode. There are some components like Apache Pig and Hive, which facilitates us to do the interactive computing or interactive programming. And Spark supports real-time stream processing. And to precisely say, within Spark, the stream processing is called near real-time processing. There's nothing in the world is real-time processing. It's near real-time processing. It's going to do the processing in micro batches. I'll cover in detail when we are moving on to the streaming concept. I am going to do the batch processing on the historical data in MapReduce. When I say stream processing, I'll get the data that is getting processed in real time and do the processing and get the result, either store it or publish it to public community. We will be doing it. Latency wise, MapReduce will have very high latency because it has to read the data from hard disk. But Spark, it will have very low latency because it can reprocess or use the data already cached in memory. But there's a small catch over here. In Spark, first time when the data gets loaded, it has to read it from the hard disk, same as MapReduce. So once it is read, it will be there in the memory. So Spark is good whenever we need to do iterative computing. So Spark, whenever you do iterative computing, again and again do the processing on the same data, especially in machine learning, deep learning, all we will be using the iterative computing. Here Spark's performance much better. You will see the Spark performance improvement 100 times faster than MapReduce. But if it is one-time processing and fire and forget, that type of processing, Spark, relatively it may be the same latency you will be getting it than MapReduce, maybe like some improvements because of the building block of Spark, that's the RDD. We may get some additional advantage. So that's the key feature or the key comparison factor of Spark and MapReduce. Now let's get on to the key features. Explain key features of Spark. We discussed about the speed and performance. It's going to use the in-memory computing. So speed and performance wise, it's going to much better when we do iterative computing. And it's a polyglot in the sense The programming language to be used with the Spark, it can be any of these languages. It can be Python, Java, R, or Scala. We can do programming with any of these languages. And data formats to give us an input, we can give any data formats like JSON, Parquet, any data formats we can give that as an input. And the key selling point with the Spark is its lazy evaluation. In the sense, it's going to calculate the DAG cycle, directed acyclic graph, DAG, we call that as a DAG. It's going to calculate what all steps needs to be executed to achieve the final result. So we need to give all the steps as well as what final result I want. It's going to calculate the optimal cycle or optimal calculation, what all steps needs to be calculated or what all steps needs to be executed. Only those steps it will be executing it. So basically it's a lazy execution. Only if the results needs to be processed, it will be processing that specific result. And it supports real-time computing. It's through Spark Streaming. There is a component called Spark Streaming which supports real-time computing. And it gels with Hadoop ecosystem very well. It can run on top of Hadoop Yarn, or it can leverage the HDFS to do the processing. So when it leverages the HDFS, the Hadoop cluster container can be used to do the distributed computing, as well as it can leverage the resource manager to manage the resources. So Spark can gel with the HDFS very well, as well as it can leverage the resource manager to share the resources, as well as data locality it can leverage. Data locality, it can do the processing near to the data where data is located within the HDFS. And it has a fleet of machine learning algorithms already implemented, right from clustering, classification, regression, all those logic already implemented. And machine learning, it's achieved using Mlib within Spark. And there is a component called GraphX, which supports graph theory. So we can solve the problems using graph theory, using the component GraphX within the Spark. So these are the things we can consider as the key features of Spark. So when you discuss with the installation of the Spark, you may come across this yarn. What is yarn? Do you need to install Spark on all nodes of yarn cluster? So yarn is nothing but yet another resource negotiator. That's the resource manager within the Hadoop ecosystem. So that's going to provide the resource management platform. Yarn going to provide the resource management platform across all the clusters. And Spark, it's going to provide the data processing. So wherever the resource being used, that location, the Spark will be used to do the data processing. And of course, yes, we need to have Spark installed on all the nodes where Spark clusters are located. That's basically we need those libraries. And additional to the installation of Spark in all the worker nodes, we need to increase the RAM capacity on the worker machines as well. Your Spark going to consume huge amount of memory to do the processing. It will not do the MapReduce way of working. Internally, it's going to generate the DAG cycle and do the processing on top of Yarn. So Yarn at the high level, it's like resource manager or like an operating system for the distributed computing. It's going to coordinate all the resource management across the fleet of servers. On top of it, I can have multiple components like Spark, Daze, Giraffe. So Spark, especially, it's going to help us to achieve in-memory computing. So Spark Yarn is nothing but it's a resource manager to manage the resource across the cluster. On top of it, we can have Spark. And yes, we need to have Spark installed in all the nodes where the Spark Yarn cluster is used. And also additional to that, we need to have the memory increased in all the worker nodes. So next question was like this: what file system does Spark support? When I say file system, when we work in an individual system, we will be having a file system to work within that particular operating system. But in a distributed cluster or in a distributed architecture, we need a file system where we can store the data in a distributed mechanism. Hadoop comes with a file system called HDFS. It's called Hadoop Distributed File System, where data gets distributed across multiple systems, and it will be coordinated by two different type of components called name node and data node. And Spark, it can use this HDFS directly. So you can have any files in HDFS and start using it within the Spark ecosystem. And it gives another advantage of data locality. When it does the distributed processing, wherever the data is distributed, the processing could be done locally to that particular machine where data is located. And to start with, as a standalone mode, you can use the local file system as well. So this could be used especially when we are doing the development or any POC, we can use the local file system. And Amazon Cloud provides another file system called S3. simple storage service. We call that as the S3. It's a block storage service. This can also be leveraged or used within Spark for the storage. And lot other file system also it supports. There are some file systems like Alexo, which provides in-memory storage. So we can leverage that particular file system as well. So we have seen all features, what all functionalities available within Spark. We are going to look at the limitations of using Spark. Of course, every component, when it comes with a huge power and advantage, it will have its own limitations as well. So the next question illustrates some limitations of using Spark. Spark utilizes more storage space compared to Hadoop. When it comes to the installation, it's going to consume more space. But in the big data world, that's not a very huge constraint because storage cost is not very great or very high in big data space. A developer needs to be careful while running the apps in Spark. The reason because it uses in-memory computing. Of course, it handles the memory very well, but if you try to load a huge amount of data in the distributed environment, and if you try to do join, when you try to do join in the distributed world, the data going to get transferred over the network. Network is really a costly resource. So the plan or design should be such a way to reduce or minimize the data transfer over the network. And however the way possible, with all possible means, we should facilitate distribution of the data over multiple machines. The more we distribute, the more parallelism we can achieve and the more results we can get. And cost efficiency, if you try to compare the cost, how much cost involved to do a particular processing, take any unit in terms of processing 1 GB of data with say like 5 iterative processing. If you compare cost wise, in-memory computing always it's costlier because memory it's relatively costlier than the storage. So that may act like a bottleneck and we cannot increase the memory capacity of the machine beyond some limit. So we have to grow horizontally. So when we have the data distributed in memory across the cluster, of course the network transfer, all those bottlenecks will come into picture. So we have to strike the right balance, which will help us to achieve the in-memory computing. Whatever the in-memory computing required, it will help us to achieve. And it consumes huge amount of data processing compared to Hadoop. And Spark, it performs better when user does iterative computing. Because like for both Spark and the other technologies, it has to read data for the first time from the hard disk or from other data source. And Spark performance is really better when it reads the data or does the processing when the data is available in the cache. Of course, yes, the DAG cycle, it's going to give us a lot of advantage while doing the processing. But the in-memory computing processing, that's going to give us lots of leverage. The next question lists some use cases where Spark outperforms Hadoop in processing. The first thing is the real-time processing. Hadoop cannot handle real-time processing, but Spark can handle real-time processing. So any data that's coming in the Lambda architecture, you will have 3 layers. And most of the big data projects will be in the Lambda architecture. You will have a speed layer, batch layer, and service layer. And the speed layer, whenever the data comes in, that needs to be processed, stored, and handled. So in those type of real-time processing, Spark is the best fit. Of course, within Hadoop ecosystem, we have other components which does the real-time processing like Storm. But when you want to leverage the machine learning along with the Spark streaming on such computation, Spark will be much better. So that's why like when you have architecture like a Lambda architecture, you want to have all 3 layers, batch layer, speed layer, and service layer. Spark can gel the speed layer and service layer far better, and it's going to provide a better performance. And whenever you do the batch processing, especially like doing a machine learning processing, we will leverage the iterative computing and can perform 100 times faster than Hadoop. The more the iterative processing that we do, the more data will be read from the memory, and it's going to get us a much faster performance than Hadoop MapReduce. So again, remember, whenever you do the processing only once, so you're going to do the processing only once, read, process it, and deliver the result. Spark may not be the best fit. That can be done with the MapReduce itself. And there is another component called Akka. It's a messaging system or message coordinating system. Spark internally uses Akka for scheduling or any task that needs to be assigned by the master to the worker and a follow-up of that particular task by the master. Basically asynchronous coordination system, and that's achieved using Akka. Akka programming internally it's used by the Spark. As such, for the developers, we don't need to worry about Akka programming. Of course, we can leverage it, but Akka is used internally by the Spark for scheduling and coordination between master and the worker. And within Spark, we have a few major components. Let's see what are the major components of Apache Spark. They name the components of Spark ecosystem. Spark comes with a core engine, so that has the core functionalities of what is required by the Spark or for the Spark. RDDs are the building blocks of the Spark core engine. On top of Spark core, the basic functionalities of file interaction, file system, coordination, all that's done by the Spark core engine. On top of Spark core engine, we have a number of other offerings to do machine learning, to do graph computing, to do streaming. We have a number of other components. So the majorly used components are these components like Spark SQL, Spark Streaming, Mlib, GraphX, and Spark R. At the high level, we will see what are these components. Spark SQL, especially, it's designed to do the processing against a structured data. So we can write SQL queries and we can handle or we can do the processing. So it's going to give us the interface to interact with the data, especially structured data, and the language that we can use. It's more similar to what we use within the SQL. I can say 99% it's same. And most of the commonly used functionalities within the SQL have been implemented within Spark SQL. And Spark Streaming is going to support the stream processing. That's the offering available to handle the stream processing. And Mlib is the offering to handle machine learning. So the component name is called Mlib, and it has a list of components, a list of machine learning algorithms already defined. We can leverage and use any of those machine learning algorithms. GraphX, again, it's a graph processing offerings within the Spark. It's going to support us to achieve graph computing against the data that we have, like page rank calculation, how many connected entities, how many triangles, all those going to provide us a meaning to that particular data. And Spark R is the component that's going to interact or help us to leverage the language R within the Spark environment. R is a statistical programming language where we can do statistical computing within the Spark environment, and we can leverage R language by using the Spark R to get that executed within the Spark environment. Additional to that, there are other components as well, like approximate database, it's called a BlinkDB, all other things like in beta stage. So these are the majorly used components within Spark. So next question, how can Spark be used alongside Hadoop? So when we say Spark performance much better, it's not a replacement to Hadoop. It's going to coexist with the Hadoop. So it's leveraging the Spark and Hadoop together. It's going to help us to achieve the best result. Yes, Spark can do in-memory computing or can handle the speed layer. And Hadoop comes with the resource manager. So we can leverage the resource manager of Hadoop to make Spark to work. And few processing, we don't need to leverage the in-memory computing. For example, one-time processing, do the processing and forget, or just store it. We can use MapReduce. So the processing cost or computing cost will be much less compared to Spark. So we can amalgamize and strike the right balance between the batch processing and stream processing when we have Spark along with Hadoop. So let's have some detailed question related to Spark core. Within Spark core, as I mentioned earlier, the core building block of Spark core is RDD, Resilient Distributed Dataset. It's a virtual, it's not a physical entity, it's a logical entity. You will not see this RDDs existing. The existence of RDD will come into picture when you take some action. So this RDD will be used or referred to create the DAG cycle, and RDDs will be optimized to transform from one form to another form, to make a plan how the data set needs to be transformed from one structure to another structure. And finally, when you take some against an RDD, the existence of the data structure, the resultant data will come into picture, and that can be stored in any file system, either HDFS, S3, or any other file system can be stored. And RDDs can exist in a partitioned form, in the sense it can get distributed across multiple systems. And it's fault tolerant. When I say fault tolerant, if any of the RDD is lost, any partition of the RDD is lost, it can regenerate only that specific partition it can regenerate. So that's the huge advantage of RDD. So if someone asks like what's the huge advantage of RDD, it's a fault tolerant where it can regenerate the last RDDs and it can exist in a distributed fashion and it is immutable. So since once the RDD is defined or like created, it cannot be changed. The next question is, how do we create RDDs in Spark? There are two ways we can create the RDDs. One is using the Spark context. We can use any of the collections that's available within the Scala or in the Java, and using the parallelize function, we can create the RDD. And it's going to use the underlying file systems distribution mechanism. If the data is located in a distributed file system like HDFS, it will leverage that and it will make those RDDs available in a number of systems. So it's going to leverage and follow the same distribution in RDD as well. Or we can create the RDD by loading the data from external sources as well, like HBase. Generally, HDFS we may not consider as an external source. It will be considered as a file system of Hadoop. So when Spark is working with Hadoop, mostly the file system we will be using will be the HDFS. So we can read from HBase, or even we can read from other sources like Parquet file or from S3, different sources, Avro, we can read and create the RDD. Okay. Next question is, what is executor memory in Spark application? So every Spark application will have a fixed heap size and fixed number of cores for the Spark executor. Executor is nothing but the execution unit available in every machine, and that's going to facilitate to do the processing, to do the task in the worker machine. So irrespective of whether you use Yarn, Resource Manager, or any other mesos like Resource Manager, every worker machine we will have one executor, and within the executor the task will be handled. And the memory to be allocated for that particular executor is what we define as the heap size, and we can define how much amount of memory should be used for that particular executor within the worker machine, as well as number of cores can be used within the executor or by the executor within the Spark application, and that can be controlled through the configuration files of Spark. Next question is, define partitions in Apache Spark. So any data, irrespective of whether it is small data or larger data, we can divide those data sets across multiple systems. The process of dividing the data into multiple pieces and making it to store across multiple systems as a different logical units is called partitioning. So in simple terms, partitioning is nothing but the process of dividing the data and storing in multiple systems is called partitions. And by default, the conversion of the data into RDD will happen in the system where the partition is existing. So the more the partition, the more parallelism we are going to get. At the same time, we have to be careful not to trigger huge amount of network data transfer as well. And every RDD can be partitioned within Spark. And the partitioning going to help us to achieve parallelism. More the partition that we have, more distributions can be done. And the key thing about the success of the Spark program is minimizing the network traffic while doing the parallel processing and minimizing the data transfer within the systems of Spark. What operations does RDD support? So I can operate multiple operations against the RDD. So there are two types of things we can do. We can group it into two. One is transformations. In transformations, RDD will get transformed from one form to another form. Say like filtering, grouping, all that is like it's going to get transformed from one form to another form. One small example like reduce by key, filter, all that will be transformations. The resultant of the transformation will be another RDD. At the same time, we can take some actions against the RDD that's going to give us the final result. I can say count how many records are there, or store that result into the HDFS. They all are actions. So multiple actions can be taken against the RDD. So the existence of the data will come into picture only if I take some action against the RDD. Okay, next question. What do you understand by transformations in Spark? So transformations are nothing but functions. Mostly it will be higher order functions. Within Scala, we have something like a higher order functions, which will be applied against that RDD. Mostly against the list of elements that we have within the RDD, that function will get applied. But the existence of the RDD will come into picture only if we take some action against it. In this particular example, I am reading the file and having it within the RDD called raw data. Then I am doing some transformation using a map. So it's going to apply a function. So within map, I have some function which will split each record using the tab. So the split with the tab will be applied against each record within the raw data. And the resultant movies data will again be another RDD. But of course, this will be a lazy operation. The existence of movies data will come into picture only if it takes some action against it, like count or print or store. Only those actions will generate the data. So next question, define functions of Spark core. So that's going to take care of the memory management and fault tolerance of RDDs. It's going to help us to schedule, distribute the task and manage the jobs running within the cluster. And so going to help us to store the data in the storage system as well as read the data from the storage system. That's to do the file system level operations. It's going to help us. And Spark core programming can be done in any of these languages like Java, Scala, Python, as well as using R. So core is at the horizontal level. On top of Spark core, we can have a number of components. And there are different type of RDDs available. One such special type is pair RDD. So next question, what do you understand by pair RDD? So it's going to exist in pairs as a keys and values. So I can do some special functions within the pair RDDs or special transformations, like collect all the values corresponding to the same key, like sort and shuffle. What happens within the sort and shuffle of Hadoop? Those type of operations, like you want to consolidate or group all the values corresponding to the same key, or apply some functions against all the values corresponding to the same key. Like I want to get the sum of the value of all the keys. We can use the pair RDD and get that achieved. So it's going to, the data within the RDD going to exist in pairs, keys and values. Right. Okay. Question from Jason. What are vector RDDs? In machine learning, you will have a huge amount of processing handled by vectors and matrices. And we do lots of operations, vector operations like effective vector or transforming any data into a vector form. So vectors, like as the normal way, it will have a direction and magnitude. So we can do some operations like sum two vectors and what is the difference between the vector A and B as well as A and C. If the difference between vector A and B is less compared to A and C, we can say the vector A and B is somewhat similar, okay, in terms of features. So the vector RDD will be used to represent the vector directly, and that will be used extensively while doing the machine learning. Yeah, Jason, thank you. And there's another question, what is RDD lineage? So here, any data processing, any transformations that we do, it maintains something called a lineage. So how data is getting transformed? When the data is available in a partitioned form in multiple systems, and when we do the transformation, it will undergo multiple steps. And in the distributed world, it's very common to have failures of machines or machines going out of the network. And the system or framework, as such, it should be in a position to handle. Spark handles it through RDD lineage. So it can restore the last partition only. Assume like out of 10 machines, data is distributed across 5 machines. Out of that, those 5 machines, 1 machine is lost. So whatever the latest transformation that had that data for that particular partition, the partition in the last machine alone can be regenerated. And it knows how to regenerate that data or how to get that resultant data using the concept of RDD lineage. So from which data source it got generated, what was its prior step, so the complete lineage will be available. And it's maintained by the Spark framework internally. We call that as RDD lineage. What is Spark driver? To put it simply for those who are from Hadoop background, Yarn background, we can compare this to AppMaster. Every application will have a Spark driver that will have a Spark context which is going to coordinate the complete execution of the job. That will connect to the Spark master and delivers the RDD graph, that is the lineage, to the master, and coordinate the tasks, whatever the task that gets executed in the distributed environment. It can do the parallel processing, do the transformations and actions against the RDD. So it's a single point of contact for that specific application. So Spark driver is a short-lived, and the Spark context within the Spark driver is going to be the coordinator between the master and the tasks that are running. And Spark driver can get started in any of the executor within Spark. Okay. Name types of cluster managers in Spark. So whenever you have a group of machines, you need a manager to manage the resources. There are different type of cluster manager. Already we have seen the Yarn, yet another resource negotiator, which manages the resources of Hadoop. On top of Yarn, we can make Spark to work. Sometimes I may want to have Spark alone in my organization and not along with the Hadoop or any other technology, then I can go with the standalone. Spark has built-in cluster manager. So only Spark can get executed in multiple systems. But generally, if we have a cluster, we will try to leverage various other computing platforms or computing frameworks like graph processing, Giraffe, These, all that we will try to leverage. In that case, we will go with Yarn or some generalized resource manager like Mesos. Yarn is very specific to Hadoop and it comes along with Hadoop. Mesos is a cluster level resource manager. When I have multiple clusters within an organization, then I can use Mesos. Mesos is also a resource manager. It's a separate top level project within Apache. Next question, what do you understand by worker node? So in a cluster, in a distributed environment, we will have n number of workers. We call that as a worker node or a slave node, which does the actual processing. Going to get the data, do the processing and get us the result. And master node going to assign what task to be done by what worker node. And it's going to read the data available in the specific worker node. Generally, the task assigned to the worker node or the task will be assigned to the worker node where data is located. In big data space, especially Hadoop, always it will try to achieve the data locality. That's what we call as the resource availability, as well as the availability of the resource in terms of CPU, memory as well will be considered. Assume I have some data replicated in 3 machines. All 3 machines are busy doing the work and no CPU or memory available to start the other task. It will not wait for those machines to complete the job and get the resource and do the processing. It will start the processing in some other machine which is going to be near to that, the machines having the data, and read the data over the network. So to answer straight, worker machines are nothing but which does the actual work and going to report to the master in terms of what is the resource utilization, and the tasks running within the worker machines will be doing the actual work. And what is a sparse vector? Just few minutes back I was answering a question like what is a vector? Vector is nothing but representing the data in multidimensional form. A vector can be multidimensional vector as well. Assume I am going to represent a point in space. I need 3 dimensions, x, y and z. So the vector will have 3 dimensions. If I need to represent a line in the space, then I need 2 points to represent the starting point of the line and the end point of the line. Then I need a vector which can hold, so it will have 2 dimensions. The first dimension will have 1 point, the second dimension will have another point. At the same way, if I have to represent a plane, then I need another dimension to represent 2 lines. So each line will be representing 2 points. Same way I can represent any data using a vector form. Assume I have huge number of feedback or ratings of products across an organization. Let's take a simple example, Amazon. Amazon have millions of products. Not every user, not even a single user would have used millions of all the products within Amazon. So only hardly we would have used like a 0.1% or like even less than that. Maybe like few hundred products we would have used and rated the products within Amazon for the complete lifetime. If I have to represent all ratings of the products with a vector, I'll say the first position of the rating, it's going to refer to the product with ID 1. Second position, it's going to refer to the product with ID 2. So I'll have million values within that particular vector. Out of million values, I'll have only values for 100 products where I have provided the ratings. So it may vary from number 1 to 5. For all others, it will say 0. Sparse means thinly distributed. Yeah. So to represent the huge amount of data with the position saying this particular position is having a 0 value, we can mention that with a key and value. So what position having what value? Rather than storing all zeros, I can store only non-zeros, the position of it and the corresponding value. That means all others going to be a 0 value. So we can mention this particular sparse vector, mentioning it to represent the non-zero entities. So to store only the non-zero entities, the sparse vector will be used, so that we don't need to waste additional space while storing the sparse vector. Let's discuss some questions on Spark streaming. How is streaming implemented in Spark? Explain with examples. Spark streaming is used for processing real-time streaming data to precisely say it's a micro batch processing. So data will be collected between every small interval, say maybe like 0.5 seconds or every seconds, and it will get processed. So internally it's going to create micro batches. The data created out of that micro batch we call that is a D stream. D stream is like a RDD. So I can do transformations and actions, whatever that I do with RDD, I can do it with DStream as well. And Spark Streaming can read data from Flume, HDFS, or other streaming sources as well, and store the data in the dashboard or in any other database. And it provides a very high throughput, as it can be processed with a number of different systems in a distributed fashion. Again, DStream will be partitioned internally, and it has the built-in feature of fault tolerance. Even if any data is lost, any transformed RDD is lost, it can regenerate those RDDs from the existing or from the source data. So DStream is going to be the building block of streaming, and it has the fault tolerance mechanism what we have within the RDD. So DStream or specialized RDD, specialized form of RDD, specifically to use it within the Spark Streaming. Okay, next question, what is the significance of sliding window operation? That's a very interesting one. In the streaming data, whenever we do the computing, the data density or the business implications of that specific data may oscillate a lot. For example, within Twitter, we used to say the trending tweet hashtag. Just because that hashtag is very popular, maybe someone might have hacked into the system and used a number of tweets. Maybe for that particular hour, it might have appeared millions of times. Just because it appeared millions of times for that specific minute duration, or like say 2-3 minute duration, it should not get into the trending tag or trending hashtag for that particular day or for that particular month. So what we will do, we will try to do an average. So like a window, this current time frame and t-1, t-2, all the data we will consider, and we will try to find the average or sum. So the complete business logic will be applied against that particular window. So any drastic changes, or to precisely say the spike or dip, any drastic spike or drastic dip in the pattern of the data will be normalized. So that's the biggest significance of using the sliding window operation within Spark Streaming. And Spark can handle this sliding window automatically. It can store the prior data, the t-1, t-2, and how big the window needs to be maintained. All that can be handled easily within the program, handles at the abstract level. Next question is, what is DStream? The expansion is discretized stream. So that's the abstract form or the visual form of representation of the data for the Spark Streaming. The same way how RDD getting transformed from one form to another form, we will have series of RDDs all put together called as a DStream. So DStream is nothing but it's another representation of RDD, or like to group of RDDs. We call that as a DStream, and I can apply the streaming functions or any of the functions, transformations or actions available within the streaming against this DStream. So within that particular micro batch, so I'll define what interval the data should be collected or should be processed. We call that as a micro batch. It could be every 1 second or every 100 milliseconds or every 5 seconds. I can define that particular period. So all the data received in that particular duration will be considered as a piece of data, and that will be called as a DStream. Next question, explain caching in Spark Streaming. Of course, yes, Spark internally it uses in-memory computing. So any data when it is doing the computing that's getting generated, it will be there in memory. But further, if you do more and more processing with the other jobs, when there is a need for more memory, the least used RDDs will be cleared off from the memory, or the least used data available out of actions from the RDD will be cleared off from the memory. Sometimes I may need that data forever in memory. Very simple example like dictionary. I want the dictionary words should be always available in memory because I may do a spell check against the tweet commands or feedback commands a number of times. So what I can do, I can say cache those, any data that comes in, we can cache it or persist it in memory. So even when there is a need for memory by other applications, this specific data will not be removed. And especially that will be used to do the further processing. And the caching also can be defined, whether it should be in memory only or in memory and hard disk. That also we can define it. Let's discuss some questions on Spark GraphX. So next question is there an API for implementing graphs in Spark? So in graph theory, everything will be represented as a graph. When I say graph, it will have nodes and edges. So all will be represented using the RDDs. So it's going to extend the RDD, and there is a component called GraphX and it exposes the functionalities to represent a graph. We can have a Edge RDD, Vertex RDD. By creating the edges and vertex, I can create a graph. And this graph can exist in a distributed environment. So same way, we will be in a position to do the parallel processing as well. So GraphX is just a form of representing the data, the graphs with edges and vertices. And of course, yes, it provides the API to implement or to create the graph, do the processing on the graph. The APIs are provided. What is PageRank in GraphX? So within GraphX, once the graph is created, we can calculate the PageRank for a particular node. So that's very similar to how we have the PageRank for the websites within Google. The higher the PageRank, that means it's more important within that particular graph. It's going to show the importance of that particular node or edge within that particular graph. When I say graph, it's a connected set of data. All data will be connected using the property, and how much important that property makes. We will have a value associated to it. So within PageRank, we can calculate like a static PageRank. It will run a number of iterations. Or there is another PageRank or dynamic PageRank that will get executed till we reach a particular saturation level. And the saturation level can be defined with multiple criteria. And the APIs, we call that as a graph operations, can be directly executed against those graph, and they all are available as API within the GraphX. What is lineage graph? So the RDD is very similar to the GraphX, how the graph representation. Every RDD internally, it will have the relation saying how that particular RDD got created and from where, how that got transformed. RDD is how they got transformed. So the complete lineage or the complete history or the complete path will be recorded within the lineage. That will be used in case if any particular partition of that RDD is lost, it can be regenerated. Even if the complete RDD is lost, we can regenerate. So it will have the complete information on what all partitions, where it is existing, what all transformations it had undergone, what is the resultant value. If anything is lost in the middle, it knows where to recalculate from and what all essential things needs to be recalculated. It's going to save us a lot of time. And if that RDD is never being used, it will never get recalculated. So the recalculation also triggers based on the action. Only on need basis it will recalculate. That's why it's going to use the memory optimally. Does Apache Spark provide checkpointing? Especially like take the example like streaming. And if any data is lost within that particular sliding window, we cannot get back the data, or like the data will be lost. Assume I'm making a window of say 24 hours. To do some average, I'm making a sliding window of 24 hours. Every 24 hours it will keep on getting slided. And if you lose any system, assume there is a complete failure of the cluster, I may lose the data because it's all available in the memory. So how to recalculate if the data system is lost? It follows something called a checkpointing. So we can checkpoint the data, and directly it's provided by the Spark API. We have to just provide the location where it should get checkpointed. And you can read that particular data back when you start the system again. Whatever the state it was in, we can regenerate that particular data. So yes, to answer the question straight, Apache Spark provides checkpointing, and it will help us to regenerate the state what it was earlier. Let's move on to the next component, Spark Mlib. How is machine learning implemented in Spark? So machine learning, again, it's a very huge ocean by itself, and it's not a technology specific to Spark. Machine learning is a common data science. It's a subset of data science world, where we have different type of algorithms, different categories of algorithm like clustering, regression, dimensionality reduction, all that we have. And all these algorithms, or most of the algorithms, have been implemented in Spark. And Spark is the preferred framework or preferred application component to do the machine learning algorithm nowadays, or machine learning processing. The reason because most of the machine learning algorithms needs to be executed iteratively a number of times till we get the optimal result. Maybe like say 25 iterations or 50 iterations, or till we get that specific accuracy. We will keep on running the processing again and again. And Spark is very good fit whenever you want to do the processing again and again. Because the data will be available in memory, I can read it faster. store the data back into the memory, again read it faster. And all these machine learning algorithms have been provided within the Spark as a separate component called Mlib. And within Mlib, we have other components like featureization to extract the features. You may be wondering how we can process the images. The core thing about processing an image or audio or video is about extracting the feature and comparing the feature, how much they are related. So that's where vectors, matrices, all that will come into picture. And we can have pipeline of processing as well. Do the processing 1, then take the result and do the processing 2. And it has persistence algorithm as well. The result of it, the generated or processed result, it can be persisted and reloaded back into the system to continue the processing from that particular point onwards. Next question, what are categories of machine learning? Machine learning as such, different categories available: supervised, unsupervised, and reinforced learning. Supervised, unsupervised, it's very popular, where we will know, I'll give with an example. I'll know well in advance what category that belongs to. Assume I want to do a character recognition. While training the data, I can give the information saying this particular image belongs to this particular category, character, or this particular number, and I can train. Sometimes I'll not know well in advance. Assume like I may have different type of images, like it may have cars, bikes, cat, dog, all that. I want to know how many category available. I'll not know well in advance. So I want to group it, how many category available. And then I'll realize saying, okay, all this belongs to a particular category. I'll identify the pattern within that category and I'll give a category name. Say like all these images belongs to boat category, or looks like a boat. So leaving it to the system by providing this value or not. That's where the different type of machine learning comes into picture. And as such, machine learning is not specific to Spark. It's going to help us to achieve to run these machine learning algorithms. What are Spark Mlib tools? Mlib is nothing but machine learning library or machine learning offering within the Spark. It has a number of algorithms implemented, and it provides a very good feature to persist the result. Generally in machine learning, we will generate a model. The pattern of the data, we call that as a model. The model will be persisted either in different forms like parquet, arrow, different forms it can be stored or persisted, and has methodologies to extract the features from a set of data. I may have a million images. I want to extract the common features available within those millions of images, and there are other utilities available to process, to define, or like to define the seed, the randomizing it. So different utilities available, as well as pipelines. That's very specific to Spark, where I can channel or arrange the sequence of steps to be undergone by the machine learning. So machine learning 1 algorithm first, and then the result of it will be fed into machine learning algorithm 2. Like that, we can have a sequence of execution, and that will be defined using the pipelines. These all are inbuilt features of Spark Mlib. What are some popular algorithms and utilities in Spark Mlib? So these are some popular algorithms like regression, classification, basic statistics, recommendation systems. Recommendation system is like well implemented. All we have to provide is give the data. If you give the ratings and products within an organization, if you have the complete dump, we can build the recommendation system in no time. And if you give any user, it can give a recommendation. These are the products the user may like, and those products can be displayed in the search result. Recommendation system purely works on the basis of the feedback that we are providing for the earlier products that we had bought. Clustering, dimensionality reduction. Whenever we do processing with a huge amount of data, it's very, very compute intensive, and we may have to reduce the dimensions, especially the matrix dimensions within the Mlib, without losing the features. Whatever the features available, without losing it, we should reduce the dimensionality. And there are some algorithms available to do that dimensionality reduction. And feature extraction. So what are all the common features or features available within that particular image? And I can compare what are all the common features available within those images. That's how we will group those images. So get me whether this particular image, the person looking like this image available in the database or not. For example, assume the organization or the police department, crime department maintaining a list of persons committed crime. And if they get a new photo, when they do a search, they may not have the exact photo bit by bit. The photo might have been taken with a different background, different lightings, different locations, different time. So 100% the data will be different, or bits and bytes will be different. But look-wise, yes, they are going to be same. So I'm going to search the photo looking similar to this particular photograph as the input I'll provide. To achieve that, we will be extracting the features. In each of those photos, we will extract the features and we will try to match the feature rather than the bits and bytes. And optimization as well, in terms of processing or doing the piping, there are a number of algorithms to do the optimization. Let's move on to Spark SQL. Is there a module to implement SQL in Spark? How does it work? So directly not the SQL, maybe very similar to Hive. Whatever the structured data that we have, we can read the data or extract the meaning out of the data using SQL. And it exposes the API, and we can use those API to read the data or create data frames. And Spark SQL has 4 major categories: data source, data frame. Data frame is like the representation of X and Y data, or like a Excel data, multidimensional structure data in abstract form. On top of data frame, I can do the query. And internally it has the interpreter and optimizer. Any query I fire, that will get interpreted or optimized and will get executed using the SQL services and get the data from the data frame, or it can read the data from the data source and do the processing. What is a parquet file? It's a format of the file where the data in some structured form, especially the result of the Spark SQL, can be stored or returned in some persistence. And the parquet, again, it is a open source from Apache. It's a data serialization technique where we can serialize the data using the parquet form. And to precisely say, it's a columnar storage. It's going to consume less space. It will use the keys and values and store the data. And also it helps you to access a specific data from that parquet form using the query. So parquet, it's another open source format, data serialization form, to store the data or persist the data as well as to retrieve the data. List the functions of Spark SQL. It can be used to load the varieties of structured data. Of course, yes, Spark SQL can work only with the structured data. It can be used to load varieties of structured data. And you can use SQL-like statements to query against the program. And it can be used with external tools to connect to the Spark as well. It gives a very good integration with the SQL. And using Python, Java, or Scala code, we can create an RDD from the structured data available. Directly using the Spark SQL, I can generate the RDD. So it's going to facilitate the people from database background to make the program faster and quicker. Next question is, what do you understand by lazy evaluation? So whenever you do any operation within the Spark world, it will not do the processing immediately. It will look for the final result that we are asking for it. If it doesn't ask for the final result, it doesn't need to do the processing. So based on the final action, till we do the action, there will not be any transformations, or there will not be any actual processing happening. It will just understand what are transformations it has to do. Finally, if you ask for the action, then in an optimized way, it's going to complete the data processing and get us the final result. So to answer straight, lazy evaluation is doing the processing only on need of the resultant data. If the data is not required, it's not going to do the processing. Can you use Spark to access and analyze data stored in Cassandra database? Yes, it is possible. Okay, not only Cassandra, any of the NoSQL database, it can very well do the processing. And the Cassandra also works in a distributed architecture. It's a NoSQL database. So it can leverage the data locality. The query can be executed locally where the Cassandra nodes are available. That's going to make the query execution faster and reduce the network load. And Spark executors, it will try to get started, or the Spark executors in the machine where the Cassandra nodes are available or data is available, it's going to do the processing locally. So it's going to leverage the data locality. Next question, how can you minimize data transfers when working with Spark? If you ask the core design, the success of the Spark program depends on how much you are reducing the network transfer. Because network transfer is very costly operation and you cannot parallelize. It gives multiple ways, or especially two ways to avoid this. One is called broadcast variable and accumulators. Broadcast variable, it will help us to transfer any static data or any informations, keep on publishing it to multiple systems. So I'll say if any data to be transferred to multiple executors to be used in common, I can broadcast it. Or I might want to consolidate the values happening in multiple workers in a single centralized location. I can use accumulator. So this will help us to achieve the data consolidation or data distribution in the distributed world at the API level or at the abstract level, where we don't need to do the heavy lifting. That's taken care by the Spark for us. What are broadcast variables? Just now, as we discussed, the value, the common value that we need, I may want that to be available in multiple executors, multiple workers. Simple example, you want to do a spell check on the tweet comments. The dictionary, which has the right list of words, I'll have the complete list. I want that particular dictionary to be available in each executor, so that with a task that's running locally in those executors can refer to that particular map task and get the processing done by avoiding the network data transfer. So the process of distributing the data from the Spark context to the executors where the task is going to run is achieved using broadcast variables. And it's built in within the Spark API. Using the Spark API, we can create the broadcast variable. And the process of distributing this data available in all executors is taken care by the Spark framework. Explain accumulators in Spark. The similar way how we have broadcast variables, we have accumulators as well. Simple example, you want to count how many error records are available in the distributed environment. Assume data is distributed across multiple systems, multiple executors. Each executor will do the processing, count the records, and atomically I may want the total count. So what I'll do, I'll ask to maintain an accumulator. Of course, it will be maintained in the Spark context in the driver program, because the driver program going to be one per application. It will keep on getting accumulated, and whenever I want, I can read those values and take any appropriate action. So it's like more or less the accumulators and broadcast variables looks opposite to each other, but the purpose is totally different. Why is there a need for broadcast variable when working with Apache Spark? It's a read-only variable and it will be cached in memory in a distributed fashion, and it eliminates the work of moving the data from a centralized location, that is a Spark driver or from a particular program, to all the executors within the cluster where the task is going to get executed. We don't need to worry about where the task will get executed within the cluster. So when compared with the accumulators, broadcast variables, it's going to have a read-only operation. The executors cannot change the value. It can only read those values. It cannot update. So mostly it will be used like a cache that we have for the RDD. Next question, how can you trigger automatic cleanups in Spark to handle accumulated metadata? So there is a parameter that we can set, TTL, that will get triggered along with the running jobs, and intermediately it's going to write the data result into the disk or clean the unnecessary data or clean the RDDs that's not being used. The least used RDD, it will get cleaned and it will keep the metadata as well as the memory clean. What are the various levels of persistence in Apache Spark? When we say data should be stored in memory, it can be in different levels, it can be persisted. So it can be in memory only, or memory and disk, or disk only. And when it is getting stored, we can ask it to store it in a serialized form. So the reason why we may store or persist is, I want this particular RDD, this form of RDD later back for reusing. So I can read it back. Maybe I may not need it very immediately, so I don't want that to keep occupying my memory. I'll write it to the disk and I'll read it back whenever there is a need. I'll read it back. The next question, what do you understand by schema RDD? So schema RDD will be used especially within the Spark SQL. So the RDD will have the meta information built into it. It will have the schema also, very similar to what we have the database schema, the structure of that particular data. And when I have the structure, it will be easy for me to handle the data. So data and the structure will be existing together. And the schema RDD now it's called as a data frame within Spark. And data frame term is very popular in languages like R, SAS, other languages, it's very popular. So it's going to have the data and the meta information about that data, saying what column, what structure it is in. Explain a scenario where you will be using Spark streaming. Assume you want to do a sentiment analysis of tweeters. So data will be streamed. So we will use a Flume sort of a tool to harvest the information from Twitter and feed it into Spark streaming. It will extract or identify the sentiment of each and every tweet and mark it whether it is positive or negative. And accordingly, the data will be the structured data, the tweet ID, whether it is positive or negative, maybe percentage of positive and percentage of negative sentiment. Store it in some structured form. Then you can leverage the Spark SQL and do grouping or filtering based on the sentiment. And maybe I can use a machine learning algorithm. What drives that particular tweet to be in the negative side? Is there any similarity between all those negative tweets? Maybe it's specific to a product or specific time by when the tweet was tweeted, or from a specific region the tweet was tweeted. So those analysis could be done by leveraging the Mlib of Spark. So Mlib, streaming, core, all going to work together. All these are like different offerings available to solve different problems. I hope you all enjoyed. Thank you, folks.
I hope you have enjoyed listening to this video. Please be kind enough to like it, and you can comment any of your doubts and queries, and we will reply them at the earliest. Do look out for more videos in our playlist and subscribe to Edureka channel to learn more. Happy learning!